Have you ever wondered how computers learn to see, speak, and even create? The answer lies in the fascinating world of machine learning, and at the heart of many of its most incredible advancements is a powerful tool, PyTorch. Before we get started, a quick note. All of the code examples for this course are hosted on our GitHub repository. Just click the link in the description of this video to access everything. Feel free to clone, explore, and follow along as we go. In this complete tutorial, we'll take you on a journey from a complete beginner to a confident PyTorch practitioner. But first, why PyTorch? What makes it the framework of choice for so many researchers, developers, and AI giants? The beauty of PyTorch lies in its simplicity and Python-first approach. If you're familiar with Python, you'll feel right at home. It's intuitive, easy to learn, and allows for rapid experimentation. This means you can spend more time bringing your ideas to life and less time wrestling with complex code. One of PyTorch's most celebrated features is its dynamic computational graph. Imagine building your machine learning models on the fly, with the flexibility to change and adapt them as you go. This define by run philosophy is a game changer for researchers and anyone pushing the boundaries of what's possible in AI. It makes debugging a breeze and empowers you to create complex and innovative neural networks with ease. But PyTorch isn't just for research. It's a production-ready framework with a robust ecosystem of tools and libraries that streamline the process of deploying models in real-world applications. From natural language processing that powers a new generation of chatbots to computer vision that enables self-driving cars, PyTorch is at the forefront of AI innovation. By learning PyTorch, you're not just learning a framework, you're unlocking the potential to build the future. You're joining a vibrant and growing community of developers and researchers who are solving some of the world's most challenging problems. So, if you're ready to dive into the world of deep learning and build intelligent systems that can learn and reason, you're in the right place. Get ready to master PyTorch and let's start building the future together. Welcome back. In this first practical step, we'll do the most fundamental thing you need to do in any PyTorch project: import the library itself. On the screen, you can see the essential line of code. It's as simple as it gets in Python. Import torch. We import the library and give it the alias torch. This is a universal convention in the PyTorch community. You'll see torch used in virtually every tutorial, research paper, and open source project. Sticking to this standard makes your code instantly recognizable and easier for others to understand. Now, before we dive into creating tensors or building models, there's a small but crucial best practice I want you to adopt: checking your PyTorch version. Why is this important? Well, the world of AI moves fast. PyTorch is constantly being updated with new features, performance improvements, and bug fixes. Knowing your version helps you debug issues, look up the correct documentation, and ensure that if you share your code with someone else, they can create the same environment to get the same results. You can easily do this by printing the version attribute. When you run this, you'll see an output telling you the exact version you have installed. With that one import statement, we now have the full power of the PyTorch library at our fingertips. In the next section, we'll start using it to create the core data structure of PyTorch, tensors. Alright, let's talk about the single most important concept in PyTorch, the tensor. The name might sound a bit intimidating, but the idea is actually very simple. A tensor is just a container for numbers, a way to organize data. In fact, all the data you'll ever feed into a neural network and all the internal parameters of the network itself will be stored in tensors. So let's build up the intuition, starting from the ground up. At the most basic level, we have a scalar. You can see on the slide this is called a zero-dimensional tensor. Don't worry about the dimension part yet. Just think of it as a single number. For example, the number 5. That's a scalar. Now, what if we have a list of numbers? Maybe the prices of 3 different items in a shopping cart. That's a vector, which is a one-dimensional tensor. It's just a sequence of numbers in a single row. Okay? Let's take it one step further. Imagine arranging numbers in a grid with rows and columns, just like a spreadsheet or a tic-tac-toe board. This is a matrix or a two-dimensional tensor. A black and white image is a great example of a matrix, where each number represents the brightness of a pixel. So, tensor is really the umbrella term that covers all of these. A scalar is a tensor, a vector is a tensor, and a matrix is a tensor. The real power comes from the fact that tensors can handle even more dimensions. A color image is often a 3D tensor, with dimensions for height, width, and color information. A video could be a 4D tensor. So, to put it simply, tensors are the language of data for PyTorch. By understanding this simple hierarchy from scalars to vectors to matrices and beyond, you've already grasped the core concept you'll use throughout your entire deep learning journey. Here, we are going to unravel the mystery behind tensors and learn how to build them from the ground up. By the end of this, you'll see that they're just simple building blocks for all the amazing things we can do in deep learning. Let's get started. All right. Let's start with the simplest building block, the scalar. Think of a scalar as just a single, lonely number. It has 0 dimensions. In our code, we've created a tensor holding the number 42. When we ask for its dimensions, PyTorch says 0, and if we want the actual Python number back, we use the .item method. Easy peasy. It's the atom of our data universe. Next up, the vector. Now that we have our atom, let's build a molecule. If a scalar is a single number, a vector is a list of numbers, all in a single row. It has 1 dimension. Here, our vector holds the numbers 2 and 3. You can see it has 1 dimension, and its shape tells us it has a length of 2. It's like a single list of your favorite things, or coordinates on a map. Now things are getting interesting with the matrix. A matrix is a grid of numbers with rows and columns, just like a spreadsheet or a tic-tac-toe board. It has 2 dimensions. Our matrix here is a 3 by 3 grid. PyTorch confirms it has 2 dimensions, and its shape is 3, 3, meaning 3 rows and 3 columns. This is a crucial step up, as 2D tensors are the standard way we represent things like grayscale images, where each number is a pixel's brightness. Finally, let's enter the 3rd dimension with a 3D tensor. Imagine taking a bunch of those matrices we just made and stacking them on top of each other. That's a 3D tensor. It has 3 dimensions. Our example here has a shape of 1, 2, 2. You can read that as I have 1 matrix, and each matrix has 2 rows and 2 columns. These are perfect for more complex data. For example, a color image is often a 3D tensor with 3 2D matrices for the red, green, and blue color channels. They're also great for sequences, like a series of measurements over time. So, to wrap it all up, the main difference between all these tensors is simply the number of dimensions they have. A scalar is a point, a vector is a line, a matrix is a flat square, and a 3D tensor is a cube. Each one adds a new dimension, allowing us to represent more and more complex data. As you get into more advanced deep learning, you'll use tensors with even more dimensions, but they all build from these simple fundamental ideas. Now that we know how to create basic tensors by hand, let's dive into the PyTorch playground and learn some powerful functions that let us create common types of tensors automatically. These are the tools you'll be using every day. Random tensors. First up is the torch.rand function. This is your go-to for creating tensors filled with random numbers between 0 and 1. It's incredibly useful for initializing the weights in a neural network, giving it a random starting point to begin learning. You'll notice the torch.manualSeed42 line. That's our little magic trick to ensure that every time we run this code, we get the exact same random numbers. This is critical for making our experiments reproducible, so if we find a great result, we can get it again, zeros and ones. Sometimes you don't want random numbers. You just need a tensor of a specific shape filled with a default value. That's where torch.zeros and torch.ones come in. They are perfect for creating placeholder tensors that you'll fill with data later, or for creating masks to hide or show parts of another tensor. Here we've made a ghost grid of zeros and a cloud array of ones. Simple, clean, and very useful for a wide variety of tasks. A range of numbers. What if you need a sequence of numbers, like a timeline or a set of indices? Torch arrange is your friend. It works just like Python's built-in range function. You give it a start, an end, and a step, and it creates a 1D tensor or vector with those values. Our step ladder starts at 5, goes up by 3, and stops before it reaches 15. It's a quick and easy way to generate predictable sequences without having to type them all out by hand, creating tensors like others. Finally, one of the most convenient tricks in the book, the like functions. Let's say you have a tensor and you need another one with the exact same shape and data type, but filled with zeros. Instead of manually checking the shape and type and then passing them to torch zeros, you can just use torch zeros like. It's like using a cookie cutter. It takes all the properties from your input tensor and creates a new one based on that template. It's clean, efficient, and helps you write less error-prone code. There are other versions too, like ones-like and rand-like, and that's a wrap on our tensor creation playground. With these functions, you're now equipped to create all kinds of tensors for your future projects. In our journey with PyTorch, we've learned how to create tensors. Now, we're going to zoom in on a critical detail, the data type or dtype. Think of dtypes as different materials you can build your tensors from. Some are heavy and precise, others are light and fast. Choosing the right one is key to building efficient and effective models. Let's explore the toolbox. Floating point types, the standard. First up, we have the floating point types, which are used for numbers with decimal points. The absolute champion and default type in PyTorch is torch.float32. It gives you a fantastic balance of precision and performance, making it the standard for training nearly all neural networks. But what if you're a scientist running a high-stakes physics simulation where the tiniest rounding error could throw off your results? That's when you bring out the heavyweight, torch.float64 or double precision. It's twice as big and much slower, but it gives you incredible precision. For most deep learning, it's overkill, but for scientific computing, it can be essential. Floating point types, the speedsters. Now, let's talk about speed. In the world of massive models, Float32 can be slow and memory hungry. This is where the 16-bit floats come in. Torch.float16 cuts memory usage in half, which can dramatically speed up training on modern GPUs. The trade-off is a much smaller numerical range, which can sometimes cause issues. To solve that, Google introduced torch.bfloat16. It maintains the same large range as Float32 while still using only 16 bits by sacrificing some decimal precision. This makes it much more stable for training, and it's quickly becoming the new favorite for high-performance computing on TPUs and the latest GPUs. Integer types, the counters. Next, we have integers, whole numbers. The most common one you'll see is torch.uint8, the unsigned 8-bit integer. It holds values from 0 to 255. Why is that range important? It's the standard for representing pixel intensities in digital images. So whenever you load an image, it's likely coming in as a uint8 tensor. For other tasks, like representing categories, labels, or indices, we use signed integers like torchInt64. If you have 10 classes in a classification problem, their labels will be stored as integers, typically in a int64 tensor, specialized types. The specialist. PyTorch also has specialists for specific jobs. The torch.bool type is incredibly simple. It's just true or false. Its main job is to create masks. You can perform a comparison, like asking which values are positive to get a Boolean tensor, and then use that mask to filter, select, or modify data. It's a fundamental technique for data manipulation. And for our friends in engineering and physics, we have complex number types like torch.complex64. These are essential for any work involving signal processing, like audio analysis with Fourier transforms, or simulations in quantum physics, quantized types, the optimizers. Finally, we have one of the coolest tricks for model deployment, quantization. After you've trained your big, powerful Float32 model, you often need to run it on a less powerful device, like a smartphone. Quantized types, like torch.kint8, allow you to convert your model's weights into highly efficient 8-bit integers. This process makes the model drastically smaller and faster for inference, usually with only a tiny acceptable drop in accuracy. It's the key to getting your models out of the lab and into the real world. Alright, so far we've learned how to create tensors with different shapes and data types. Now let's look at 3 incredibly important arguments you can set when creating a tensor: device, dtype, and requires grad. These are what give you fine-grained control and unlock the full power of PyTorch. First, we have this line, device equals torch dot. Device open parenthesis CUDA:0 if torch.CUDA dot is available, else CPU close parenthesis. This is a standard and very important piece of code. It checks if your computer has a compatible NVIDIA GPU which uses CUDA. If it does, it sets the device to CUDA. If not, it defaults to the CPU. When we create our tensor, we pass in this device variable. This tells PyTorch, I want this tensor to live and perform its calculations on the fastest hardware available. Moving tensors to the GPU is the key to accelerating deep learning training. Next, we have dtype equals torch.bfloat16. We're being very specific here. As we learned in our dtypes tutorial, bfloat16 is a modern, memory-efficient format that's great for training large models on the latest hardware. By setting this explicitly, we are making a conscious choice to optimize for performance and memory usage. Finally, and this is perhaps the most magical part of PyTorch, we have requires grad equals true. This is the switch that turns on PyTorch's automatic differentiation engine called AutoGrad for this specific tensor. By setting this to true, we're telling PyTorch, keep an eye on this tensor. I want you to track every operation it's involved in, because later I'm going to need to calculate the gradient with respect to it. This is the absolute foundation of how neural networks learn. It allows PyTorch to automatically figure out how to adjust this tensor's values to improve the model's performance during backpropagation. So, to sum it up, with these 3 arguments, we're not just creating a simple array of numbers. We are creating a sophisticated computational object, placing it on the optimal hardware for speed, defining its numerical precision for efficiency, and enabling it to be automatically updated as part of a learning process. This is what makes PyTorch so powerful. We're going to take a tour of the basic arithmetic you can perform on PyTorch tensors. It's easier and more intuitive than you might think. Let's start with our headliner act. A tensor we'll call galaxy scores. It's just a simple 1D tensor holding a few numbers. Now, what happens if we want to give every score a boost? We can just take our tensor and add a number to it, like galaxy on scores plus 5. PyTorch is smart enough to perform this operation on every single element in the tensor, creating a brand new tensor with the uplifted scores. The same thing works for multiplication. If we want to hit the warp drive and multiply all our scores by 3, we just use the star operator. Again, this creates a new tensor, warp or multiplied, with the results. But here's a key point and a common source of confusion. Notice that our original galaxy scores tensor hasn't changed at all. The operations we just did created new tensors. The original data remains untouched unless we explicitly tell PyTorch to change it. So how do we do that? Through reassignment. If we want to apply an alien tax and subtract 2 from our scores, we can do the calculation and then assign the result right back to the galaxy charn scores variable. Now, the original tensor variable points to this new updated data. Let's do it again with a star bonus of plus 10. See? The scores are updated in place. While using simple operators like plus and star is common, PyTorch also provides equivalent functions like torch.multiply. This does the exact same thing as the star operator, but can sometimes make the code's intent a bit clearer. Finally, the real power comes from element-wise operations between two tensors of the same shape. For example, if we want to square every score, we can just multiply the galaxy scores tensor by itself. PyTorch will match up each element and multiply it with its corresponding partner in the other tensor. And that's it. You now know the basics of tensor arithmetic in PyTorch. You can add, subtract, multiply, and perform powerful element-wise operations with a syntax that's clean, simple, and easy to read. And that brings us to the end of the first part of our PyTorch journey. Let's quickly recap everything we've accomplished. We started from the very beginning, understanding what a tensor is and how to create them, from simple scalars and vectors all the way to multidimensional tensors. We explored the tensor creation playground, learning powerful functions like rand, zeros, and arrange. We then took a deep dive into the all-important concept of data types, or dtypes, learning how to choose the right tool for the right job, whether it's the standard float 32, the speedy bfloat 16, or the efficient int8 for quantization. Finally, we put it all together, learning how to perform basic arithmetic and, most importantly, how to control our tensors with device, dtype, and the magic of requires grad. You now have a rock-solid foundation in the fundamental building blocks of PyTorch. With these skills, you are more than ready for what comes next. In the second part of this series, we're going to take these fundamentals and start building. We'll look at more advanced operations, explore how to build our very first neural network, and really start to unlock the power of deep learning. I can't wait to share it with you, and it will be coming very soon. If you found this tutorial helpful and you're excited for part 2, please consider supporting the channel. Go ahead and hit that like button, subscribe so you don't miss the next video, and make sure to ring that notification bell to be the first to know when it drops. Thank you so much for learning with me today. Keep experimenting, stay curious, and I'll see you in the next one. Welcome back to BrainOmega. In this second part of our comprehensive PyTorch tutorial, we're starting with something that every deep learning project relies on: random tensors. Randomness is everywhere in machine learning, from initializing model weights, shuffling datasets, generating synthetic inputs, to even simulating images. PyTorch gives us powerful and flexible tools to work with randomness, and today we'll explore the most commonly used functions. Let's start with the basics. Torch.rand gives us a tensor filled with random values from a uniform distribution between 0 and 1. If you want values from a normal distribution, which is especially common when initializing model parameters, you can use torch.random. For discrete values like class labels or indexing, torch.randint comes in handy. And when you need a tensor that matches the shape of an existing one, use torch.rand-like or torch.randan-like. This is especially helpful when working inside model layers where shape compatibility matters. We also showed how you can create a random tensor using the size argument explicitly, like torch.rand size 3, 4. This gives you more clarity when you're building dynamic shapes in functions or loops. Plus, we generated a random tensor shaped like an image, 224, 224, 3, mimicking the format of an RGB image. This is perfect for testing computer vision models when real data isn't available yet. Now here's a critical tip. Randomness in ML should be reproducible. That's where torch.manual seed comes in. By setting a fixed seed, you ensure that your random values remain the same across multiple runs. This is absolutely essential in research and production, whether you're comparing training results or trying to reproduce the outcome of a paper. Controlling randomness means controlling your experiments. Alright, now that we've mastered random tensors, let's take a look at two of the simplest and most essential tensor operations in PyTorch. Torch.zeros and torch.ones. These functions create tensors that are fully initialized with zeros or ones. They're incredibly useful in many real-world scenarios, from padding and masking to debugging tensor shapes or even creating baseline model inputs. Let's look at a few examples. First, we create a 2x3 zero tensor using torch.zeros 2, 3. Then we create a 2's3 tensor filled with ones using torch.ones 2, 3. Next, we demonstrate how to generate a tensor of ones that has the same shape as another tensor using torch.ones-like. This is great when you need to preserve shape compatibility in your model's computation graph. Then we go a step further and use the size keyword to explicitly specify tensor shape. This is helpful when you're defining tensors inside functions or with dynamic dimensions. Torch.zeros size 3, 4 creates a 3x4 zero-filled tensor. Torch.ones size 3, 4 does the same but fills it with ones. You'll also notice we print out the dtype of each tensor, which tells us what kind of numbers it holds. This can be important when matching tensors during arithmetic operations or neural network layers. Want to go even further? You can also set a custom data type and run these tensors on your GPU. The full code from this video is available on our GitHub page, and you'll find the link in the description of this video. Feel free to run the code on your machine, modify it, and follow along as we move forward. Up next, we'll see how these random tensors tie into model weight initialization, data augmentation, and even synthetic data set generation for training and evaluation. In this section, we're diving into one of the most important operations in all of deep learning, matrix multiplication. Whether you're building a neural network, a transformer model, or an image classifier, matrix multiplication is happening behind the scenes, a lot. Let's walk through the main functions you'll use in PyTorch to multiply matrices. First, we have torch.me. This performs matrix multiplication, but only for 2D tensors, your classic math matrix. If you try using it with tensors that aren't 2D, you'll get an error. Then we have torch.matmul. This is more flexible. It works with scalars, vectors, matrices, and even batched matrices. If you're ever unsure, this is your go-to. And if you like Pythonic syntax, you can just use the @ symbol. It behaves just like torch.matmul, and it makes your code cleaner. For batches of matrices, like in mini-batch training, use torch EMM. It works only on 3D tensors where the first dimension is the batch size. And finally, if you want total control, use torch.einsum. It's based on Einstein notation and lets you define custom multiplications like inner products, transposed operations, or diagonal extractions. For example, ik kj to ij is standard matrix multiplication. But with einsum, you can also do things like I to extract a diagonal. These tools give you complete control over how you compute, and understanding them is critical for building advanced models. We'll also look at element-wise operations, shape errors, and how not to do it with for loops. Let's start with something that often confuses beginners. When you write tensor asterisk tensor, you're not doing matrix multiplication. You're doing element-wise multiplication. That means PyTorch will multiply each element of one tensor with the element in the same position of the other tensor. For actual matrix multiplication, you should use torch.matmul tensoren tensor2 or the shorthand tensoren at sign tensor2. So, while the at sign symbol is clean and Pythonic, it's not always ideal for beginners because it can hide what's really going on under the hood. Stick to torch.matmul when you're learning. Now, here's a common pitfall. Your tensors need to be shaped correctly. For matrix multiplication to work, the number of columns in the first matrix must match the number of rows in the second. For example, trying to multiply a 3x2 matrix with another 3x2 matrix will throw a shape mismatch error. Always check your tensor shapes before multiplying. And here's a big one. Never implement matrix multiplication manually using for loops in Python. It's slow and inefficient. PyTorch already uses optimized C++ and CUDA backends under the hood. We'll show this with a timing comparison using %% time. The PyTorch version finishes instantly, while the loop-based one takes much longer. Your go-to place for mastering deep learning step by step. In this part of the tutorial, we're diving into something that comes up in almost every PyTorch project: reduction operations. This code demonstrates how to perform essential reduction operations on a PyTorch tensor, including calculating the minimum, maximum, mean, and sum, along with a more advanced example using dimension-wise reduction. It starts by generating a 3-4 tensor filled with random floating point values between 0 and 1 using torch.rand.3-4. This 2D tensor acts like a small data batch or matrix. The script then applies torch.min tensor and torch.max tensor to find the smallest and largest values in the entire tensor, respectively, useful for understanding data ranges or identifying outliers. Next, torch.mean tensor calculates the average of all elements in the tensor, providing a single scalar summary. Similarly, torch.sum tensor computes the total sum of all elements. Both are commonly used in training loops for aggregating loss values, gradients, or accuracy measures. The final line, torch.mean tensor dimba1, showcases a powerful technique, reducing across a specific dimension. In this case, it computes the mean across each row, returning a 1D tensor with one mean value per row. This is especially useful when working with batches of data, where you might want to compute statistics for each item in the batch separately. Altogether, this example highlights how PyTorch allows you to easily extract key insights from tensors, whether globally or across dimensions, using highly optimized operations. We are going to explore one of the most fundamental aspects of working with tensors in PyTorch: how to reshape and manipulate tensor dimensions. Whether you're preparing inputs for a model, managing batches of data, or dealing with output layers, knowing how to reshape and reformat your tensors is essential. We start with a basic 2x3 tensor and use the .view method to reshape it into a 3x2 tensor. The bot view function allows us to reorganize the shape of a tensor as long as the total number of elements stays the same. Alternatively, we could also use torch.reshape for the same purpose. Reshaping is a core operation that you'll use anytime you're adjusting data for compatibility with a model layer. Next, we demonstrate torch.stack, which lets us combine multiple tensors along a new dimension. For example, stacking two 1D tensors will give us a 2D tensor. This is incredibly helpful when building batches or aligning sequences for processing in RNNs or transformers. Then, we move on to torch.squeeze. This function removes any dimensions of size 1. It's especially useful when you have tensors that come from data loaders or inference steps where extra singleton dimensions often appear. By squeezing a tensor with shape 1, 3, 1, 5, we reduce it down to a cleaner 3, 5 shape. Now, the inverse of squeeze is torch unsqueeze, which adds a new dimension of size 1 wherever we need it. This is particularly useful when a model expects a batch dimension and you're feeding in a single sample. For instance, converting a 1D tensor with shape 3 into 1, 3 makes it compatible with batch-based operations. Finally, we look at torch.permute, which lets us rearrange the order of dimensions. Unlike reshape, permute doesn't change the data layout, just how dimensions are ordered. This is very common when switching between formats like NCHW and NHWC in image processing or adjusting tensor shapes for attention layers. Together, these operations form the backbone of tensor manipulation in PyTorch. You'll use them in almost every serious project, from data pre-processing to output formatting. We're diving into a skill you'll use constantly in PyTorch, indexing and selecting data from tensors. Whether you're feeding inputs into a model, slicing batches, or extracting specific outputs, understanding how to access parts of a tensor is absolutely essential. We begin with a simple 3x3 tensor filled with values ranging from 10 to 90. PyTorch allows you to access any individual element by specifying its row and column. For example, if you say row 1, column 2, you'll get the value sitting in the second row and the third column. That's index 1, 2 in code. You can also select an entire row, for instance, getting the first row by using just index 0. To access a full column, like the second column, we use the colon symbol to mean all rows, followed by the index for that column, in this case 1. We also demonstrate slicing, for example saying rows 0 to 1, columns 1 to 2 gives you a small subtensor taken from the top right portion. This is very useful when working with mini batches or cropping parts of your data. Now here's something even cooler. PyTorch supports what's called fancy indexing. That means you can pass in lists of positions, like choosing the item from row 0 in column 1 and another from row 2 in column 2, all in a single operation. Finally, we show one of the most powerful features in PyTorch, Boolean masking. Suppose you want to filter the tensor and keep only the values greater than 50. PyTorch will first create a mask, a grid of true and false, where each true indicates that the condition is met. Then, when you apply that mask back to the tensor, it returns only the values where the condition holds. This is super useful for filtering predictions, loss values, or feature maps. These indexing techniques, from basic slicing to fancy indexing and Boolean masking, are crucial building blocks of real-world machine learning in PyTorch. You'll see them again and again when working with data loaders, batches, attention heads, and more. And that brings us to the end of this part of the PyTorch tutorial. We covered a lot, from creating random tensors and performing reductions, to reshaping, stacking, squeezing, and selecting data with powerful indexing techniques. These are the core building blocks you'll use in nearly every deep learning project, so take the time to practice and get comfortable with them. If you found this video helpful, don't forget to like, subscribe, and turn on notifications so you won't miss the next chapters in this series. We're just getting started, and there's so much more to explore together. Thanks for learning with us here at BrainOmega, and I'll see you in the next one. Welcome to the third part of our PyTorch tutorial course here on BrainOmega. In the previous parts, we explored the basics of tensors and operations, and today we're going to dive deeper. We'll see how PyTorch works seamlessly with NumPy, one of Python's most widely used numerical libraries, and then we'll cover reproducibility, which is the key to running experiments that give the same results every time. And don't worry about typing out all the code yourself. Every example you see in this video is available on our GitHub repository. You'll find the link in the description of this video. So, open up your notebook, follow along with the code, and let's get started. Let's start by converting a NumPy array into a PyTorch tensor. When we use torch from NumPy, PyTorch does not make a copy of the data. Instead, it creates a tensor that points to the same memory as the NumPy array. That means the two objects are linked. If you change one in place, the other will reflect that change. Another important detail is about data types. By default, NumPy creates arrays with float 64 precision, while PyTorch usually prefers float 32 for speed and efficiency. So if you want to match PyTorch's defaults, you'll need to explicitly cast the tensor to float 32. Now let's explore the difference between in-place and out-of-place operations. If we make an out-of-place change, like reassigning a NumPy array to a new value, it creates a new object in memory. Since the tensor was linked to the old memory, it doesn't see the change. On the other hand, if we modify the NumPy array in place, meaning we update the values directly in the same memory, then the tensor instantly reflects the change. This distinction, out of place versus in place, is really important when working with shared memory. Let's reverse the process and convert a tensor into a NumPy array. When we call .numpy on a tensor that's on the CPU, PyTorch again shares the memory instead of making a copy. That means if you update the tensor in place, the NumPy array updates too. But if you reassign the tensor to a brand new object, the NumPy array is still pointing to the old memory, so it doesn't change. This behavior is very efficient because it avoids unnecessary copies, but you have to be mindful about when you want a true copy versus when sharing is okay. If your tensor lives on the GPU, NumPy can't directly access that memory. That's why calling .numpy on a CUDA tensor will raise an error. The correct way is to first detach the tensor from the computation graph, move it back to the CPU, and then convert it into a NumPy array. Now, let's talk about reproducibility. Machine learning models rely heavily on randomness. For example, random weights when starting training. That randomness is great for exploration, but sometimes you want your experiments to be repeatable, so you and a colleague can get the same results when running the same code. To achieve this, we need to set seeds for every random number generator. Python's built-in random, NumPy's random, and PyTorch's random number generators for both CPU and GPU. PyTorch also gives us deterministic mode, which forces certain operations to run the same way every time, although it can slow things down. To wrap everything up, here's a single cell that demonstrates all the key points: reproducibility, converting between NumPy and PyTorch, memory sharing behavior, and seeding randomness for repeatability. This is the kind of cell I keep at the top of a notebook when I want predictable results every time I run it. And that wraps up the third part of our PyTorch tutorial course. We've learned how to convert between NumPy arrays and PyTorch tensors, the difference between in-place and out-of-place operations, and how to make our experiments reproducible by setting seeds. If you found this lesson helpful, don't forget to give the video a like, share it with your friends who are also learning PyTorch, and most importantly, subscribe to BrainOmega so you don't miss the next part of the course. Thanks for watching, and I'll see you in the next tutorial. Welcome to BrainOmega, PyTorch Tutorial 4. Today we'll build a small but realistic regression project end-to-end, locking in deterministic runs, a clean data pipeline with proper train, val, test splits, and efficient mini-batches via data loaders. We'll train with mixed precision on GPU, use learning rate scheduling, apply early stopping with best model checkpointing, and keep training stable with gradient clipping. All metrics flow into TensorBoard so you can see exactly what's happening. By the end, you'll have a reliable, repeatable workflow you can trust and reuse on your next project. When we build machine learning projects, one of the most important things to aim for is reproducibility. That simply means if we or someone else run this exact project tomorrow, we should get the same results. Without reproducibility, it's hard to debug, compare experiments, or build trust in our models. To achieve this, we need to make sure that all sources of randomness, whether they come from Python, NumPy, or PyTorch, are controlled. That's why we set a seed value and force PyTorch to use deterministic algorithms whenever possible. A seed acts like a reference point. Once you fix it, random number generators will always produce the same random sequence of numbers. Before we even touch CUDA, the GPU backend, we configure some environment variables. For example, cublasconfig helps ensure that operations on the GPU, like matrix multiplications, behave deterministically. In practice, this can slightly reduce performance or even cause issues on certain systems, so it's something you can comment out if needed. After that, we import the usual suspects: Python's random, NumPy, and PyTorch. Notice how we also bring in useful PyTorch utilities such as data loader, tensor dataset, and summary writer for TensorBoard logging. We'll use those later when we move beyond reproducibility and start training. The core of our reproducibility setup is the seed everything function. Here, we call the seeding functions for Python's random, NumPy, and both CPU and GPU seeds in PyTorch. We also configure the backend flags, disabling benchmark mode, and enabling deterministic mode for QDNN. This ensures PyTorch doesn't silently switch between faster but non-deterministic algorithms. Finally, we attempt to enforce deterministic algorithms globally with torch.use _ deterministic algorithms, open parenthesis, true close parenthesis. Depending on your hardware and PyTorch version, some operations may not support this mode, so you might see a warning, but that's expected. Next, we decide where our model will run, either on GPU if one is available, or on CPU otherwise. We store this in a device object. Since GPUs support automatic mixed precision, AMP, we also set a flag use _ amp to true when running on CUDA. AMP lets us speed up training and save memory by mixing float 16 and float 32 operations safely. Finally, we make sure PyTorch's default data type is set to float 32. This is the standard choice for most deep learning tasks, and being explicit about it avoids subtle bugs when working with tensors. At this point, we've laid down the foundation, a deterministic, reproducible, and device-aware environment. Everything we do from here, data loading, model training, or evaluation, will be consistent and repeatable across runs. That's a huge win for both beginners and advanced practitioners because it builds confidence that the results come from our design choices, not from hidden randomness. Now that our environment is reproducible, the next step is to bring in some real data. For this tutorial, we'll use a classic dataset from scikit-learn, the diabetes dataset. It's small, only 442 samples, each with 10 input features. but it's perfect for practicing regression workflows. We load the features X and targets Y using load diabetes, making sure to convert them into float 32 NumPy arrays right away. This is important because PyTorch models expect float 32 by default, and keeping types consistent prevents hidden errors later. Before training, we also want to make sure our features are standardized. That means we scale them so that each feature has zero mean and unit variance. Why does this matter? Neural networks, especially multi-layer perceptrons, MLPs, train more stably and converge faster when inputs are on a similar scale. For this, we use scikit-learn's standard scaler. After scaling, we convert the NumPy arrays into PyTorch tensors so that they're ready to be wrapped in datasets and data loaders. Next, we split our dataset into train, validation, and test sets. A common choice is 70% for training, 15% for validation, and 15% for testing. Training data is used to update model weights. Validation data is used to tune hyperparameters and detect overfitting, and the test set is held back until the very end to evaluate performance fairly. We create a tensor dataset from our features and labels, then use random split to divide it. To keep splits reproducible, we set a manual seed in the generator. This way, you'll always get the same exact split across runs. Once we have datasets, we set up data loaders to feed mini-batches efficiently into the model. Mini-batching helps speed up training by leveraging vectorized operations and GPU parallelism, while also smoothing out noisy updates compared to single-sample training. For training, we shuffle the data at each epoch to reduce bias, while validation and test sets stay in a fixed order. To make things efficient on GPU, we enable pin memory so that batches are transferred faster to CUDA. We also define a worker init fn to seed each data loader worker process separately. This ensures that even parallel data loading is reproducible. We choose a batch size of 64 for training and slightly larger batches of 128 for validation and testing, since evaluation doesn't require gradient computation and can be done more efficiently. Finally, we check the lengths of our data loaders to confirm that everything is split correctly. At this stage, we have a tiny regression dataset prepared with proper pre-processing, clean splits, and efficient mini-batch pipelines, exactly the kind of foundation you want for building trustworthy experiments. With the data pipeline ready, we can define a simple yet solid multi-layer perceptron, MLP, for regression. Our regressor class subclasses nn.module and builds the network inside a nn.sequential container to keep the forward pass clean and readable. The first layer, nn.linear open parenthesis in underscore dim comma, hidden close parenthesis, projects the 10 standardized input features into a higher dimensional hidden space, 64 by default. Right after that, we add nn.batchNorm 1D open parenthesis, hidden close parenthesis, which normalizes activations per feature across the batch. On tabular data, this often stabilizes training and lets us use slightly higher learning rates. We then apply a nonlinearity with nn.ReLU open parenthesis, close parenthesis, so the model can learn curved nonlinear relationships, and follow with nn.dropout open parenthesis, dropout close parenthesis as a lightweight regularizer that randomly zeroes some activations during training to reduce overfitting. The middle block repeats a hidden linear ReLU stack to increase model capacity without making it overly deep. This two hidden layer pattern is a dependable default for small tabular problems. Finally, a last nn.linear hidden one serves as the regression head, outputting a single continuous value per sample. No activation here because regression targets aren't bounded. If you find the model underfitting, high bias, you can raise hidden, for example 128, or add another hidden block. If it's overfitting, Validation loss worse than training? Consider increasing dropout, for example 0.2 to 0.3, or adding weight decay in the optimizer later. After constructing the module, we move it to the correct compute device with dot to device, which ensures all parameters and incoming tensors live on the same CPU/GPU. This avoids subtle runtime errors and keeps data transfers efficient. Printing some p.numel for p in model.parameters gives a quick parameter count, a helpful sanity check on model size and memory needs, while printing the model itself shows a readable layer-by-layer summary. By default, PyTorch initializes weights with sensible heuristics, for example chiming/he initialization where appropriate, which generally work well with ReLU networks. You can swap in a custom initializer later if you want tighter control. In short, this architecture is intentionally small, regularized, and easy to train. Batch norm for stability, ReLU for nonlinearity, dropout for generalization, and a single unit head for scalar regression. It's a practical baseline, simple enough for beginners to understand, yet strong enough to produce reliable results on the standardized diabetes dataset. With the model defined, we need two ingredients to make learning happen: a loss function to tell the network how wrong it is, and an optimizer to nudge the weights in the right direction. For regression, we'll use mean squared error. That's nn.mse loss in code. Think of it as measuring the average of the squared mistakes between our predictions and the true values. Squaring means bigger mistakes count extra, which usually gives us smoother fits. If you ever find that a few outliers are throwing things off, switch to smooth L1 loss, also called Huber, which is a bit more forgiving. To update the weights, we'll use AtomW with a learning rate of 1e-2, that's 0.01, and a weight decay of 1e-3, that's 0.001. AtomW is atom with decoupled weight decay. Think of it as a gentle regularizer that helps the model generalize. This learning rate is intentionally a little brisk because our features are standardized and we're using batch normalization. If training looks jittery, just dial it down to 3e-3, 0.003. Learning rates don't need to stay fixed, so we'll add a scheduler called reduce LRO on plateau. It watches the validation loss and, if progress stalls for about 10 checks in a row, it cuts the learning rate in half. We say it runs in min mode because lower loss is better. I like to think of this as an auto brake. Start fast, then slow down as we approach the good stuff, often landing in a better spot without manual tuning. One practical note: this scheduler only reacts when you call scheduler.step open parenthesis val_loss close parenthesis after each validation phase, so we'll wire that into the training loop. Loss is what the optimizer chases. Metrics are how we, as humans, judge progress. Our regression metrics helper builds a small dashboard you can log to TensorBoard or print each epoch. We'll track MSE, the same quantity as the loss, just for reference. MAE, mean absolute error, easy to read because it's in the same units as the target, and RMSE, root mean squared error, also in target units, so it's intuitive. We'll also report R squared. In plain English, R squared tells you how much of the variation in the target your model is explaining. Close to 1 means it's explaining most of it. Around 0 means it's no better than always predicting the average. Negative means it's actually worse than that simple baseline. We add a tiny safety constant internally to avoid weird edge cases if the target barely varies. You'll notice the metric function expects CPU tensors. That's on purpose. Moving small tensors to the CPU before logging keeps GPU memory free and avoids blocking the GPU with light bookkeeping work. In practice, after each evaluation step, we detach the predictions, move them to CPU, and pass them into the metrics function. The function returns a neat dictionary, perfect for TensorBoard, so each value becomes its own time series. That way you can spot patterns like loss is dropping but MAE has stalled, or R squared starts climbing once the scheduler kicks in. Put it all together and you get a clean, reusable pattern. MSE guides the optimizer. Atom W plus weight decay gives stable, regularized updates. The plateau scheduler adapts the learning rate as progress slows. And a compact metrics panel, MAE, MSE, RMSE, R squared, gives you human-friendly feedback. Separating optimize with loss from judge with metrics is a best practice you can carry into almost any regression project. Early stopping is our safety net against overfitting and wasted compute. Think of it like this. After every validation check, we ask, did the model genuinely get better? If yes, we reset the weight counter and stash away a copy of the current best weights. If not, we increment the weight counter. Once we've waited too long without real improvement, defined by a patience window, we stop training early. In this class, patience is how many validation rounds we're willing to wait, and min delta is the tiniest improvement we still consider real, so tiny noise doesn't fool us. We track the best validation loss we've seen, self.best, and when a new best shows up, we clone the model's state dict to CPU for safekeeping, self.best state. The step method returns two flags, whether we improve this round and whether it's time to stop because we've exceeded patience. In our setup, we create early stopper with a patience of 30 and a min delta of 1 E-6, that's 0.1. 0.00001, which is conservative and works well for small tabular problems. We also set best path equals best underscore model dot pth. So later in the loop, we can save the best checkpoint with torch dot save early underscore stopper dot best state comma best path. Right when we see an improvement or after training finishes, we can restore those best weights with model dot load state dict early stopper dot best state before doing a final test. The result, training stops at the right time, and you walk away with the best model you saw along the way, not just the last one. We're ready to train, so first we set up TensorBoard logging with a summary writer. This lets us record losses, metrics, and the learning rate as the run progresses, so you can visualize everything later. We'll train for up to 300 epochs, and we'll keep training stable with gradient clipping. Here we cap the total gradient norm at 1.0, which helps prevent those rare but destructive exploding gradient steps. Because we may be on a GPU, we also prepare automatic mixed precision. If CUDA is available and we chose to use AMP earlier, we create a grad scaler to safely scale the loss and keep low precision math numerically stable. Alongside that, we define an autocast helper that returns the right context manager. On GPU with AMP, it uses autocast, so many ops run in faster, float 16 under the hood, and on CPU or when AMP is off, it becomes a harmless no-op. This way, the rest of our training code stays clean and identical across devices. Training and validation flow through a single function, run epoch, which takes a data loader and a flag that says whether we're training or just evaluating. We switch the model into the correct mode with model.train, open parenthesis mode equals train, close parenthesis. Training mode enables layers like dropout and batch norm to behave properly, while evaluation mode freezes their behavior for consistent validation. For each mini-batch, we move inputs and targets to the right device with non-blocking equals true to speed up transfers when pinned memory is enabled. In training, we start by zeroing the gradients efficiently with set to none equals true, then run the forward pass inside autocast so AMP can kick in on GPU. We compute the loss, and if AMP is active, we scale it and backpropagate through the scaled value, clip the gradients to our max norm, take an optimizer step via the scaler, and then update the scaler. If AMP isn't active, we do the same steps without scaling. During validation, we wrap the forward pass in Torch Inference mode to turn off gradient tracking and save memory and time. After each batch, we accumulate the loss for averaging, and we also collect metrics on the CPU. We detach the predictions and targets, move them to the CPU, and send them to our regression metrics helper. Doing the bookkeeping on the CPU keeps the GPU focused on the heavy lifting. At the end of the epoch, we average the loss and the metric values across all batches, so a single number represents that epoch's training or validation performance. The main training loop ties everything together. For each epoch, we run one pass over the training loader and one over the validation loader. Then we step the learning rate scheduler with the latest validation loss. This is the plateau scheduler that will cut the LR in half if progress stalls for a while. We log everything to TensorBoard, training loss, validation loss, each metric for train and val, and the current learning rate. Next comes early stopping. We feed the validation loss and model to our stopper. If we truly improved, we save a fresh copy of the best weights to disk. If we've gone too long without improvement, we trigger an early stop to avoid wasted compute. Every 20 epochs, or right when early stopping trips, we print a concise status line with train loss, val loss, validation R squared, and the current learning rate, plus a little star when we've just hit a new best. Finally, we measure how long training took, close the writer to flush any remaining logs, and print a tidy summary. The result is a training loop that's fast on GPU, safe with mixed precision, protected by gradient clipping and early stopping, adaptive with a plateau scheduler, and fully observable in TensorBoard. It's the kind of loop you can trust and reuse in many future projects. If you're in Google Colab, you can open TensorBoard right inside the notebook. First, we load the TensorBoard extension, and then we point it to the folder where our logs are being written. In our case, that's the runs directory we set in Summary Writer. So run these two lines. Load the TensorBoard extension, then TensorBoard with logdir equals runs. After a moment, a panel will appear showing your dashboards. Once it's up, click into Scalars to see your training loss and validation loss over time. You'll also find the metrics we logged, MAE, MSE, RMSE, and R squared, as separate curves, plus the learning rate so you can watch the scheduler kick in. You can compare multiple runs, smooth the curves to reduce noise, and zoom into specific epochs. If you don't see anything yet, make sure you've run the training cell first so it creates log files. If the embedded view doesn't load in Colab, look for the Open in New tab link that appears under the panel. Working locally instead of Colab? You can launch TensorBoard from a terminal with TensorBoard-logdir runs and then open the shown URL in your browser. The experience is the same. Loss curves, metrics, and learning rate all in one place. Pro tip: name different experiments with unique subfolders inside runs. For example, run/xp_lr_1e-2. So TensorBoard can overlay their curves and you can compare settings at a glance. That's it. 2 lines in Colab to bring your training to life visually, and an easy terminal command if you're running on your own machine. First, we load the best model weights we saved during training. That file, best_model.pth, contains a snapshot of the model at the moment it performed best on the validation set. We load it to the CPU to be safe and compatible on any machine, then move the model back to the correct device, CPU or GPU. We also switch the model to evaluation mode with model.eval. This is important. It tells layers like batch norm and dropout to behave in their inference settings, so results are stable and comparable. Now we run our test set. This is data the model has never seen during training or validation, so it's the fairest way to judge real performance. We wrap the loop in Torch inference mode to turn off gradient tracking. This makes evaluation faster and uses less memory. For each mini batch, we send inputs and targets to the device, make predictions, compute the loss for reference, and collect our metrics on the CPU. When the loop finishes, we average the loss and each metric across all test batches so we get a single, easy-to-read summary. Finally, we print a short report: mean squared error, root mean squared error, mean absolute error, and R-squared. Remember the intuition. MAE and RMSE are in the same units as your target, so they're easy to interpret. Lower is better. R-squared tells you how much of the variation in the target your model explains. Close to 1 is strong, around 0 is no better than predicting the average, and negative means worse than that simple baseline. With this, you've closed the loop. You trained with early stopping and checkpointing, restored the best version of your model, and measured its true performance on unseen data. To wrap up, let's visualize how our model's predictions compare to the real target values on the test set. First, we switch the model to evaluation mode and turn on inference_mode so everything runs fast and memory light. We loop over the test data loader, move each batch to the right device, generate predictions, and immediately bring those predictions back to the CPU. We collect all predictions and all true targets into 2 big arrays so we can plot them at once. Now we make a scatter plot where each point shows true value on the x-axis and predicted value on the y-axis. If the model were perfect, every point would sit exactly on the diagonal line where prediction equals truth. So we draw that reference line, then scatter our points to see how closely they hug it. Tight clustering around the line means strong performance. A lot of vertical spread means the model is off by more in those regions. You can also look for patterns, like curved shapes or gaps, that might hint at underfitting, overfitting, or missing features. A couple of tips. If the points look too dense, try reducing the marker size or adding a little transparency. If the range is very narrow, expand the figure size or set x/y limits to match the mean and max of your data. This one simple chart gives you an intuitive, at-a-glance check of calibration. Are predictions systematically high or low? And error spread across the target range, making it a great final sanity check before you ship your model. Welcome back to BrainOmega. This is PyTorch tutorial number 5. In this part, we're moving into classification with synthetic datasets, things like circles, blobs, and moons that are perfect for learning how neural networks separate data. We'll start with the basics: generating toy datasets, making sure everything is reproducible, and setting up a clean PyTorch pipeline. Then we'll dive into visualization tools, like plotting the raw points and even drawing a decision boundary that shows exactly how the model is classifying the input space. Along the way, we'll use modern metrics from Torch metrics, like accuracy for binary and multi-class problems, to measure performance properly. By the end, you'll have a clear picture of how to set up a classification project from scratch, test models on simple datasets, and actually see how your network is learning. It's a fun, visual step forward from regression, and a great foundation for tackling real-world classification problems. We'll start by pulling in the core libraries we need. From Python's scientific stack, we import NumPy for fast number crunching and matplotlib for plotting. From PyTorch, we grab the base torch package, the neural network toolbox torch.nn, and a couple of handy dataset tools, Tensor Dataset and Data Loader, so we can bundle tensors together and feed them to the model in mini batches. This gives us everything we need to build, train, and visualize a small classifier. Next, we bring in data utilities from scikit-learn that generate toy classification datasets, circles, blobs, and moons. These are perfect for learning because they're small, quick to compute, and visually intuitive. We'll also use train-test-split to split our data into training and testing sets the right way, so we can evaluate fairly on examples the model hasn't seen. For evaluation, we'll use Torch metrics. It provides ready-made, battle-tested metrics that plug right into PyTorch. Here we import binary accuracy for two-class problems and multi-class accuracy for problems with more than two classes. Using Torch metrics keeps our training loop clean and makes metric computation consistent across CPU and GPU. Reproducibility matters, so we set a seed, here it's 42, and pass it to both PyTorch and NumPy. Fixing the seed means that dataset generation and any random operations will be repeatable, which is crucial when you're debugging or comparing experiments. Finally, we make our code device agnostic. If a CUDA-capable GPU is available, we'll use it. Otherwise, we fall back to the CPU. We store that choice in a device variable so we can move tensors and models to the right place later. With imports done, metrics ready, randomness controlled, and the device selected, our project is set up for a smooth, reliable training run. Let's add two small plotting helpers so we can see our data and how the model is separating it. The first one, plot points, just draws the raw dataset. It accepts tensors or NumPy arrays, moves tensors to the CPU, and converts everything to NumPy for plotting. We make a simple scatter plot with the first feature on the x-axis and the second on the y-axis, and we color each point by its class label. This is the quickest way to sanity check that our dataset looks like moons, circles, or blobs, and to spot whether classes overlap or are nicely separable. If you pass a title, it shows at the top. Otherwise, it keeps the plot clean and minimal. The second helper, plot decision boundary, lets us visualize the model's decisions across the whole input space, not just at the training points. We decorate it with Torch inference mode so PyTorch turns off gradient tracking faster and lighter, and we call model eval to switch layers like dropout and batch norm into evaluation behavior. To draw the boundary, we first find a box that covers all our data, slightly padded so the edges aren't cramped. Then we create a dense grid of points inside that box using NP mesh grid. Think of this grid as a fine checkerboard that spans the 2D feature space. We stack the coordinates into a big array, convert it to a float 32 tensor on the right device, and feed all grid points through the model at once to get logits. From logits, we turn those model outputs into predicted classes. If the model has a single output column, we treat it as binary classification. Apply a sigmoid to get probabilities and mark anything at least 0.5 as class 1. Below that is class 0. If the model has multiple output columns, it's multiclass. We apply a softmax to get class probabilities and then take the argmax, whichever class has the highest probability. We reshape these predicted labels back into the grid shape and draw a filled contour plot. This colors the background by the predicted class in each region. Finally, we scatter the original data points on top, again colored by their true labels, so you can compare where the model agrees or disagrees with the ground truth. A few tips. The steps argument controls how fine the grid is. Higher values give smoother boundaries but take longer to compute. If you see a matplotlib warning about edge colors on unfilled markers, it's harmless. Setting edge colors equals none avoids it. And if your data is scaled or standardized, the boundary will reflect that scale. So always generate the grid in the same space the model expects. With these two functions, you get an instant visual read on both the shape of the data and the shape of your model's decision surface. Before we build our models, let's quickly review the standard recipe for classification networks in PyTorch. For binary classification, where we only need to decide between two classes, the setup is pretty straightforward. The input layer has as many features as there are columns in your dataset. We usually include one or more hidden layers with activations like RealU, which introduce nonlinearity so the model can handle complex decision boundaries. The output layer has exactly one neuron because we only need one number to represent the probability of being in class 1 versus class 0. At inference time, We pass that single output through a sigmoid function, which squeezes it between 0 and 1, making it interpretable as a probability. For training, we use binary cross-entropy with logits. That's BCE with logits loss in PyTorch. This loss function combines the sigmoid and the cross-entropy in one numerically stable step, so you don't need to apply sigmoid yourself inside the model. For multi-class classification, where we have more than 2 classes, the recipe is just slightly different. Again, the input size equals the number of features, and we use hidden layers with ReLU activations. But now the output layer has as many neurons as there are classes, one for each possible category. At Inference, we apply a softmax function to turn those outputs into probabilities that sum to 1. The class with the highest probability is the model's prediction. For training, we use cross-entropy loss in PyTorch. Like its binary cousin, this loss already includes the softmax step, so you can feed it raw logits directly. In short, binary classification equals one output, sigmoid, BCE with logits, multiclass equals outputs equal to number of classes, softmax, cross-entropy loss. Keeping this quick reference in mind will save you confusion later when you switch between different classification tasks. Let's start with a classic toy problem for binary classification. 2 concentric circles. This dataset is perfect for showing why we need nonlinear models. No straight line can separate the inner circle from the outer one. We generate the data with make circles. The key settings are n samples equals 1000. We create 1000 points, so the pattern is easy to see. Noise equals 0.03. We add a little jitter so it's not perfectly clean. This makes the task more realistic. Factor equals 0.5. This controls how far apart the circles are. Here the inner circle's radius is half the outer one. Random_state equals seed. We pass our fixed seed so the dataset is reproducible. After that, we convert x and y into PyTorch tensors with float 32 dtype, the standard type most PyTorch models expect. Printing the shapes is a quick sanity check. X should be 1002 because each point has 2 coordinates, and y should be 1000 with class labels 0 or 1. Finally, we call plot points to visualize what we're working with. You'll see an inner ring and an outer ring colored by class. This is a great reminder. A simple linear classifier would fail here, but a small neural network with ReLU can learn a curved decision boundary that wraps around the inner circle. Now that we have our circles dataset, we need to evaluate the model fairly, so we split the data into a training set and a test set. The training set is what the model learns from. The test set is held back until the end so we can see how well the model generalizes to unseen examples. We use train test split with test size equals 0.2, which means 80% for training and 20% for testing. We pass our random_state equals seed so the split is reproducible, and we add stratify equals y so both splits keep the same class balance. This is especially important in classification so we don't end up with, say, too many class 0 points in one split and too few in the other. Right after splitting, we move each tensor to the correct device, GPU if available, otherwise CPU, so that later computations run in the right place without constant copying back and forth. Finally, we check the lengths of xtrain and xtest as a quick sanity check that the split sizes are what we expect. With this, we're set up to train on one portion of the data and test on truly held out examples, which gives us a trustworthy measure of real-world performance. To set a baseline, we'll start with a purely linear network. No ReLU, no nonlinearity, so you can see its limits on the circle's dataset. The class linear circle net builds a tiny model with 2 linear layers. It takes our 2 input features, x1, x2, maps them to 8 hidden units, then maps those to one output. Because there's no activation between these layers, the whole thing still behaves like a single linear transformation overall. That means its decision boundary is effectively a straight line, which can't wrap around a circle. We move the model to the right device so it can run on GPU if available. For training, we use binary cross-entropy with logits, BCE with logits loss. With logits means the loss function expects raw scores straight from the model, not probabilities. It applies the sigmoid internally in a numerically stable way. This is the recommended setup for binary classification in PyTorch. As our optimizer, we'll use plain SGD with a learning rate of 0.1, a simple choice that's fine for this tiny model and helps you see the basic training dynamics clearly. Finally, we track binary accuracy from torch metrics, threshold 0.5 by default, moved to the same device as the model. Accuracy gives us an easy-to-read percentage of correct predictions, so we have more context than loss alone. This model is intentionally too simple. It sets a baseline and demonstrates why nonlinearity is essential, especially for shapes like concentric circles that can't be separated by a straight line. Let's do a short training run to see how this linear-only model behaves. Inside train binary, each epoch follows the classic PyTorch routine. We switch to training mode with model.train open parenthesis, close parenthesis, run a forward pass on the training inputs, and get logits, raw scores before any sigmoid. We call .squeeze1 just to remove the extra column dimension so the shapes line up with our labels. Then we compute the binary cross-entropy with logits loss, zero the old gradients, backprop with loss.backward, and take one optimizer step. That's the entire learning loop. Compute loss, take a step, repeat. Every few epochs, we pause to evaluate. We flip the model into evaluation mode with model.eval and wrap the code in torch.inference mode so PyTorch skips gradient tracking. This makes it faster and lighter. We run the model on the held-out test set, compute the test loss for reference, and then turn logits into predictions. Apply a sigmoid to map scores into probabilities, then check if they're at least 0.5 to decide class 1, otherwise class 0. We measure accuracy with our torch metrics, binary accuracy, which gives us an easy-to-read percentage. The print line summarizes training loss, test loss, and test accuracy, so you can see the trend as training moves along. Finally, we call plot decision boundary to visualize what the model learned. For a linear model on circular data, you'll typically see a single straight-ish boundary slicing through the rings, which can't properly separate an inner circle from an outer one. That's the point of this baseline. It shows, in both numbers and pictures, that a linear decision surface isn't enough. In the next step, we'll add nonlinearity so the model can curve and wrap its boundary around the data. Now let's give the network the ability to bend. We'll build nonlinear circle net, which stacks linear layers with ReLU activations in between. ReLU stands for Rectified Linear Unit, and it's the standard way to add nonlinearity so the model can learn curves instead of just straight lines. Our architecture takes the two input features, expands to 16 hidden units, applies ReLU, repeats that hidden block once more, and then ends with a single output neuron for binary classification, one logit. That last layer still outputs raw scores. During training, we'll use BCE with logits loss, which handles the sigmoid step internally. We move the model to the right device so it runs on GPU if available. For optimization, we switch to Adam with a learning rate of 0.01. Adam adapts the step size per parameter, which often makes training smoother and faster on small networks like this. The training loop train binary NL looks the same as before. Set the model to train mode, compute logits on the training set, calculate the loss, zero the gradients, backprop, and take an optimizer step. Every so often, we evaluate on the held-out test set in inference mode, compute test loss, convert logits to predictions with a sigmoid, and a 0.5 threshold and report accuracy. We also crank up the number of epochs, here 800, to give the nonlinear model time to settle into a clean boundary. When you plot the decision boundary, you should now see the background coloring wrap around the inner circle. That's the payoff of ReLU. The network composes simple pieces into a curvy boundary that linear models can't draw. If you notice the model overfitting, training loss falling while test loss rises, you can reduce the hidden size, add dropout or weight decay, or stop earlier. But on this toy dataset, a small two-layer ReLU MLP is usually enough to reach high accuracy and produce a neat circular boundary that matches the data. To really understand activations, we'll build them from scratch using plain PyTorch tensor ops and then plot their shapes. First, we create a range of inputs, A from -10 to +10. This gives us a good spread so we can see what each activation does to small, medium, and large values. Our ReLU custom takes any negative input and clips it to 0, while positive values pass through unchanged. That's the essence of ReLU. It's simple, fast, and helps networks learn nonlinear boundaries without saturating on the positive side. Next is sigmoid custom. It turns any real number into a value between 0 and 1, which is why it's often used for binary probabilities. Around 0, it's steep. Small changes in input cause big changes in output, but out at the extremes it flattens, which can slow learning if your inputs are very large in magnitude. Finally, tang custom maps inputs to -1 to +1. It's like a centered version of sigmoid, still squashes large values, but it's symmetric around 0, which can sometimes help optimization for certain architectures. We then plot each function. The x-axis is the input value from A, and the y-axis is the activation output. On the ReLU plot, notice the sharp knee at 0. Everything to the left is flat at 0. Everything to the right is a straight line. On the sigmoid plot, you'll see the familiar S-curve, gently approaching 0 on the left and 1 on the right. On the tan plot, you'll see a similar S shape but centered, smoothly approaching -1 and +1. These pictures make it clear how activations reshape signals inside the network. One practical note: these custom versions are great for learning, but in real models, you should use PyTorch's built-ins, torch.relu, torch.sigmoid, torch.tang, or their NN* counterparts, because they're vectorized, optimized, and more numerically stable, especially for very large positive or negative inputs. Still, building them yourself once helps you develop an intuition for how the network transforms data layer by layer. Now we'll switch to a multi-class problem with 4 clusters. We use scikit-learn's make blobs to generate 1,000 points in 2 dimensions grouped into 4 centers. The cluster STD equals 1.5 setting adds some spread so the classes slightly overlap, more realistic and a bit more challenging. We convert the features to float 32 tensors, and importantly, the labels to long dtype. PyTorch's cross-entropy loss expects integer class indices 0, 1, 2, 3 in that dtype. A quick call to plot points lets us see the 4 colored clusters before training. We do a proper train test split with stratification, which keeps the class balance the same in both sets. Because we created the tensors on the GPU initially, we momentarily move them to the CPU for train test split, then move each split back to the correct device. With the data ready, we define a small MLP, blobnet, 2 hidden layers with ReLU for nonlinearity, and an output layer with Num classes neurons. In multi-class setups, the model outputs raw scores logits for each class. At Inference, you'd apply a softmax to turn those into probabilities, but for training, you don't apply softmax yourself. Cross-entropy loss handles that internally in a numerically stable way. We set up blob model, the cross-entropy loss, and an atom optimizer at 0.01. For evaluation, we use multi-class accuracy from torch metrics, configured with gnome classes equals 4. The training loop is straightforward. Set the model to train mode, run a forward pass on the training set, compute the loss, zero gradients, backprop, and step the optimizer. Every 25 epochs, and on the first epoch, we switch to eval mode, compute test loss, take the argmax over the class dimension to get predicted labels, and report accuracy, a simple, intuitive metric for multi-class classification. Finally, we visualize the decision boundary. The background coloring shows which class the model predicts at each point in the 2D plane, and the test points are plotted on top. A clean result will show 4 regions that roughly wrap around each cluster. If you see ragged edges or confusion between 2 classes, try training longer, adjusting the hidden size, or tweaking the learning rate. With this setup, simple MLP, cross-entropy, and multi-class accuracy, you've got a solid template for N-class classification problems. Time for a quick hands-on challenge. We're going to classify the classic 2 moons dataset. Your goals: generate 1,000 samples with a fixed random state of 42, build a nonlinear model, and push test accuracy to at least 96%. The key idea is the same as with circles. A straight line won't cut it, so we need real U layers to bend the decision boundary. Start small, 1 or 2 hidden layers, and if accuracy stalls, try training longer or making the network a bit wider or deeper. In the reference solution, we call make moons with a bit of noise to make the task realistic, convert to PyTorch Tensors, and do a stratified train test split so both sets keep the same class balance. The MoonNet model stacks 2 hidden layers with ReLU and finishes with a single output for binary classification. We train with Atom at a learning rate of 0.01 and use BCE with logits loss, which combines the sigmoid and cross-entropy in a stable way. Every 100 epochs, we evaluate on the test split, turn logits into probabilities with a sigmoid, apply a 0.5 threshold for class labels, and compute binary accuracy with torch metrics. When you plot the decision boundary, you should see a smooth curve that snakes between the 2 moon-shaped clusters. If your accuracy is shy of 96%, here are quick tweaks. Train longer, for example 800 plus epochs. Increase hidden units from 32 to 64, or add a 3rd hidden layer. If you see overfitting, training loss drops but test loss rises, dial the capacity back or lower the learning rate a bit. This exercise cements the pattern you've learned. Non-linearity plus clean training loop plus proper evaluation gets you strong results on classic 2D datasets. Now for a classic nonlinear multi-class challenge, the CS231N style spirals. We'll generate 3 intertwined arms, each representing a class. The code builds N equals 150 points per class, so with K equals 3 classes and D equals 2 features, we end up with 450 total samples in the plane. For each class, we create a radius R that grows from the center and an angle T that sweeps out a spiral, then add a bit of random noise so the pattern isn't perfectly clean. After stacking the XY coordinates for all classes and labeling them 0, 1, 2, we convert everything to PyTorch tensors and take a quick look with plot points. You should see 3 colorful arms curling out from the origin, an ideal testbed for nonlinear decision boundaries. Next, we do a stratified train test split so class proportions stay the same in both sets, and we move each split to the correct device. Our model, SpiralNet, is a small MLP with 2 hidden layers of 64 units and ReLU activations, ending with K outputs, 1 logit per class. For training, we use cross-entropy loss, which expects raw logits and integer labels. It wraps the softmax internally for numerical stability. Optimization is handled by Atom at a learning rate of 0.01, and we track performance with multi-class accuracy configured for 3 classes. The training loop is standard. Forward pass on the training set, compute cross-entropy, zero the grads, backprop, and step the optimizer. Every so often, First epoch and every 100 after, we switch to eval mode, measure test loss, take the argmax over class scores to get predictions, and compute accuracy. Finally, plot decision boundary paints the 2D plane by predicted class and overlays the test points. A well-trained model will carve out curved regions that follow the spiral arms. If accuracy lags or boundaries look jagged, try training longer, slightly lowering the learning rate or adding a touch more capacity. This example drives home the point. Nonlinearity is what lets neural networks bend and twist decision surfaces to match complex patterns. Welcome back to BrainOmega. This is PyTorch tutorial number 6. Today we're stepping into the world of image classification with the CIFAR10 dataset, one of the most popular benchmarks in computer vision. In this tutorial, we're going to build a complete image classification workflow step by step. We'll start by creating a data pipeline with PyTorch, setting up datasets, applying transforms, building data loaders, and adding some augmentation to make the model more robust. Then, we'll add device-agnostic training utilities so our code runs seamlessly on GPU if available, or CPU otherwise. From there, we'll walk through 4 different models, each one a little more powerful than the last. Model A, a simple linear baseline, just a flattened layer followed by a linear classifier. Model B, a multi-layer perceptron with nonlinear activations. Model C, a small CNN, our first real computer vision network. Model D, transfer learning with torchvision.models.resnet18, a modern pre-trained backbone. Along the way, we'll track metrics and visualizations like accuracy and confusion matrices so we can really see how the models are performing. We'll also learn how to save and load the best model so your hard work isn't lost when training finishes. And finally, we'll put our model to the test, making predictions on random test images and even on your own uploaded images. By the end, you'll have a practical, end-to-end template for image classification in PyTorch that you can reuse, extend, and apply to real projects. We'll start by importing the core libraries for this project. From PyTorch, we bring in Torch and the neural network module NN. From Torch Vision, we import datasets and transforms. These give us easy access to common image datasets and the standard pre-processing steps they need. We'll also use PyTorch's data loader to batch and shuffle data efficiently. Finally, we import matplotlib for quick visualizations so we can actually see sample images and predictions as we go. Right after the imports, we print out the versions of PyTorch, Torch Vision, and matplotlib. This is a small step that saves headaches later. If something behaves differently on another machine, you can quickly compare versions. We also print whether CUDA is available. That tells us if there's a compatible NVIDIA GPU we can use for faster training. Last, we set a device variable. If CUDA is available, we'll use CUDA. Otherwise, we'll fall back to CPU. Keeping this in one place makes the rest of the code device agnostic. Whenever we create tensors or move a model, we'll send them to device, and the same script will run smoothly on both GPU and CPU. With libraries loaded, versions confirmed, and the device selected, we're ready to start building the image pipeline. We'll kick things off by making our experiments reproducible. The setSeed function fixes the random seeds for Python, NumPy, and PyTorch, both CPU and CUDA. So when you or someone else reruns this notebook, you'll get the same results. Same data shuffles, same weight initialization, same outcomes. That's essential for debugging and for fair comparisons between model variants. Next, we add 2 tiny utilities that make training easier to track. Print train time takes a start and end timestamp and prints a neat summary of how long training took on the active device, CPU or GPU. Use it around your training loop to see the speed difference between devices or settings. An accuracy fan is a quick, no-frills accuracy helper. It compares predicted labels to the true labels and returns a percentage. It's perfect for simple sanity checks, even if you later use torch metrics for richer reporting. With seeds set and helpers ready, we've laid the groundwork for repeatable experiments and clean, readable logs as we build out the rest of the pipeline. CIFAR-10 is a classic vision dataset, 60,000 color images, each 32 by 32 with 3 channels, spread across 10 everyday classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. We'll prepare it the right way for training and testing. First, we define the per-channel mean and standard deviation commonly used for CIFAR-10. These values let us normalize images so that each color channel has roughly 0 mean and unit variance, which usually helps models train faster and more stably. Next, we build 2 transform pipelines. For training, we include light augmentation, a random horizontal flip, and a random crop with 4 pixels of padding. These simple tweaks make the model more robust by showing it slightly varied versions of the same image. We then call toTensor, which converts PIL images to PyTorch tensors and scales pixel values to 0, 1, and finish with normalize using the CIFAR-10 stats. For testing, we skip augmentation. We want a fair, stable benchmark, and apply only toTensor and the same normalization. With transforms set, we create the train and test datasets via datasets.cifar10, pointing to a data folder, enabling download equals true, so the files are fetched if needed, and attaching the appropriate transform pipeline to each split. We also grab class names for easy labeling during visualization and evaluation. In the next step, we'll wrap these datasets in data loaders so we can batch, shuffle, and stream them efficiently to the model. Before we start training, it helps to see what the data looks like. Because our dataset is normalized for the model, colors would appear off if we plotted tensors directly. So we create an inverse normalization transform, ENV norm, that undoes the per channel mean, ST we applied earlier. Right before plotting, we pass each image through ENV norm and then clamp values to 0, 1 so the display looks natural. The showBatch helper picks a random set of images from the dataset using torch.randperm, arranges them in a small grid, and renders each one with its class name as the title. PyTorch images are stored as channels first, C times H times W, but Matplotlib expects height-width channels, so we transpose the tensor to HWC before calling imshao. We also turn axes off for a cleaner look and use tight layout so the grid fits nicely on screen. Calling show batch train data n equals 16 gives you a quick gallery of unnormalized training samples, perfect for checking that your transforms are working as expected and getting a feel for the variety inside CIFAR-10 before you build the model. Now we'll wrap the datasets in data loaders, which handle batching, shuffling, and background loading for us. We set a batch size of 128, a good starting point for CIFAR-10 on modern GPUs. For the training loader, we turn on shuffle equals true, so each epoch sees the data in a new order. This usually helps optimization. For the test loader, we keep shuffle equals false, so evaluation is deterministic. We also set numWorkers equals 2, which spawns a couple of background worker processes to preload batches while the GPU is training the current one. This helps keep the pipeline fed. And pin memory equals true speeds up host to GPU transfers when you're using CUDA. The last line prints how many iterations per epoch you'll get for train and test given this batch size. With these loaders, you've got an efficient, device-friendly data pipeline that keeps training smooth and fast. To keep our notebook clean and reusable, we'll wrap the core training logic into a few small functions. The first one, train one epoch, runs a single pass over the training set. We put the model in training mode. This makes layers like dropout and batch norm behave correctly, then loop over the data loader. For each batch, we move images and labels to the chosen device, GPU if available, otherwise CPU, run a forward pass to get logits, compute the loss, and do the standard optimizer steps, 0 grads, with set to none equals true for a small speed/memory win, backprop, and step. We also track running totals so we can report the average loss and accuracy across the whole epoch. Accuracy is computed by taking the argmax over class scores and comparing to the true labels. Next is evaluate, which is the same idea but for the test/validation split. We decorate it with torch.nograd and switch the model to eval mode so PyTorch skips gradient bookkeeping and layers act in inference mode. This makes evaluation faster and more consistent. We again accumulate loss and accuracy across all test batches and return the averages. Finally, fit ties everything together into a simple training loop that runs for a configurable number of epochs. It sends the model to the correct device, initializes a history dict to store loss/accuracy curves, and times the entire run so we can print a neat summary at the end. Each epoch we call train 1 epoch and then evaluate, append the results to history, and print a friendly line with the latest train/test loss and accuracy. When it's done, we call print train time to show how long training took on this device and return both the history and the duration. With these helpers in place, the rest of the tutorial can focus on models and data, while training stays compact, readable, and device agnostic. We'll start with a super fast baseline. Take each 32 by 32 by 3 image, flatten it into a single vector of 3072 numbers, and feed it straight into a linear layer that outputs 10 logits, 1 score per CIFAR 10 class. That's exactly what linear baseline does. NN flatten converts the image to a 1D feature vector, and NN linear 3072 to 10 learns a simple weighted sum for each class. There's no convolution and no hidden layers here, so don't expect high accuracy. The goal is a quick sanity check that our pipeline, data, transforms, loaders, and loops is wired correctly. We fix the random seed for reproducibility, move the model to the active device, GPU if available, and use cross-entropy loss, NN cross-entropy loss, which takes raw logits and integer labels. For optimization, we choose SGD with a learning rate of 0.1, a straightforward choice that works fine for this tiny model and keeps the training dynamics easy to see. Finally, we call our reusable fit function for 5 epochs, which trains on the loader, evaluates on the test set each epoch, prints loss and accuracy, and returns a history of metrics along with the total training time. This linear run establishes a baseline we can beat when we add nonlinearities and convolution next. Now let's add capacity with a small multi-layer perceptron. Instead of sending pixels straight to the classifier, we first flatten the image and pass it through 2 hidden layers with ReLU activations. Those ReLUs give the network the nonlinearity it needs to model more complex patterns than a single linear layer ever could. In this setup, each hidden layer has 256 units, a sensible starting point for CIFAR 10 when you're not using convolutions. The final layer still outputs 10 logits, 1 per class, and we'll keep using cross-entropy loss so we can feed in raw logits directly. For optimization, we switch to SGD with momentum and Nesterov enabled. Momentum helps the updates carry velocity in promising directions and damps out noisy gradients, which usually speeds up convergence. We keep the learning rate at 0.1 to start. Paired with momentum 0.9, this often trains faster and more stably than plain SGD. We seed for reproducibility, move the model to the active device, and run our reusable fit loop for 10 epochs so the MLP has time to improve over the linear baseline. What should you expect? Typically, the MLP will outperform the flatten-only model because those hidden layers can combine pixels in nonlinear ways. It's still not as data efficient as a CNN, which exploits image structure, but it's a great demonstration. Simply adding reuse and depth lets the network learn curved decision boundaries in pixel space and push accuracy beyond the linear baseline. If learning seems unstable, try lowering the LR to 0.05. If it plateaus early, try training longer or increasing the hidden size to 512. Now we'll switch to a convolutional neural network, which is designed specifically for images. Unlike MLPs that flatten pixels and ignore spatial structure, a CNN looks at local patterns, edges, corners, textures, and builds them up into higher-level features. Our small CNN has 3 feature blocks. The first block uses 2 3x3 convolutions with 32 filters each. Padding keeps the size the same, followed by a max pool that halves the spatial size from 32 by 32 to 16 times 16. The second block repeats the idea with 64 filters, then pools to 8 by 8. The third block uses 128 filters and pools to 4 by 4. This progressive downsampling means the network learns more abstract features while keeping computation reasonable. After the feature extractor, we have a small classifier head. Flatten a linear layer to 256 units with ReLU and a final linear layer to 10 logits, 1 per CIFAR 10 class. Because we're producing raw logits, we keep using cross-entropy loss, no softmax needed in the model. We seed for reproducibility, move the model to the active device, and train with Adam at a learning rate of 1 times 10 to the power of -3 for 10 epochs using our reusable fit loop. What should you expect? This compact CNN should clearly outperform the linear and MLP baselines because it exploits the 2D structure of images and shares weights across space, making it both data efficient and parameter efficient. If you want a little extra accuracy, try light augmentation, already in our pipeline, train a bit longer, or add batch norm after convolutions. If training is slow or memory is tight, reduce channels, for example 16 to 32 to 64, or batch size. This model gives you a solid, practical baseline for 32 by 32 images. Now let's level up with transfer learning. Instead of training everything from scratch, we'll take a pre-trained ResNet 18, a model that's already learned rich visual features from millions of images, and fine-tune it for CIFAR 10. We load ResNet 18 with default pre-trained weights, then swap out the final fully connected layer so it outputs 10 logits, 1 per CIFAR 10 class. Everything else stays the same, which means we get powerful feature extractors, edges, textures, shapes, right out of the box. ResNet 18 expects 224 by 224 inputs, but CIFAR 10 images are 32 times 32. To keep things simple, we wrap the model with a tiny resize wrapper that upsamples each batch on the fly using bilinear interpolation before passing it through ResNet. That way, we don't have to rebuild our data loaders or transforms. The wrapper handles sizing transparently. For optimization, we use Adam W with a small learning rate, 0.0001, and weight decay, 0.0001. Small steps are key in transfer learning. You want to gently adjust the pre-trained features to your new task rather than overwrite them. We fine-tune all layers here, nothing is frozen, which often works well on CIFAR 10. If you're short on compute, you could freeze the backbone and train only the final layer as a quick start. Finally, we call our fit loop for 5 epochs to get a strong baseline fast. What to expect? Even with minimal tuning, A pre-trained ResNet 18 typically beats small scratch models by a healthy margin, thanks to its general-purpose features and deeper architecture. If you want a bit more performance, train longer, use a short warm-up on the learning rate, or unfreeze gradually, start with the head, then the last block, and so on. This gives you a practical, reusable template for transfer learning on new image datasets. Let's wrap everything up by comparing models side by side. We collect two simple numbers for each run: the final test accuracy, the last value from the history, and the total training time in seconds. We put those into a small pandas data frame so we can display a neat table and sort it by accuracy to see which model came out on top. This makes it easy to spot trade-offs. Maybe one model trains much faster, while another gets a few extra points of accuracy. Below the table, we draw a bar chart of test accuracy. Each bar represents one model: the linear baseline, the MLP, the small CNN, and the transfer learned ResNet 18. It's a quick visual that tells the story at a glance. You should see the MLP beat the linear model, the CNN beat the MLP, and the ResNet 18 transfer model, typically leading the pack thanks to its pre-trained features. A couple of quick notes for fairness. We trained different models for different numbers of epochs and with different optimizers, so this is a practical comparison, not a controlled benchmark. If you want a strict A/B test, equalize epochs, tune learning rates, or run multiple seeds and average the results. Still, this table plus chart combo is perfect for summarizing what you built and for deciding which model you'd like to refine next. Now that we've trained several models, let's see where the best one still gets confused. First, we pick the winner by sorting our results table by test accuracy and grabbing the top entry. We map that name back to the actual model object, move it to the active device, and switch to evaluation mode so layers behave consistently during inference. To build a confusion matrix, we run the best model over the entire test set with gradients turned off. For each batch, we compute logits, take the argmax to get the predicted class for each image, and collect both the predictions and the true labels. After the loop, we concatenate everything into two big tensors, all predictions and all targets. We use torch metrics to compute the multi-class confusion matrix. This gives us a 10 by 10 grid, one row and column per CFAR 10 class. Each cell row equals true class, column equals predicted class, counts how many images of a given true class were predicted as each class. Ideally, you want strong numbers along the diagonal. That means most images are being classified correctly, and smaller numbers off the diagonal, which represent misclassifications. Finally, we plot that matrix with matplotlib. The x-axis shows predicted classes, the y-axis shows true classes, and the color intensity indicates how many examples fell into each cell. This visualization quickly tells you the story. Maybe cats and dogs get mixed up, or airplanes sometimes look like ships at low resolution. Use these patterns to guide improvements, add targeted augmentation, tweak the model capacity, or collect more examples for the confusing categories. Once you've got a strong model, the next step is to save it so you can reuse it later, without retraining. We create a saved models folder, making sure it exists, build a file name based on the best model's name, and call torch.save bestmodel.stateDict path. Saving the state dict is the standard PyTorch practice. It stores just the learned weights and biases, making files smaller and more portable than saving the full Python object. To reload, you need to recreate the same architecture and then load the weights into it. That's what the recreate function does. Given a model name, it constructs the matching network, linear baseline, MLP, CNN, or the ResNet 18 wrapper for transfer learning. For the ResNet path, we rebuild the backbone without pre-trained weights, replace the final layer to output 10 classes, and wrap with the same resize module so the input size matches. With an empty model in hand, we call load state dict on the file we saved using map location device so it loads on CPU or GPU as needed, switch to eval mode, and we're ready to use it. As a quick sanity check, we run evaluate on the test loader and print the accuracy. If it matches the number you saw before saving, within tiny rounding differences, you've confirmed the save and restore cycle works. From here, you can ship the model, resume training, or run it to make predictions in another script or environment. No retraining required. Let's see how the best model performs on actual test images. The predict and plot helper picks a handful of random samples from the test set, runs them through the model, and shows the images with their predicted and true class names. A few details make this smooth and fast. We decorate the function with torch.nograd, so PyTorch skips gradient tracking during inference. This saves memory and speeds things up. For each chosen index, we grab the image label pair, add a batch dimension with unsqueeze 0, and move it to the active device before calling the model. We take the argmax over the logits to get the predicted class ID. Since our dataset images are normalized for training, we invert that transform for display. Inv norm x.clamp01 brings colors back to a natural range, and permute 1, 2, 0 switches from channels first to h times w times c so matplotlib can plot it. On the figure, each tile shows the prediction on the first line and the ground truth on the second. If the prediction is correct, we keep the title black. If it's wrong, we color it red so mistakes pop out visually. Call predict and plot best model test data n equals 9 to get a quick 3x3 gallery. It's a great way to sanity check what the model gets right, what it struggles with, and whether certain classes, like cat versus dog, are easy to confuse. You can bump n higher for a bigger grid, or rerun the cell to see a fresh random sample each time. If you're running in Google Colab, you can try the model on your own photos. This cell opens a small file picker. Choose one or more .jpg or .png images, and we'll run them through the same pre-processing the model expects. We load each file with PIL, convert it to RGB, and resize to 32 by 32 so it matches CIFAR10's input size. Then we apply totensor to turn it into a PyTorch tensor and normalize with the standard CIFAR10 mean and STD values, just like we did for the training set. For inference, we wrap everything in torch.nograd to keep it fast and memory light, add a batch dimension with unsqueeze 0, and move the tensor to the active device. We pass it through best_model, take the argmax over the logits to get a class ID, and display the original image with the predicted label as the title. It's a quick way to sanity check how the network behaves on real-world pictures that weren't part of the dataset. A couple of tips. Since we resize to 32 by 32, images with unusual aspect ratios can look squished. If that bugs you, consider a center crop or letterboxing step before resizing. Also remember, the model only knows CIFAR10's 10 classes. If you upload something outside that set, it will still pick the closest CIFAR class it can. If you're not in Colab, the code will print a friendly message explaining that uploads aren't available in this environment and show the underlying error. That's it for PyTorch tutorial part 6. Let's quickly recap what you practiced and where you can go from here. On the skills side, you learned how to load and augment image data with Torch Vision, and how to write clean, device-agnostic training loops that work on CPU or GPU. You built and compared a range of models, starting with a linear baseline, then an MLP with RealU, then a small CNN, and finally transfer learning with a pre-trained ResNet 18. You measured performance with accuracy, dug deeper with a confusion matrix, and saw how to save and reload the best model so you don't lose progress. And finally, You made predictions on both random test images and even your own uploads. But this is just the beginning. To push further, you can try stronger augmentations like color jitter or random erasing, add learning rate schedulers and early stopping, or explore other backbones like EfficientNet or MobileNet for better accuracy and speed trade-offs. You can also track metrics more professionally with TensorBoard or weights and biases, or export the trained model to TorchScript so it's ready for deployment. And if you want to really challenge yourself, here are some exercises. Swap out optimizers, use AtomW everywhere and compare results. Experiment with schedulers like cosine annealing LR or one-cycle LR. Train with mixed precision to measure speedups. Create a confusion pairs gallery showing images the model confuses most often. Fine-tune more layers of ResNet 18 by unfreezing deeper blocks and compare. Each of these pushes your PyTorch skills to the next level. So keep experimenting, keep measuring, and most importantly, welcome to BrainOmega, PyTorch Tutorial 7. Today we're building a strong image classifier for 3 food classes, pizza, steak, and sushi, using transfer learning. We'll start with feature extraction, freezing the pre-trained backbone so we only train a lightweight classifier head, and then we'll fine-tune the top layers to squeeze out extra accuracy. You can run the notebook on CPU, but I highly recommend a GPU for much faster training. Why transfer learning? Training deep models from scratch usually demands huge datasets and lots of compute. With transfer learning, we reuse a backbone that's already learned rich visual features on a large corpus like ImageNet, and we adapt just the final layers to our small specific dataset. The result is quicker convergence, better accuracy with less data, and far less overfitting than a from-scratch model. In this project, we'll download a compact pizza, steak, sushi dataset, set up data loaders with the exact transforms the pre-trained model expects, and build a network that combines a frozen backbone with a custom classifier head. We'll train in 2 clear stages: first feature extraction, then fine-tuning, and evaluate the result with a confusion matrix, inspect misclassifications, and even test on a custom image so you can see how it behaves off dataset. I'll finish with a few exercises to help you go deeper, but by the end of this tutorial, you'll already have a clean, reusable transfer learning workflow you can plug into your own image classification tasks. We'll start with a quick environment check so the rest of the notebook runs smoothly. First, we try to import PyTorch and Torch Vision and print their versions. This is a simple sanity check that helps you diagnose mismatches later. If the import fails, we fall back to a small helper that installs the stable PyTorch plus Torch Vision wheels, CUDA-enabled build by default, then re-imports them so you can continue without manual steps. Finally, we choose a device. If a compatible GPU is available, we'll use CUDA. Otherwise, we'll run on CPU. Keeping this logic up front makes the whole tutorial device agnostic. All tensors and models will be sent to device, and you can switch between CPU and GPU without changing the rest of the code. Let's pull in everything we'll need and lock down reproducibility. We start with standard Python and scientific tools: OS, pathlib.path, random, math, time, NumPy, and matplotlib for file paths, randomness, quick math, timing, arrays, and plots. From PyTorch, we import the core torch package, NN for building models, and data loader to batch and stream data efficiently. From Torch Vision, we bring in datasets for ready-made image datasets, transforms, aliased as T, for preprocessing and augmentation, and to pill image for converting tensors back to displayable images. We'll also use TQDM to wrap loops with a progress bar so you can see training move forward in real time. A small but important piece is the setSeed function. It fixes randomness across Python, NumPy, and PyTorch, including CUDA, so you get repeatable results when you rerun the notebook or share it with others. We also set QDNN to deterministic mode and turn off benchmark. This nudges PyTorch to choose stable kernels rather than the absolute fastest ones, which keeps runs consistent. After seeding, we print the selected device so you can confirm whether you're on CPU or GPU. With imports in place and randomness under control, the rest of the tutorial will be smooth, predictable, and easy to debug. We're starting our transfer learning journey with a simple but effective dataset made up of 3 food classes: pizza, steak, and sushi. It's compact, lightweight, and already arranged in a clean image classification folder format, which means PyTorch can read it straight away without extra pre-processing. Inside the main folder called data/pizza_steak_sushi, you'll find 2 subdirectories, train and test. Each of these contains 1 folder per class: pizza, steak, and sushi, each filled with .jpg images belonging to that category. This folder structure is the exact layout that TorchVision.datasets.image folder expects, so it automatically assigns labels based on folder names and builds datasets ready to load into PyTorch. If the dataset isn't already present locally, the next cell in the notebook will handle everything for you. It will download and unzip the images automatically, so you can jump right into exploring, visualizing, and transforming the data without any manual setup. Think of this as your starter pack for image classification, small enough to train quickly, but rich enough to test every stage of a real-world transfer learning pipeline, from data loading and augmentation to feature extraction and fine-tuning. Let's make sure the dataset is on disk before we do anything else. We start by creating a data/folder and defining a target path, data/pizza_steak_sushi. If that folder doesn't exist yet, we download a small zip file straight from GitHub using requests, save it to data/pizza_steak_sushi.zip, and then unzip it into the target directory with Python's built-in zip file module. After extraction, we delete the ZIP to keep things tidy. If the dataset is already present, we simply print a message and move on, so this cell is idempotent, safe to run multiple times. Finally, we define train dir and test dir, pointing to the train/test subfolders, and print them out. This gives us a clean, reproducible starting point. Run once to fetch the images, and from then on your notebook will just reuse the local copy without downloading again. If you're on a flaky connection and the download fails, just rerun the cell. If you want to swap in your own dataset later, keep the same folder layout so the rest of the pipeline works unchanged. Before we build our datasets, we'll grab the exact pre-processing that the pre-trained backbone expects. Modern Torch Vision models ship with a weights enum that bundles not only the checkpoint, but also the canonical transforms used during pre-training, things like resizing, center cropping, converting to tensor, and channel-wise normalization. Here we pick efficient net B0, a great speed accuracy balance, and load efficient net _B0_weights .default, calling weights .transforms, returns an auto_transforms object that mirrors the original ImageNet pre-processing pipeline. Using this is the safest way to avoid silent accuracy loss from mismatched input sizes or normalization. If you switch backbones later, ResNet, ConvNext, VT, just change the weights enum and regenerate transforms. The rest of your data pipeline stays the same while remaining perfectly aligned with the model's pre-training. Now that the transforms are set, we can wrap the folders into PyTorch datasets and stream them efficiently with data loaders. Image folder is perfect here because our directory layout already follows the convention split /class*.jpg. It automatically assigns numeric labels based on the subfolder names and applies the auto_transforms pipeline so every image is resized, tensorized, and normalized exactly as efficient net B0 expects. We grab the discovered class names to confirm the mapping, pizza, steak, and sushi, and then build two data loaders. For training, we enable shuffle equals true, so each epoch sees a new ordering of images, which generally improves generalization. We keep a batch size of 32 as a balanced default and set pin memory equals true for faster host to GPU transfers when running on CUDA. Num workers is set to 0 for collab friendliness. If you're on a local machine, try bumping it to 2 to 4 to overlap data loading with GPU compute. The final line prints dataset sizes so you know how many samples you'll be training and testing on, which is helpful for sanity checks and for estimating steps per epoch. Before we start training, it's helpful to see what a real batch looks like. We grab one batch from the training loader and lay the images out in a small grid so you can quickly scan variety across classes. Because we applied the pre-trained auto-transforms, resize, tensor conversion, normalization, the tensors aren't directly display-friendly. Here we convert each tensor back to a PIL image for a quick preview. Colors may look a touch different from the originals. That's normal when you've normalized for ImageNet and then do a simple inverse for display. Each subplot shows the image alongside its class name, mapped from the integer label, which is a great sanity check that image folder picked up the folder names correctly and that labels align with visuals. If you see repeated classes or odd crops, double-check your directory structure and transforms. Otherwise, this quick peek confirms the data pipeline is wired up and ready for training. Time to build the model. We're starting with efficient net B0 loaded with pre-trained weights, then swapping its final classification layer so it outputs exactly 3 logits, one for pizza, one for steak, one for sushi. In efficient net B0, the body of the network lives in features, and the classifier head is a small sequential block at the end. We read the number of incoming features from base_model.classifier open bracket 1 close bracket dot in features, then replace the head with a simple dropout arrow, linear stack. Dropout adds a touch of regularization, and the new linear layer maps those features to our 3 classes. This gives us a model that keeps all the rich general-purpose visual features learned from ImageNet, while tailoring the final decision layer to our specific problem. For the feature extraction phase, we freeze the backbone by setting requires grad equals false on all parameters in base model.features. That means backpropagation will only update the new classifier head, not the convolutional feature extractor. The benefits are twofold. Training is much faster and less data hungry, and you get a surprisingly strong baseline without touching the heavy part of the network. We then move the model to the selected device, CPU or GPU, and print a quick trainable parameter count so you can see how small the head is compared to the full model. After we get a solid baseline, we'll switch to fine-tuning by unfreezing a few top blocks and training with a smaller learning rate. That second phase lets the model gently adapt its higher-level features to your food images and usually buys a few extra points of accuracy without overfitting. Let's set up a clean, reusable training loop that you can drop into any image project. We start with a tiny helper, accuracy from logits, which turns raw model outputs logits into class predictions by taking the argmax, then compares them to the true labels and returns the batch accuracy as a plain Python number. The core work happens in run epoch. We switch the model into train or eval mode depending on the flag. This matters for layers like dropout, batch norm, move each batch to the selected device, and run a forward pass to get logits and cross-entropy loss. When train equals true, we enable gradients, zero them efficiently with set to none equals true, backpropagate, and take an optimizer step. When train equals false, gradients are disabled for speed and memory savings. Throughout the loop, we keep running totals of loss and accuracy, weighted by batch size, so the epoch averages are correct even if the last batch is smaller. You'll see TQDM wrap the loader to give a smooth progress bar without cluttering your logs. On top of that, train model orchestrates the full multi-epoch routine. We create an AtomW optimizer, but only over parameters that are marked requires grad equals true, which is perfect for the feature extraction phase where the backbone is frozen. We use NN cross entropy loss since the model outputs raw logits for 3 classes. Each epoch we call run epoch once for training and once for validation, stash the results into a history dict, and print a compact status line. We also keep track of the best validation accuracy and clone the model's state dict when we hit a new best, so at the end we can restore the strongest checkpoint automatically, no accidental overfitting to the final epoch. Finally, plot curves draws side-by-side charts for loss and accuracy over time, train and val, so you can spot healthy learning, both lines, improving, plateaus, consider a smaller LR or more epochs, or overfitting, train improves while val stalls or degrades. This set of helpers gives you a tidy, production-style training loop with checkpointing, clear prints, progress bars, and quick diagnostics. Now we'll run Phase 1, Feature Extraction, where the backbone is frozen and only the new classifier head learns. This is the quickest way to get a strong baseline because we're reusing the pre-trained visual features and just teaching the final layer how to separate pizza, steak, and sushi. We set a modest learning rate, 1e-3, 0.001, which is usually plenty when you're training a small head on top of a fixed feature extractor, and we train for 15 epochs to let the classifier settle without overfitting. Calling train model kicks off the loop with our train and test loaders. Under the hood, it uses AtomW on the parameters that still require gradients, just the head right now, tracks loss and accuracy each epoch, and keeps the best checkpoint by validation accuracy. After training, plot curves shows 2 charts, loss train versus val and accuracy train versus val. A healthy run here looks like steadily falling losses and rising accuracies that flatten out as learning converges. If validation lags or bounces, try a slightly lower LR or a few extra epochs. If training leaps ahead of validation, consider light regularization, more dropout on the head, or stronger augmentation. Once you're happy with this baseline, we'll unfreeze the top blocks and fine-tune with a smaller learning rate to squeeze out a bit more accuracy. Now we move into Phase 2, fine-tuning, where we let the pre-trained backbone learn a little from our specific data. Instead of unfreezing the entire network, which can overfit or destabilize training on small datasets, we take a gentle approach and unfreeze only the last 2 efficient net feature blocks. These top layers encode higher-level patterns, textures, shapes that are most relevant to adapting from ImageNet to our food images. Because the backbone already contains good features, we use differential learning rates, a smaller LR for the backbone so it nudges weights carefully, and a larger LR for the head so the classifier can still move quickly. We keep cross-entropy loss and build an AtomW optimizer with 2 parameter groups to apply those distinct LRs. The train fine-tune loop reuses our run epoch routine under the hood. It trains for a few epochs, evaluates each round on the validation set, and tracks the best checkpoint by validation accuracy, restoring it at the end. This protects you from finishing on a slightly worse epoch due to random variation. After fine-tuning, we optionally merge the Phase 1 and Phase 2 histories, so plot curves shows a single continuous view of training. You'll often see a nice bump in val accuracy and a small drop in val loss as the unfreezed blocks adapt to pizza, steak, and sushi. If you notice overfitting, train improves while val stalls, reduce how much you unfreeze, try only the last block, lower the backbone LR further, or add a bit more augmentation. Time to see how well the model actually performs on unseen data. We switch to evaluation mode with model.eval, so layers like dropout and batch norm behave consistently, and we wrap the loop in torch.inference underscore mode, open parenthesis to disable gradients. This makes inference faster and lighter on memory. For each test batch, we move images to the correct device, run a forward pass to get logits, and convert them to class probabilities with softmax. We then take the argmax to get predicted class IDs and collect three things for later analysis: the probabilities, all probs, the predicted labels, all preds, and the true labels, all targets. After processing the entire test loader, we concatenate the lists into full tensors and compute a simple headline metric, test accuracy, by comparing predictions to targets and averaging the matches. This gives you a clean, trustworthy score on data the model never saw during training or fine-tuning, and it sets the stage for deeper diagnostics like a confusion matrix and misclassification review in the next step. Let's dig into where the model gets things right and wrong. We start by installing and importing scikit-learn's metrics, then build a confusion matrix from the full set of test targets and predictions. The matrix shows true classes along one axis and predicted classes along the other. Big numbers on the diagonal mean correct predictions, while off-diagonal counts reveal confusions. For example, steak predicted as pizza. We render it with confusion matrix display, add class labels for readability, and use a simple blue color map. This gives you an immediate visual of which pairs of classes are most often mixed up and whether one class is systematically harder than the others. Below the plot, the classification report breaks performance down per class. Precision, of what we predicted as this class, how much was correct. Recall, of all items in this class, how many we found. And F1, their harmonic mean, plus support, class sample count. This is especially useful if the dataset is imbalanced or if you care more about certain mistakes than others. If you need a normalized matrix, percentages instead of raw counts, you can call confusion matrix normalize equals true to turn each row into rates. Use these diagnostics to guide your next tweaks. Improve augmentation for the most confused class, adjust fine-tuning depth or learning rates, or gather a few more examples for the weakest category. Let's go beyond overall accuracy and inspect the mistakes the model is most confident about. These are the dangerous errors. We first identify all misclassified test examples by comparing predictions to targets, and if there are none, we celebrate and exit. Otherwise, because the test loader doesn't shuffle, batch order matches the dataset order, so we can index directly into test data. From the full probability matrix, all probs, we extract each example's predicted probability for the class it chose. This is our notion of confidence. We then filter to the wrong examples, sort them descending by confidence, and display the top 6 in a grid. For each image, we show the photo, inverse transformed to a viewable format, the predicted label, the true label, and the model's confidence. This view is invaluable for debugging. Are high confidence mistakes tied to specific lighting, angles, or textures? For example, steak char that looks like pizza toppings, or sushi rolls that resemble steak slices. Use these insights to guide data augmentation, crop, flip, color jitter, collect a few targeted samples for the confused class, or tweak fine-tuning depth and learning rates to better adapt the backbone. Let's finish with inference on your own image. This cell downloads a picture from a URL, runs it through the same auto-transforms the pre-trained backbone expects, and feeds it to the model to get a prediction with probabilities. The helper predict image switches the model to eval mode and wraps inference in torch inference mode so it's fast and memory light. We convert the PIL image into a tensor via the auto-transforms, Add a batch dimension with unsqueeze 0, move it to the right device, and run a forward pass to get logits. Applying softmax turns logits into class probabilities. We take the argmax to find the predicted class index and return both the index and the full probability vector. In the main block, you can paste any pizza, steak, sushi image URL. We fetch it with requests, open it with PL, call predict image, and render the photo with a title showing the predicted label and its confidence. If the download fails, bad URL timeout, you'll see a friendly error message. Pro tip: if you want to test local files or Colab uploads instead of URLs, just replace the download step with image.openpath/your_image.jpg. Convert to RGB and reuse the same predict_image function. Here are some great ways to level up this project framed as a practical roadmap. First, train longer in both phases. Extend the epochs and watch how the curves evolve. A gentle LR drop in phase 2 often turns small gains into stable improvements. Next, swap the backbone. Try ResNet 18, Convenex Tiny, or VIT-B 16. Update the weights, enum, and final head dimension to match, and compare speed, accuracy trade-offs. For augmentation, move beyond weights.transforms and craft a manual pipeline with random resized crop, color jitter, and random horizontal flip, but keep ImageNet normalization. This often boosts robustness on small datasets. Deepen your confusion insights by reporting per-class accuracy, listing the most confused class pairs, and showing a few example images for each class. This explains why the model makes certain mistakes. Explore progressive unfreezing. Start with just the classifier, then unfreeze the last block, then the last two, and so on. Track validation accuracy to find the sweet spot between adaptation and overfitting. While fine-tuning, experiment with differential learning rates. If the backbone LR is too high, you'll see validation wobble or regress. Dial it down to keep updates gentle. Make the workflow portable by saving the best state dict and writing a small reload function for inference in a separate script or service. Finally, test generalization with out-of-distribution images, say a salad, and discuss how the model behaves when the input isn't pizza, steak, sushi. This is a great segue into confidence calibration, thresholds, and OOD detection in real apps. Here are the big takeaways to lock in. Always use the transforms bundled with your pre-trained weights, so your inputs match the backbone's original training distribution. This avoids silent accuracy loss from size or normalization mismatches. Kick off with feature extraction, freeze the backbone for a fast, strong baseline, then fine-tune selectively, unfreeze the top blocks and use smaller learning rates to squeeze out extra performance without overfitting, and rely on visual diagnostics to guide your next moves. Learning curves reveal optimization issues, the confusion matrix shows which classes get mixed up, and a most wrong gallery spotlights high confidence mistakes you should target with augmentation, data fixes, or tuning. Hello everyone and welcome to the BrainOmega channel. Today we're diving into a fascinating topic at the intersection of two powerful fields, graph neural networks and reinforcement learning. The source code is available in our GitHub repo. Grab it from the link in this video's description. We'll be building an agent that learns to play the classic game cart pole, but with a unique twist. Instead of feeding the game state directly into a standard neural network, we'll first represent it as a graph and then use a GNN to make decisions. This tutorial will walk you through the complete Python code, explaining every block step by step. By the end, you'll understand how to structure a graph reinforcement learning project. Let's get started. So, what's our goal? We're tackling the cart pole environment from OpenAI Gym. In this game, we have a cart that can move left or right, and our job is to balance a pole on top of it. The state, or the information we get from the game at any moment, is a simple array of 4 numbers. the cart's position and velocity, and the pole's angle and velocity. A traditional approach would feed these four numbers into a standard neural network. But we're going to do something different. We'll convert this array into a graph structure first, and then feed that graph into a graph neural network, or GNN. This allows our model to learn not just from the values themselves, but from the connections and relationships between them. Let's jump into the code, starting with graphmaker.py. Before we can build a graph, we need to define its components. This first function, construct_sur index pairs, is all about defining the features for the nodes in our graph. Given our state of four numbers, this function creates specific pairings. First, it pairs adjacent elements, grouping cart position with cart velocity and pole angle with pole velocity. Then, it adds symmetric pairings, linking the cart's position with the pole's velocity and the cart's velocity with the pole's angle. For the cart pole state, this gives us four pairs of indices. Each of these pairs will be used to create a single node in our graph, where the node's features are the two state values indicated by the indices. Now that we know how to pair our state variables, let's look at the createGraphData function, which actually builds the graph. First, it creates the edge index. This defines the connections or edges between the nodes. By using permutations, we are creating a fully connected graph. This means every single node is connected to every other node, allowing the GNN to learn the maximum number of relationships. Second, it creates the node features, which PyTorch geometric calls X. It uses the index pairs from our previous slide to build a list of features for each node. So, our graph will have four nodes, and each node will have features consisting of a pair of values from the game state. Finally, it bundles the node features and edge connections into a data object, a standard container used by the PyTorch geometric library. Moving on to model.py, this is the brain of our operation. Let's look at how the graph reinforce agent is initialized. The most important layer is the graph convolution layer, which is a GCN conv from PyTorch geometric. PyTorch Geometric is a library built on top of PyTorch, designed specifically for deep learning on graphs and other irregular structures like social networks, molecular data, knowledge graphs, and more. This is what performs the graph convolution, allowing information to be passed between connected nodes. Note that its input dimension is 2, because each of our nodes has features made of two numbers. We also have standard linear layers, a layer normalization for stability, and an Adam optimizer to handle learning. Finally, we have experience memory. This is a list that will store the rewards and action probabilities from each step within a single episode. This is crucial for the reinforce algorithm, which we'll see soon. The forward method is where the agent makes a decision. It takes the graph's node features and edge index as input. First, the graph data is passed through our GCN conv layer. This is where the network learns from both the node features and the graph's structure. Next, we use global add pool. This is a critical step. It aggregates the feature vectors from all the individual nodes into a single feature vector that represents the entire graph. This gives us a holistic summary of the game's state. After aggregation, this single vector is passed through a standard linear layer. Finally, we apply log softmax to the output. This gives us the log probability for each possible action. In cartpole's case, the log probability of moving left and the log probability of moving right. After an episode finishes, the agent needs to learn from what just happened. This happens in the optimize method, which implements the reinforce policy gradient algorithm. First, it looks at the entire episode's history, which we saved in experience memory. It goes backward from the final step and calculates the discounted cumulative reward for each step. This means rewards earned earlier in the episode are worth more than later ones, thanks to the discount arm factor. Second, it normalizes these rewards by subtracting the mean and dividing by the standard deviation. This is a standard trick that makes training much more stable. Third, it calculates the policy loss. The formula is negative log probability times reward. The intuition is simple. If an action led to a high positive normalized reward, we want to increase that action's probability. If it led to a low negative reward, we want to decrease its probability. Finally, it backpropagates this loss to update the network's weights and clears the memory for the next episode. Now, let's bring everything together in main.py. This script orchestrates the entire process. First, we import our necessary libraries and our own graph data processor and graph reinforce agent classes. We create the card pole environment and set a device for our tensors using a GPU if one is available. We then set a random seed. This is crucial for reproducibility. It ensures that if we run the code multiple times, we'll get the exact same results. Next, we define our hyperparameters, the learning rate for the optimizer, the number of episodes to train for, and gamma, the discount factor for future rewards. Finally, we instantiate our graph reinforce agent and call our construct index pairs function once at the beginning to get the template for our graph nodes. The main training loop is the heart of our program. For each episode, we first reset the environment to get an initial state. Then, inside the while loop, which runs until the pole falls over, we have our agent environment interaction. Step 1. We take the current state from the game and use our createGraphData function to convert it into a graph object. Step 2. We feed the graph's features and edges into our agent model. The model outputs log probabilities, which we convert to a probability distribution and then sample from to choose an action. Sampling allows the agent to explore different actions instead of always picking the most likely one. Step 3. We perform the chosen action in the environment. The game gives us back the next state, a reward, and a done flag. We store the reward and the log probability of the action we took in the agent's memory for the optimized step later. Once the while loop finishes, which means the episode is over, a couple of things happen. First, and most importantly, we call agent.optimize. This triggers the learning process we discussed from model.py, where the agent updates its GNN weights based on the entire episode's performance. We also record the total score for the episode. And finally, every 10 episodes or so, we print the average score over the last few episodes. This helps us track whether our agent is actually learning and improving over time. After all the training episodes are done, we close the environment. If all goes well, you should see the average score trending upwards. So, let's recap what we've accomplished. We successfully built a reinforcement learning agent that represents its environment state as a graph. We created a data processor to handle the state-to-graph conversion. We built a GNN-based agent that can take this graph and make decisions. We implemented the reinforce algorithm to allow the agent to learn from its experiences. And finally, we tied it all together in a main training loop. This project is a fantastic starting point. From here, you could try using more advanced graph layers like graph attention networks, apply this technique to more complex environments where relationships between state variables are even more critical, or experiment with different ways of constructing the graph itself. I hope this tutorial has been helpful and has demystified the process of combining GNNs with reinforcement learning. Thank you so much for watching. If you found this video useful, please hit the like button, subscribe for more content, and feel free to leave any questions in the comments below. See you in the next one. Hello everyone, and welcome. Today, we're diving deep into one of the most powerful and scalable architectures in modern deep learning, the mixture of experts, or MoE. If you'd like to follow along or customize the code yourself, the complete source code is available on our GitHub. You can find the link in the description of this video. We'll go beyond the theory and build a complete working MO model from scratch using PyTorch. Our model will use a CNN to extract features from images and then use an MOE transformer layer to perform classification. We'll break down every single component: the gating network, the experts, the load balancing loss, and the final training pipeline. By the end of this video, you'll have a solid understanding of how to implement and train your own MOE models. Let's get started. So, what exactly is a mixture of experts, and why is it so important? Imagine a giant monolithic neural network. To process any input, whether it's simple or complex, the entire network has to be activated. All those billions of parameters are used every single time, which is incredibly inefficient. The mixture of experts model proposes a smarter way. Instead of one giant, we have a collection of smaller, specialized networks called experts. Then we have a lightweight gating network that acts like a router. For each input, the gating network quickly examines it and says, okay, for this specific data, I'm going to activate expert 1 and expert 4. The rest can stay dormant. This is called conditional computation. We get the representational power of a massive model, but only pay the computational cost of a much smaller one for each forward pass. This is the key to scaling models to trillions of parameters, like we see in large language models today. Let's start our code walkthrough with the simplest piece, the expert network itself. As you can see, an expert is nothing fancy. In our implementation, it's just a basic two-layer feed-forward neural network. It takes the input data, passes it through a linear layer, applies a ReLU activation function, and then passes it through a final linear layer. Each of our experts will be an instance of this same class. The idea is that through training, each one of these simple networks will learn to become a specialist on different types of features or patterns in the data. Now, for the most critical part of the MOE, the gating func, or the gating network. This module's job is to choose which experts get to see the input. Here's how it works. First, it takes the input X and passes it through a single linear layer. The output of this layer gives us a score or logit for each expert we have. Second, we use torch top k to find the indices and scores of the top k experts. In our case, k is 2. This is the top k routing strategy. We are deciding to only use the best 2 experts for this input. Third, we apply a softmax function only to the scores of these top experts. This turns their scores into a probability distribution, giving us the weights for combining their outputs. Finally, we create a sparse tensor. It's a tensor full of zeros, but we scatter the weights we just calculated into the positions corresponding to our top k experts. This gives us a final weight vector where only the chosen experts have non-zero weights. The transformer block with MOE is where we assemble all the pieces. In its initialization, we create a module list of our experts and instantiate our gating network. Now, let's look at the forward pass. First, we get the sparse gate weights from our gating network. This tells us which experts to use and how much to trust each one. Second, we pass the input X to all experts and stack their outputs into a single tensor. This might seem inefficient, but on modern hardware, running these small, identical operations in parallel is very fast. Third, we perform the core MOE operation. We multiply the expert outputs by their corresponding gate weights. Since the weights for non-selected experts are 0, their outputs are effectively nullified. We then sum the weighted outputs to get our final MO output. Finally, we add a residual connection by adding the original input X back to the output and apply layer normalization, which are standard practices for stabilizing transformer-like blocks. There's a common problem with MOE models. The gating network can get lazy and learn to always send data to the same few favorite experts. This means the other experts never get trained, and our model doesn't reach its full potential. To fix this, we introduce a load balancing loss. This is an auxiliary loss function designed to encourage the router to spread the work out more evenly. Here's how we calculate it inside our MOE block. After getting the gate weights, we first calculate the average weight or dispatch probability assigned to each expert across the entire batch of data. Then we apply a formula that penalizes this distribution if it's not uniform. We'll add this load balancing loss to our main classification loss during training. This nudges the gating network to explore using different experts, leading to better overall model performance. Now let's put everything together into our final CNNMOE transformer model. The architecture is a powerful and common pattern. First, we define a CNN feature extractor. This is a standard convolutional neural network whose job is to take a raw input image and convert it into a flat feature vector that captures its important visual information. Then, in our main model class, we chain the components together. An input image X first goes through the feature extractor. The resulting feature vector is then passed to our transformer block with the mixture of experts layer. This block processes the features and also returns our load balancing loss. Finally, the output of the MOE block is passed to a final fully connected layer, FCOut, which produces the classification scores for our different classes. Before we look at the training loop, let's quickly look at the config.py file. This is a very good practice in any machine learning project. Instead of hard coding values like learning rate or the number of experts directly into our model and training script, we define them all in this separate configuration file. This makes it incredibly easy to experiment. If we want to try training with 8 experts instead of 5, or use a different dataset like CIFAR10, we only need to change one line in this file without touching the main application logic. Here you can see we set our dataset, model dimensions, and training parameters like batch size and learning rate. Finally, let's look at the training loop, which is managed by our trainer class. The most important part is how we incorporate our special load balancing loss. Inside the loop for each batch, we first pass the images through our model to get the classification outputs and the load balancing loss. Then we calculate our total loss. This is the key step. The total loss is a combination of two things. The standard classification loss, which is cross entropy in our case, plus the load balancing loss we calculated earlier, multiplied by a small scaling factor called alpha. By adding these two losses together, we ensure that when we call loss.backward, the gradients will update the model weights to not only get the classification right, but also to encourage the gating network to distribute the load across all experts. The rest of the loop involves the standard steps of zeroing the optimizer, backpropagation, and updating the weights. So let's quickly recap what we've accomplished. We have successfully built a complete mixture of experts model from the ground up in PyTorch. We implemented the individual expert networks, the crucial top K gating function that routes data, and the important load balancing loss that ensures all our experts get trained. We then combined these into a full-fledged image classification model and created a configurable training script to run it. You now have a solid foundation to start experimenting with MOE architectures yourself. Try changing the number of experts, see how performance changes as you vary K, or apply this model to other computer vision datasets. Thank you so much for watching. I hope this deep dive was helpful. If you found value in this tutorial, please hit the like button, subscribe for more advanced deep learning content, and feel free to ask any questions in the comments below. Hello everyone and welcome to the BrainOmega channel. Have you ever wished you had a personal assistant to take notes during your meetings? Well, today we're going to build one. You can find the complete code and examples on our GitHub page. Just check the link in the video description. In this step-by-step tutorial, we'll create a complete meeting minutes generator using Python. This powerful tool will take any meeting audio, transcribe it using OpenAI's Whisper, generate professional structured meeting minutes with a Llama 3.1 model, and finally, give us a downloadable PDF of the results. We'll cover everything from setting up the models to building the user interface. Let's dive in and build our very own AI meeting assistant. So, what's the big picture? Our application automates the entire process of creating meeting minutes. It starts when a user uploads an MP3 audio file of their meeting. This file is first sent to OpenAI's Whisper API, which is incredibly accurate at transcribing speech to text. Once we have the raw transcript, we send it to a Llama 3.1 model. This is where the real magic happens. We'll use a carefully crafted prompt to instruct the Llama model to act as a professional minute taker, organizing the messy transcript into a structured document with a summary, key discussion points, and clear action items. Finally, to make the output easy to share and store, our script will convert these generated minutes into a PDF file that the user can download directly. We'll use the Gradio library to create a simple and clean web interface for the whole process. Let's start with the code in meeting minutes generator.py. The init method is where we set everything up. First, we load our OpenAI API key from environment variables and define the names of the models we'll be using. Whisper 1 for transcription and Meta Llama 3.18b instruct for generating the minutes. Now, here's a crucial part for making this run on consumer hardware. We're using the bits and bytes library to load the Llama model with 4-bit quantization. This dramatically reduces the model's memory footprint, allowing us to run this powerful 8 billion parameter model without needing a top-of-the-line GPU. We define the quantization configuration and then pass it to the from pre-trained method when loading our model. This is a key optimization for making large models accessible. Next up is the transcribe audio method. This function is straightforward but powerful. Its only job is to take the file path of our meeting recording and get it transcribed. We use a simple try except block for error handling. Inside the try block, we open the audio file in binary read mode. Then we make a call to the OpenAI Python client, specifically the OpenAI.audio.transcribe function. We pass it the model name we defined earlier, Whisper1, and the audio file itself. We also specify that we want the response format to be simple text. The API handles all the complex speech-to-text processing, and what we get back is a single string containing the full transcription of the meeting. This is the core of our application's intelligence, the generate minutes method. The magic here is all in the prompt engineering. We create two main pieces of text to guide the Llama model. First, a system message. This sets the persona for the AI. We tell it, you are a professional meeting minutes writer, and we give it very specific instructions on the format we want. A summary, discussion points, takeaways, and action items, all in Markdown. Second, we create a user prompt where we provide the raw transcript we got from Whisper. We combine these into a messages list, which is the standard format for interacting with instruction-tuned models. We then use our tokenizer to prepare these messages, generate a response from the model, and finally do a little bit of string cleaning to remove any special tokens from the model's output, leaving us with a clean, well-formatted Markdown document. Once we have our beautifully formatted Markdown text, we need a way to present it professionally. That's where the generate PDF method comes in. This function uses the FPDF library, a simple and effective tool for creating PDFs in Python. We initialize a new PDF object, add a page, and set a standard font like Arial. The key component here is the multi-cell function. We loop through each line of our generated minutes and add it to the PDF using multi-cell. This function is great because it automatically handles text wrapping, so we don't have to worry about lines running off the page. Finally, we generate a unique file name using Python's UID library to avoid overwriting files, save the PDF, and return the file path. The process upload function is the main orchestrator of our backend logic. It's a Python generator function, which means it can yield values back to the user interface incrementally, allowing us to show real-time progress updates. First, it performs some basic input validation to make sure a valid MP3 file was uploaded. Then, it calls the methods we've already discussed in sequence. It calls transcribe audio to get the transcript, yielding a status update to the UI. If that's successful, it calls generate minutes to create the structured text, again yielding an update. Finally, it calls generate PDF to create the downloadable file and yields the final results, the markdown text, and the path to the newly created PDF file. This function neatly ties our entire pipeline together. Now, let's look at interface.py. A powerful backend isn't very useful without a user-friendly way to interact with it, and the Gradio library makes this incredibly easy. We define a launch interface function. Inside it, we create a gr.blocks layout, which gives us full control over the UI's structure. We add some titles using gr markdown. Then we define our core components: an audio input widget for uploading the MP3, a markdown output component to display the generated minutes, a file output component to provide the download link for the PDF, and a button to start the process. The most important line is submit button click. This single line connects our UI to our backend. We tell it that when the button is clicked, it should call the generator.process upload function, using the audio input as its input and sending the results to the markdown output and PDF output components. It's that simple to wire everything up. Last but not least, we have the main.py file. This script is as simple as it gets, and it has one job: to start our application. It imports the launch interface function we just created in our interface.py file. Then, inside the standard if name equals main block, it calls this function. This is the command that initializes our meeting minutes generator, builds the Gradio UI, and starts the local web server, making our application accessible in a web browser. To run our entire project, all we need to do is execute this one file. So, let's recap what we've built today. We've created a fully functional AI meeting assistant. It uses Whisper for highly accurate transcription, a quantized Llama 3.1 model with sophisticated prompt engineering to generate professional notes, and a PDF generator for a polished final output. And we wrapped it all in a simple interactive web application using Gradio. This project is a fantastic starting point. You could extend it by adding support for more audio formats, integrating speaker diarization to identify who said what, or swapping out the Llama model to experiment with other powerful language models. I hope this tutorial has been a valuable look into how different AI tools can be combined to create incredibly useful applications. Thank you so much for watching. If you found this helpful, please like, subscribe, and share. See you in the next one. Hello everyone, and a huge welcome to this coding adventure. Have you ever looked at incredible AI models like Llama or ChatGPT and thought, that's amazing, but how does it actually work? It can feel like magic, but today we're going to pull back the curtain and become the magicians ourselves. The full code is available on our GitHub. Check the link in the video description. In this video, we're not just going to talk about large language models. We are going to build one from the ground up using PyTorch. We'll write every line of code, understand every component, and by the end, you'll have a working mini LLM that you trained yourself. This is a hands-on journey from a blank script to a text-generating AI. So, Grab your favorite drink, open up your code editor, and let's get started. Before we start coding, let's look at our roadmap. Building a language model is a journey with several key stops, and we'll be visiting every single one. First, we need to create our tokenizer. Think of this as teaching our computer a new language by creating a dictionary. It needs to know how to break down human text into numerical pieces it can work with. Next up is data preparation. Once we have our dictionary, we need to read our book, our text dataset, and convert the whole thing into a format the model can train on. We'll also create a system to feed it data in small, manageable batches. Then comes the main event, building the model itself. This is where we'll construct the transformer architecture, the brain of our operation, layer by layer. After that, we'll set up our configuration file. This is like the settings menu for our project, where we can easily tweak all the important numbers. With everything in place, we'll write our training script. This is where the learning happens. We'll feed the model data and watch it get smarter over time. And finally, the moment we'll all be waiting for, inference. We'll load our trained model and start a conversation with it, prompting it to generate new and original text. It's a complete journey, so let's take our first step. Alright, first stop, tokenizer.py. Our model can't read words like hello or world, it only understands numbers. The tokenizer is the translator that bridges this gap. We're using a library called sentence piece to train what's known as a byte pair encoding, or BPE, tokenizer. This is a really clever approach. Instead of just splitting by words or characters, it learns the most common subwords from our text. So it might learn that ing, the, and trans are very common and should be their own tokens. We call the train function and give it our text file. I'm using a Wikipedia dump here. We tell it the model type is BPE and set our desired vocab size, which is how many words we want in our dictionary. The most important argument here is byte fallback equals true. This is our safety net. It means if we ever encounter a weird symbol or a character from another language, our tokenizer won't crash. It will just fall back to representing it by its raw bytes. This makes our tokenizer incredibly robust. When we run this, we get two files, a .model file, which is the trained tokenizer logic, and a .vocab file, which is the dictionary it created. After training our tokenizer, it's always a good idea to make sure it works as expected. That's what these next two functions are for. Think of it as a quick sanity check. The load tokenizer function is our way of loading the trained .model file back into our program so we can use it. It creates a sentence piece processor object which has the encode and decode methods we need. The test tokenizer function puts it to the test. First, it takes a sample sentence and calls tokenizer.encode. This converts our human-readable string into a list of integers, according to the vocabulary we just trained. Then, it immediately calls tokenizer.decode on that list of integers. This should hopefully give us back our original sentence. Running this script and seeing the original and decoded text match perfectly gives us the confidence that our tokenizer is ready for action. Okay, our tokenizer is ready. Now we need to prepare our mountain of text data for training in datautils.py. First, look at the load or create data function. Tokenizing a large text file can take a little while, and we don't want to do it every single time we run our training script. So this function is a smart utility. The first time you run it, it reads your text file, encodes the entire thing into a long sequence of tokens, and saves it to a file called encoded data point t. Every subsequent time you run it, it will see that the file already exists and just load it directly, saving you a ton of time. Next, get train valid data does a simple but crucial 90-10 split. We'll use 90% of our data for training the model and hold back the remaining 10% for validation, which helps us check for overfitting. Finally, getBatch is our workhorse. At every step of training, the model needs a small chunk of data. This function goes into our dataset, randomly picks a few starting points, and slices out sequences of a fixed context length. It then creates X, the input, and Y, the target. Remember, Y is just X shifted one token over. The model's job is to look at a sequence of tokens in X and try to predict the corresponding token in Y at every single step. Now for the part you've been waiting for, model.py. We're starting with the absolute heart of the transformer, the head of self-attention. This is where the magic happens. Imagine a token is a person in a crowded room trying to understand a conversation. To do that, it needs to pay attention to other people. In our model, each token creates 3 vectors to help it do this: a query, a key, and a value. The query is like the token asking, "I'm a verb. Who around here is a noun that I might be related to?" The key is like every other token holding up a sign saying, "I'm a noun" or "I'm an adjective." The value is the actual meaningful content that each token holds. In the forward method, we first calculate the attention scores. We do this by taking the dot product of every token's query with every other token's key. This tells us how much each token should pay attention to every other token. But here's a crucial rule. In language, you can't know the future. A token at position 5 shouldn't get information from a token at position 6. That's where our trill mask comes in. We mask the attention scores to hide all future positions, ensuring information only flows from the past to the present. Finally, after a soft max to normalize the scores, we use these attention weights to create a weighted sum of all the value vectors. The result is a new, improved vector for each token that is now enriched with context from all the other tokens it paid attention to. So, a single self-attention head is great, but it's like having just one person trying to understand all the different relationships in a text. What if one head is good at finding subject-verb relationships, but another is better at linking pronouns to nouns? That's the idea behind multi-head attention. It's like having a team of specialists. The multi-head class simply creates a list of our head modules and runs them all in parallel on the same input. In the forward method, you can see we get a list of outputs, one from each head. Each head has focused on something different. We then torch.cat them together, effectively lining up all the specialist reports side by side. This concatenated result is now very rich, but it's also very wide. So we use a final combine linear layer to project it back down to our model's standard embedding size. We've successfully gathered information from multiple perspectives and fused it into a single powerful representation. After our tokens have gathered all this great context from their neighbors through multi-head attention, they need some time to process it. That's the job of the forward layer. You can think of attention as the communication step and the feed-forward layer as the thinking step. This part of the network processes each token individually. If you look at the structure, it's a very standard 2-layer neural network. We take the output from our attention layer, project it to a much larger dimension, in this case 6 times larger, apply a GELU activation, and then project it back down. This expansion and contraction pattern gives the model more capacity to find complex patterns and nonlinear relationships within the features of each token. It's a simple but vital part of the transformer's power. Okay, team, let's assemble our Lego bricks. We've built the attention piece and the feed-forward piece. Now we'll put them together into a single, repeatable block. This transformer block is the fundamental unit that we will stack to create the depth in our network. The structure is very elegant and follows a consistent pattern. The input X comes in, and first it passes through a layer norm. Then it goes into our multi-head attention layer. The output of that is then added back to the original input X. This X plus is the famous residual or skip connection. It's incredibly important because it allows gradients to flow directly through the network during training, which makes it possible to train very deep models without them forgetting the original signal. After that first sublayer, the pattern repeats. The result goes into another layer norm, then into our forward layer, and finally through one more residual connection. This add and norm pattern is a cornerstone of modern deep learning architectures. Now for the grand assembly. In the GPT class, we take our block and stack it up to create the full model. Let's look at the init method. We start with two crucial embedding layers. The token embeddings layer converts our input token numbers into dense vectors, but the model also needs to know the order of the tokens. That's where positions embedding comes in. It provides a unique vector for each position in the sequence. Without this, our model would just see a jumbled bag of words. Then, we create our blocks by making a nn.sequential container with n layers copies of our block class. This is the deep part of our network. After the blocks, a final layer norm and a final linear layer project the output back to the size of our vocabulary, giving us a score for every possible next token. Finally, notice the init weights method. We're not just using the default random weights. We're applying a specific initialization scheme that is known to work well for training transformers, which helps our model converge more smoothly during training. Let's break down the two most important methods in our GPT class. First, the forward method. This is what happens during a single step of training. We take the input token IDs, look up their token embeddings and their position embeddings, and simply add them together. This combined vector, which now contains information about both what the tokens are and where they are, is then passed through our entire stack of transformer blocks. The final output, the logits, is a giant tensor of scores. If we're training, we're also given the targets. Our goal is to calculate how far off our predicted scores were from the actual correct next tokens. We do this using cross-entropy, which gives us a single number, the loss. The whole goal of training is to make this number as small as possible. Second is the generate method, which is the fun part. This is how we generate text. It works in a loop. In each iteration, it takes the text generated so far, passes it through the model to get the logits for the very next token, converts those scores into probabilities using softmax, and then samples a new token from that probability distribution. It then appends this new token to our sequence and repeats the process. This predict, append, repeat cycle is what allows the model to write text one token at a time. Let's take a quick look at config.py. This might seem like a simple file, but it's one of the most important for doing serious research and experimentation. Think of this as the main settings menu or control panel for our entire project. Every important number that defines our model or our training process is here. We have the architecture parameters like batch size, the context window, the embed size, and how many n layers and n heads to use. We also have our training hyperparameters like the learning rate. If you want to see what happens when you train a deeper model, you just come here and change n layers from 7 to 12. If you want to try a different learning rate, you change one line. This practice keeps our main code clean and makes running experiments incredibly easy and organized. Alright, it's time to put on our trainer hats and step into train.py. The main function here orchestrates our entire training run. It starts by loading our tokenizer and data. Then it instantiates our GPT model. Now, here's a neat professional trick in the optimizer setup. We're using AtomW, a fantastic modern optimizer, but we're not applying weight decay, a type of regularization, to all parameters equally. It's often found that applying it to biases or layer normalization parameters can be less effective or even harmful. So, we split our parameters into two groups. The first group gets the parameters with two or more dimensions, like the weights in our linear layers, and we apply our full weight decay to them. The second group gets the one-dimensional parameters like biases, and we turn weight decay off for them. We also set up a cosine annealing LR scheduler. This will start with our initial learning rate and smoothly decrease it in a cosine curve over the course of training, which often helps the model settle into a better final minimum. Training a large model can take hours or even days. Imagine you're 10 hours into a 12-hour training run and your power goes out. It would be a disaster if you had to start over. That's why checkpoints are our saviors. This block of code checks if a checkpoint file already exists. If it does, it loads not just the model's weights, but also the state of the optimizer, the last iteration number, and the best validation loss achieved so far. This allows us to seamlessly resume training right where we left off. Next is the calculate loss helper function. This is how we'll periodically check in on our model's performance. Notice the first and last lines inside the function, model.eval and model.train. This is crucial. Model.eval tells PyTorch to turn off any layers that behave differently during training and testing, like dropout. This gives us a stable, deterministic loss value. After we're done evaluating, we always remember to switch back to model. Train mode to turn those layers back on for the next training step. All right, here we are at the engine room of our project, the main training loop. This is where the learning actually happens, step by step, for hundreds of thousands of iterations. At every single step, we do 4 things. First, we get batch to grab a fresh chunk of training data. Second, we do the forward pass. We feed the batch to the model and get back our loss. Third, we do the backward pass, which is where the learning occurs. We call optimizer.zeroGrad to clear out any old gradients. Then, loss.backward calculates the gradients for this specific batch. It figures out how to adjust each weight to reduce the loss. We then clip grad norm to prevent our gradients from becoming too large and unstable. Finally, optimizer.step actually applies the updates to the model's weights. Fourth, every so often, as determined by eval interval, we pause to evaluate the model. We print the validation loss, and if it's the best score we've seen so far, we save a new checkpoint. This loop is the rhythm of deep learning: forward, backward, update, evaluate, and repeat. After all that hard work training, it's time for the grand finale in Inference.py. This script is all about interacting with our trained model. The setup is simple. We load our tokenizer and our best saved checkpoint file into our GPT model structure. The most important line here is model.eval. This officially puts the model into inference mode, turning off dropout and other training-only features. Then we enter a simple while loop that lets us talk to our AI. We get a prompt from the user's input. We use our tokenizer to encode that text into a tensor of token IDs. Then we pass these IDs to our model's generate method, which, as we know, autoregressively predicts new tokens. Finally, we take the list of generated token IDs and use our tokenizer's decode method to turn them back into a human-readable string, and we print it to the screen. This is where we get to see the creativity and knowledge our model has learned from the data. So let's take a moment to appreciate what we've just accomplished. We have built an entire end-to-end language model pipeline from absolute scratch. We created our own tokenizer. We built a data pipeline. We implemented a transformer from its most basic components. We wrote a robust training script with checkpointing and evaluation, and we created an inference script to use our model. You haven't just used an API, you've built the engine behind it. You now have a deep, practical understanding of the technology that is changing the world. I encourage you to take this code, experiment with it, change the configs, train it on your own data, and continue your learning journey. Thank you so much for building this with me today. If you enjoyed this deep dive, please give the video a like, subscribe for more tutorials like this, and let me know in the comments what you're inspired to build next. Happy coding! Hello everyone, and a huge welcome to this coding adventure and BrainOmega channel. Have you ever seen those incredibly realistic AI-generated images and wondered how they're made? It can feel like magic, but today we're going to pull back the curtain and become the magicians ourselves. One of the cornerstone technologies that kicked off the modern generative AI revolution is the Generative Adversarial Network, or GAN. Please note that this is a simplified version of our GAN, which you can access on our GitHub repository. The link is available in the video description. We will also publish an advanced version of the code soon. In this video, we're going to build a complete working GAN from the ground up using PyTorch. We're not just going to import a pre-made model, we are going to write the code for our generator network that creates images and our discriminator network that judges them. We'll watch them compete, learn, and evolve right before our eyes. This is a hands-on journey from a blank script to an AI that can generate handwritten digits that look just like the real thing. It's a foundational project for anyone serious about deep learning. So, grab your favorite drink, open up your code editor, and let's get started. So, what's the big idea behind a GAN? Before we write a single line of code, let's understand the beautiful core concept. The best analogy is to think of a game between an art forger and an art detective. We have two neural networks playing against each other. The first is the generator. This is our art forger. Its goal is to get so good at creating fake art, in our case images of handwritten digits, that no one can tell it's a fake. It starts out completely clueless, taking a canvas of pure random noise and just splashing paint on it. The second network is the discriminator, our sharp-eyed art detective. Its job is to be an expert critic. It looks at an image and must determine if it's a priceless original from the real museum, our dataset, or a forgery created by our generator. Now here's the adversarial part. We train them together in a loop. The detective gets punished for mislabeling a real image as fake or a fake image as real. The forger gets punished when the detective successfully catches its fakes. So, as the detective gets better, the forger is forced to create more sophisticated fakes to pass inspection. This constant, escalating competition is the engine of learning that pushes our generator to create incredibly realistic images. Alright, let's dive into the code. Before we build our main models, we have two small but very important helper functions. First, let's talk about weights init. A notorious problem with training GANs is that they can be very unstable. Sometimes the generator finds one good image and just keeps making that, or the gradients just vanish. The authors of the DC GAN paper, a landmark in GAN research, discovered that how you initialize the random weights in your neural networks at the very beginning can have a huge impact on training stability. They found that initializing weights from a normal distribution with a mean of 0 and a standard deviation of 0.02 worked really well. This function, weights init, is our tool to apply this specific initialization scheme to all the relevant layers in our models. It's a small trick that can make a big difference. Second, we have our show function. This is purely for us, the humans. Our generator will be producing PyTorch tensors on the GPU with pixel values ranging from -1 to 1. To actually see these as images, we need to do a few things. This function first detaches the tensor from the computation graph and moves it to the CPU because Matplotlib can't work with GPU tensors. Then it reshapes the data and, most importantly, remaps the pixel values from the -1 to 1 range to the 0 to 1 range that image viewers expect. Finally, it arranges them in a nice grid and plots them. This function will be our window into the generator's mind. Next up, let's get our experiment organized with the GAN-config data class. When you work on a machine learning project, you'll have dozens of settings. learning rates, batch sizes, image sizes, directory paths, and more. Hard coding these numbers directly into your training script is a recipe for disaster. It becomes messy and impossible to track your experiments. A much cleaner approach is to use a configuration class, and Python's data class is perfect for this. It's like a central control panel for our entire project. We can define all our key parameters right here. For example, sDimension is the dimensionality of our input noise vector. Think of this as the DNA for each image. A 100-dimensional vector of random numbers is the seed from which an entire image will be grown. lar is our learning rate, and betas are specific parameters for the Adam optimizer that control its momentum. By keeping all these settings in one place, we can easily tweak them, run a new experiment, and see what works best, all without changing our core logic. Now for our first major player, the generator. Remember, this is our art forger. Its mission is to take a simple 100-dimensional random noise vector and transform it into a complex 784-dimensional vector that represents a 28 by 28 pixel image. So, how does it do that? We're using a NN sequential model, which is like an assembly line for data. The noise vector Z goes in one end and the image comes out the other. We're using a series of linear layers to progressively upsample or increase the number of features, from our ZDIM of 100 up to 256, then 512, then 1024, and finally to our target image dimension of 784. After each upsampling layer, we use batch norm 1D. This is a normalization technique that helps stabilize training by keeping the outputs of each layer in a consistent range, which is especially important in GANs. Then, a ReLU activation introduces nonlinearity, allowing the model to learn more complex relationships. The final layer is a tanh activation function. This is a very deliberate choice. Tanh squishes all the output values into a range of -1 to 1. This is crucial because we're going to normalize our real input images to the exact same range. By doing this, we ensure that the fake images created by the generator and the real images from our dataset are on a level playing field. With our forger built, we now need our detective, the discriminator. Its architecture is essentially the mirror image of the generator. Its job is to take a high-dimensional input, a 784-pixel image, and classify it, boiling it all down to a single number, representing its verdict, real or fake. It's also an NN sequential model. It takes the flattened image and passes it through linear layers that progressively downsample the number of features, from 512 down to 256. For our activation function, we're using leaky ReLU. This is a popular choice in GAN discriminators. Why? A standard ReLU function outputs 0 for any negative input, which means the neuron can die and stop learning. Leaky ReLU has a small non-zero slope for negative inputs, so it always allows a small gradient to flow through. This helps keep our network alive and learning throughout the training process. Finally, the output layer is a single linear neuron that produces one number, a logit. We don't apply a sigmoid function here because our loss function, BCE with logits loss, is designed to take raw logits for better numerical stability. This single number is the discriminator's final judgment. Okay, our models are designed. Now let's prepare the real art for our detective to study. That's the job of the getDataLoader function. Every image in the MNIST dataset will pass through a small assembly line of transformations we define with transforms compose. First, transforms. Resize, make sure every image is the correct size. Then transforms to tensor does two things. It converts the image data into a PyTorch tensor and scales the pixel values from their original range into a new range of 0 to 1. The final transforms normalize 0.5, 0.5 is the key. It takes the 0-1 range and remaps it to 1-1. Why? Because this now perfectly matches the negative 1,1 output range of our generator's TAN activation. This synchronization is critical for fair competition. We then load the MNIST dataset with these transforms and wrap it all in a data loader. The data loader is a fantastic PyTorch utility that automatically handles creating mini batches of data, shuffling the data every epoch to ensure our model doesn't just memorize the order, and using multiple CPU workers to load data in the background so our GPU is never waiting. Alright, it's time to enter the training arena. In the first part of our train function, we do all the setup for the main event. First, we create our output directories and set up a summary writer. This writer is our connection to TensorBoard, a powerful tool that will let us visualize our training progress, like plotting our loss curves in real time. Next, we call our getDataLoader to get our data iterator, and we initialize our generator and discriminator models, making sure to move them to the GPU with .2CFG device if one is available. Then, we immediately call apply weights init on both models. This is where we use our helper function to set their initial weights according to the best practices for GANs. Finally, we set up our criterion, which is BCE with logits loss, the perfect loss function for this kind of binary classification task. And, crucially, we create two separate Adam optimizers. OptGen will only update the weights of the generator, and OptDisc will only update the weights of the discriminator. They are two separate players in this game, so they need their own dedicated optimizers. Now we enter the main training loop, and the adversarial game begins. For every batch of images, round 1 goes to the detective, the discriminator. Our goal here is to make it a better critic. We start by calling optDisc 0grad to clear any old gradients from the previous step. The discriminator's training has two parts. First, we show it the real images. We calculate its loss by comparing its predictions, disk real output, against a tensor of all ones, because we want it to confidently label these as real. Second, we teach it about fakes. We generate a batch of fake images using the generator. Then we pass these fakes to the discriminator. This time we compare its predictions, disk fake output, against a tensor of all zeros. Now look at this line, disk fake detach. The .detach call here is the most critical detail in this step. It tells PyTorch to treat the fake tensor as a constant, as if it were just an image we loaded from a file. This effectively freezes the generator, ensuring that when we call lossDisk.backward, the gradients will only be calculated for the discriminator's weights. We are exclusively training the detective in this round. Finally, we average the loss from the real and fake batches, backpropagate, and update the discriminator's weights. The detective is now a little bit smarter. Okay, the detective has had its turn. Round 2. The forger, our generator, gets to learn. Its goal is simple: to get better at fooling the now smarter discriminator. First, we clear the generator's old gradients with opt-gen 0grad. Now here comes the beautiful clever trick of GANs. We take the same batch of fake images we created a moment ago and pass them through the discriminator one more time. But notice, this time we do not use .detach. We want the computational graph to remain connected, so gradients can flow all the way back to the generator. So how do we calculate the generator's loss? We compare the discriminator's output on these fake images to real labels, a tensor of all ones. We are essentially telling the loss function a lie. We are saying the generator's goal is to produce images that the discriminator classifies as real. The loss gene therefore represents how well the generator failed at this goal. By calling loss.gen backward, we calculate the gradients that will teach the generator how to adjust its weights to make its output images even more likely to be classified as real by the discriminator in the future. We then take a step with the generator's optimizer, and the forger's training for this round is complete. Training a GAN without watching it is like flying blind. Is the generator actually improving, or is it just making noise? Is one model overpowering the other? This section of the code is our cockpit dashboard, where we track our progress. Throughout the loop, we accumulate the loss*disk and loss*gen values. Then every log interval steps, we print out the average losses. This gives us a quick numerical check. Ideally, you want to see both losses staying relatively balanced. If one drops to 0, it means one player has completely overpowered the other, and learning has stopped. More importantly, we use torch.nograd. This is a context manager that tells PyTorch, for this block of code, we're just looking, not training, so you don't need to track gradients. This makes everything inside run faster and use less memory. We generate a new sample of fake images and use our show function to plot them next to a batch of real images. This visual feedback is everything. You'll literally see your generator go from producing fuzzy static to recognizable digits over the course of training. Finally, we use our writer to log the scalar loss values to TensorBoard, which will create beautiful graphs for us to analyze later. Finally, let's look at the very bottom of the script. This is standard Python that ensures the code inside only runs when you execute this file directly from the command line, not when it's imported by another file. Here, we're using Python's built-in argparse library. This is what transforms our script into a powerful command line tool. By defining arguments like ~epochs or ~lr, we give ourselves the ability to control our experiments without ever having to edit the source code. This is how you would work in a real research or production environment. You can start one training run with python train.py, epochs 50, and then start another one in a different terminal with python train.py, epochs 100, LR 0.0001 to compare results. The script parses any arguments you provide, uses them to create our GAN config object, and then passes that configuration into our train function to kick off the whole process. It's a very clean and professional way to handle experimentation. So let's take a step back and appreciate what you've just built. This isn't just a script. It's a complete system embodying a fundamental concept in AI. You have built a generator, an AI artist that can create novel content from nothing but random noise. You've built a discriminator, a critical AI judge that learns to differentiate real from fake. And most importantly, you've orchestrated the adversarial training loop, the competitive dance that allows both networks to achieve a state of equilibrium where the generated images become indistinguishable from reality. You've done this all within a clean, configurable project. You now have a deep, hands-on understanding of how GANs work. The next steps are up to you. Try a new dataset like Fashion MNIST. The biggest leap would be to convert our simple linear models into convolutional ones to build a DC GAN, which will yield even more impressive images. But for now, play with the hyperparameters, see what breaks, see what works, and truly make this project your own. Thank you so much for following along with this deep dive. If you found this tutorial helpful, please give it a like and subscribe for more content that goes beyond the surface. Happy generating! Hello everyone, and a huge welcome to this hands-on project. We all know Python is fantastic for getting ideas up and running quickly, but when it comes to raw computational speed, C++ is the undisputed champion. What if we could get the best of both worlds? What if we could write our logic in simple Python and then have a personal AI expert instantly rewrite it into blazingly fast, high-performance C++? You have access to the code on our GitHub page, and you can find the link in the description of this video. Well, today, that's exactly what we're going to build. We are going to create a complete Python to C++ code converter from scratch. This isn't just a simple script, it's a full-stack application that uses powerful large language models like GPT-4o and Claude 3.5 Sonnet as its reasoning engine. We'll build the back-end logic, the AI communication pipeline, and a beautiful web interface with Gradio where you can see the magic happen in real time. This is a deep dive tutorial where we'll explain every line of code and the reasoning behind it. By the end, you'll have a powerful tool and a deep understanding of how to integrate modern AI into your own applications. So, let's get started. Before we write a single line of code, let's zoom out and look at our project's blueprint. A good application has a clear structure, and ours can be thought of as a factory assembly line, with each file playing a specific role. It all begins at the front door, our Gradio user interface, UI.py. This is where the user will interact with our application, pasting in their Python code and clicking buttons. When the user clicks Convert, the request is sent to our conversion logic, conversion.py. Think of this as our master translator and project manager. Its job is to take the Python code, wrap it in a carefully constructed set of instructions, and manage communication with our AI models. Next, the conversion logic sends the request over the internet to the LLM API. This is where the heavy lifting happens. A massive model like GPT-4o or Claude analyzes the request and generates the high-performance C++ code. The generated code is then sent back to our application. At this point, our execution engine, execution.py, can be used. This part of our factory is the quality control and testing department. It can compile and run the new C++ code and the original Python code, so we can verify that the logic is correct. Finally, the results, both the newly generated C++ code and the output from execution, are sent back to the Gradio UI to be displayed neatly for the user. Understanding this flow will make it much easier to see how each piece of code we write fits into the bigger picture. Alright, let's start with the foundation of any good project. The configuration file, config.py. Think of this as the central control panel for our entire application. Instead of hard-coding important values throughout our scripts, we define them all in one clean, organized place. First, we use a library called python.env. This allows us to store our secret API keys in a special file named .env. This is a critical security practice because it ensures we never accidentally commit our sensitive credentials to a public GitHub repository. The load.env function reads this file and makes the keys available as environment variables. Next, we create what are called API clients. An API client is an object that handles all the complex details of communicating with a service. Think of it like having a dedicated pre-programmed phone line directly to OpenAI and another one to Anthropic. We instantiate them here so they're ready to use anywhere in our project. We also define our model names as constants. This is great because if a new, better model like GPT-5 comes out, we only have to change the name in this one spot. Finally, we define our system message. This is our prime directive for the AI. It sets the context and personality for every single conversation we have with it. We're telling it from the start. You are an expert C++ developer. Your goal is performance. Your output should be code. This is the foundation of our prompt engineering. Now we move to the heart of our application, conversion.py, and specifically to the most creative part of working with LLMs, prompt engineering. The AI models we're using are incredibly powerful, but they aren't mind readers. The quality of the C++ code we get back is almost entirely dependent on how clearly and effectively we ask for it. Let's break down how we construct our request. The user prompt for function builds the specific task for this one conversion. We don't just give it the Python code. We surround it with very clear instructions. We explicitly say fastest possible implementation and produces identical output. We even give it helpful hints that a good programmer would know, like pay attention to number types to ensure no int overflows, and remember to include all necessary C++ packages. This level of detail dramatically improves the quality of the generated code. Then, the messages for function assembles the final payload. Modern chat-based models work best with a structured conversation history. Here, we create a list of messages. The first message is our system role. Using the system message from our config file, this sets the AI's long-term personality. The second message is the user role, which contains the specific one-time request we just built. This system user structure is the standard and most effective way to guide the model's behavior. With our perfect prompt constructed, it's time to actually send it to the AI. That's the job of our StreamGPT and StreamClaude functions. Now, we could just send the request and wait for the full C++ code to come back, but that might take 5 or 10 seconds, and during that time, our user interface would just be frozen, leaving the user wondering if it's even working. A much better user experience is to stream the response. This means the model sends us the code token by token as it generates it. Let's look at StreamGPT. We make our API call, but we add the crucial argument stream equals true. This changes the return value from a single object to a generator. We can then loop through this generator, and in each iteration, we get a small chunk of the response. We append this chunk to our reply and then yield the current state of the reply. In our UI, this will make the C++ code appear to be typed out in real time. Now, StreamClaude is similar, but adds another layer of professionalism, error handling with exponential backoff. Sometimes a popular API can be temporarily overloaded. This code is wrapped in a try.except block. If it catches an API error that indicates the service is overloaded, it doesn't just crash. It waits for a couple of seconds and then tries again. If it fails again, it doubles the waiting time before the next attempt. This is a robust way to handle temporary network issues and makes our application much more reliable. So we have functions to build our prompt and functions to talk to the APIs. Now we need something to connect them all together. That's the optimize function. It's the orchestrator or the project manager for our backend. This is the single function that our user interface will call. It's very straightforward. It takes the user's Python code and the model they selected from the drop-down menu in the UI. It then uses a simple if-elif block to act as a switchboard, choosing the correct streaming function, StreamGPT or StreamClaude, to call based on the user's choice. It then needs to consume the entire stream. The for loop iterates through every partial result yielded by our streaming function. While the UI will be updating in real time with these partial results, this loop's purpose is to wait until the stream is completely finished and capture the final output. Once the loop is done, we have the complete C++ code. We pass this to our simple write output helper function. This function just does a little bit of text cleaning to remove any markdown formatting the AI might have added, and then saves the final clean code to a file named optimized.cpp. Finally, it returns the complete code, which Gradio will then display in the output text box in our UI. Generating the C++ code is cool, but how do we know it actually works? And is it really faster? That's where our execution.py script comes in. This is our execution engine and testing ground. First, let's look at execute Python. To run Python code that's currently just a string, we can use the built-in exec function. It's very powerful, but be aware, it can be a security risk if you're running untrusted code. To capture the output of any print statements within that code, we do a clever trick. We temporarily hijack Python's standard output and redirect it to an in-memory text buffer using io.stringio. We run the code, capture everything printed to the buffer, and then restore the standard output. Now for execute CPP. This is a two-step process that mimics what a developer would do on the command line. First, we use Python's sub-process module to call the clang ++ compiler. Look at the flags we are using. -std equals C++ 17 ensures we're using a modern C++ standard. Allfast is an aggressive optimization flag telling the compiler prioritize speed above all else. And March native tells it to generate code that is specifically optimized for the exact CPU architecture of the machine it's running on. This is where we get our high performance. If the code compiles successfully, we then use subprocess a second time to run the newly created executable and capture its output. If any errors happen during compilation or runtime, our try except block will catch them and return the error message to the user. Now let's build the front door to our application, the user interface in UI.py. Normally, to build a web interface like this, you'd need to be a web developer and know HTML, CSS, and JavaScript. But the Gradio library is like a superpower for Python developers, letting us build and share interactive UIs with just a few lines of Python. We define our entire layout inside A with GR blocks as UI block. This gives us full control. We use GR tabs to create a clean, organized interface with a conversion tab and an execution tab. Inside these, we lay out our components using GRrow and widgets like grTextbox for multi-line code input, GR dropdown for our model selection, and GR button for our actions. We can even pass in custom CSS to style it and give it a polished, professional look. Now for the most magical part, the .click methods at the bottom. This is how we wire up our front-end buttons to our back-end Python functions. This one-line convert button.click optimize comma space says everything. When the convert button is clicked, call the optimize function. Take the values from the Python input text box and the model dropdown as its inputs, and whatever that function returns, display it in the CPP output text box. It's an incredibly simple and powerful way to connect a user interface to our code. Last but not least, we have our launcher script, main.py. Every great application needs a single clear starting point, a main entrance, and that's exactly what this file is. Its job is incredibly simple but essential. It imports just one thing, the launch.ui function we just defined in our ui.py file. Then, inside the standard if name equals main block, which ensures this code only runs when we execute this script directly, we do two things. First, we call launch UI, which runs all our Gradio code and constructs the entire UI object in memory. Second, we call the launch method on that UI object. This is the final command that actually starts the local web server, builds the HTML and JavaScript for the web page, and with in-browser equals true, automatically opens a new tab in your default browser pointing to our running application. To start this entire complex full-stack AI application, all a user needs to do is run one simple command in their terminal, python main.py. So let's step back and look at what you have just built. This is so much more than just a simple script. You have orchestrated a complete system of modern AI tools to create a genuinely useful and powerful application. You've learned how to securely manage API keys and interact with state-of-the-art language models like GPT-4o and Claude 3.5. You've practiced the crucial art of prompt engineering to guide and control the behavior of these AIs. You've built a robust execution engine that can compile and run native code from Python, and you've wrapped it all in a beautiful full-stack web application using Gradio. The skills you've learned here are the foundation for building the next generation of AI-powered software. I encourage you to take this project and make it your own. Try adding more target languages like Rust or Go. You could even build in an automatic performance benchmark that runs both versions and shows the user exactly how much faster the C++ code is. Thank you so much for joining me on this journey. If you found this tutorial valuable and you feel like you've learned a lot, please give the video a like and subscribe for more deep dives into building real-world AI applications. Happy coding! Hello everyone, and welcome to what I think is a really fun and exciting project. We've all chatted with AI models like ChatGPT or Claude one-on-one, but have you ever wondered what would happen if you put them in the same room and made them talk to each other? What would they say? Would they agree? Would they argue? The complete code of the application is available in our GitHub repository. You can find the link in the description of this video. Well, today we're going to find out. We're going to build a multi-chatbot conversation system from scratch. This application will allow us to give a topic to 3 different AI models, one from OpenAI, one from Anthropic, Claude, and a local Llama model, and watch in real time as they not only respond to the topic but also critique each other's answers. We'll build the entire system using Python, from the back-end logic that calls the APIs to a beautiful streaming web interface using Gradio. This is a fantastic way to learn about multi-agent systems and API integration. Let's start building our AI debate club. Before we write any code, let's understand the flow of our application. You can think of it as setting up and running a formal debate club. Our Gradio UI, which we'll define in main.py, is where we, the user, act as the moderator. We propose the topic for the debate. When we click Run, the topic is handed off to our conversation conductor, the run conversation function inside conversation.py. This function is like the debate's director. It manages the entire flow. The conductor first sends the initial topic to each of our chatbot agents. Each agent is an instance of our chat system class, which is a universal wrapper we'll build to handle communication with the different APIs. Each agent forms its opening statement. Then comes the most interesting part, the critique round. The conductor takes the response from, say, the OpenAI agent and shows it to the Claude and Llama agents, asking them, "What do you think of this?" It does this for every agent's response. Crucially, every single message, every opening statement, and every critique is sent back to our Gradio UI the moment it's generated. This is called streaming, and it will allow us to watch the entire debate unfold live. It's a clear, logical flow that we're now going to build piece by piece. Let's start with our most fundamental building block, the chat system class in chatsystem.py. Think of this as a universal translator or a blueprint for any chatbot we want to add to our system. By having this generic wrapper, we can make our project easily extensible in the future. In the init constructor, we store everything that defines one of our debaters. We pass in the processor, which is the actual API client object from libraries like OpenAI or Anthropic. We give it a system string which defines its personality and instructions. We specify the model name, and we initialize an empty list called messages to store this bot's unique conversation history. Now, the call method is where the communication happens. It takes a new message, appends it to its history, and then makes the API call. Here, we see a key piece of real-world coding, handling slight differences between APIs. The Anthropic API for Claude expects the system message to be a separate parameter in the create call. However, the OpenAI API, which the local Llama server also mimics, expects the system message to be the very first item in the messages list itself. This simple if-else block handles that difference gracefully, allowing our single call method to work for all our bots. Now we move to conversation.py, the script that will direct our AI play. The first part of this file is all about setting the stage and casting our characters. We start by loading our secret API keys from our .env file. Then we initialize the client object for each of our three services. For OpenAI and Claude, it's straightforward. For our local Llama model, we point the OpenAI client to our local server address, which is typically localhost:11434. Next, we define the specific models we'll be using. I've chosen some fast and capable models here like GPT-4o Mini and Claude 3 Haiku to keep the conversation flowing quickly. And now for the fun part, creating our debaters. We create 3 instances of our chat system class. For each one, we pass in the appropriate client and model name, but most importantly, we give each one a system string that defines its personality. Notice the prompt for OpenAI chat. We've explicitly told it to be insightful but also snarky, to disagree and to challenge everything. This will make the conversation much more interesting. We then group all our chatbot objects into a simple list called Chatbots for easy access. This is the core logic of our application, the run conversation function. A key thing to understand is that this is a Python generator function because it uses the yield keyword. Think of yield as pressing a pause button. The function runs until it hits a yield, sends the specified data back to whoever called it, in our case the Gradio UI, and then patiently waits. When the UI is ready for the next update, the function resumes from exactly where it left off. This is the mechanism that enables our real-time streaming display. First, we loop through our chatbots and reset their message history to ensure every conversation starts fresh. We prepare the initial prompt from the user's topic. We set up a dictionary called logs to keep track of the text that will appear in each chatbot's display box. Now, for the first main loop, we iterate through each chatbot in our list. For each one, we first update its log to say calling and immediately yield this status to the UI. Then we make the actual call to the bot's API to get its response to the initial prompt. We store this response and then update the log again with the full response text, yielding once more to the UI. This loop ensures each bot gives its opening statement one by one. Now for the most dynamic part of the debate, the critique round or the rebuttals. This happens right after the first loop finishes. Here we have a nested loop structure. The outer loop iterates through each of our chatbots. This is the bot that will be doing the critiquing. The inner loop then iterates through the responses we collected in the first round. This is the response that is being critiqued. We have a simple if statement to make sure a bot doesn't critique its own response. Then for each critique, we again yield a status update to the UI like critiquing response of Claude. We then construct a brand new prompt. This time, the prompt is very specific. We ask the current bot to critique the following response from, and we insert the other bot's name and its actual response. We then call the bot's API with this new critique prompt to get its analysis. Finally, we format this critique, add it to the bot's log, and yield the final state to the user interface. This nested loop ensures a full round robin of critiques, making for a very interactive and engaging output. Finally, let's look at main.py, where we build the stage for our AI debate using Gradio. This script is wonderfully concise thanks to the power of the Gradio library. We create a layout using GR blocks. We use GR Markdown to add our titles and descriptions. We use GRrow to organize our components horizontally. We create a text box for the user to enter their topic and a button to start the conversation. Below that, we create 3 separate Markdown components, one for each of our AI models to serve as their display boxes. Now for the most important part, the .click event handler. This single line of code connects our front end to our back end. We tell the run button that when it is clicked, it must call our run conversation function. The input should be the value from our topic input text box. And here's the key for our multi-output display. The outputs parameter is a list of our 3 markdown components. Because our run conversation function yields a tuple of 3 strings, Gradio is smart enough to map the first yielded value to the first output component, the second value to the second, and so on. This is how each bot's log gets routed to the correct box in the UI. Finally, demo.launch starts the web server and opens the application in your browser. So, let's step back and look at the powerful system you've just built. This is more than just a simple chatbot. You've created a universal chatbot wrapper, a piece of reusable code that makes it easy to add new AI models. You've built a multi-agent conductor, a sophisticated piece of logic that can orchestrate complex multi-step interactions between different AIs. And you've wrapped it all in a beautiful streaming web UI that brings the entire process to life. You now have a framework for experimenting with multi-agent AI systems, which is a cutting-edge area of research. The possibilities from here are endless. You could easily add a 4th chatbot to the debate, perhaps one using Google's Gemini API. You could create more complex conversation flows with multiple rounds of rebuttal. You could even change the prompts to make the AIs collaborate on writing a story or solving a coding problem. Thank you so much for following this tutorial. If you learned something new and had fun building this project, please give the video a like and subscribe for more deep dives into creative and practical AI applications. Happy coding! Hello everyone, and welcome to a really exciting and cutting-edge topic in AI. We often think of AI in 2 ways. There's machine learning, which is great at pattern recognition and gut feelings, and then there's old-school symbolic AI, which is based on logic and hard-coded rules. What if we could get the best of both worlds? That's exactly what we're going to do today. We are going to build a Neuro-Symbolic reinforcement learning agent from scratch. We'll create an agent that learns to solve the classic cart-pole balancing problem using a hybrid brain. One part of its brain will be a fast, dynamic echo state network, providing the neuro component. The other part will be a symbolic reasoning module, a set of human-defined rules that provide the symbolic common sense. We'll code every component, see how they work together, and train the agent to master the game. This is a fantastic look into the future of building more robust and interpretable AI systems. Let's get started. The complete source code for this project is available on our GitHub repository. Just follow the link in the video description to check it out. So, what is the big idea behind our Neuro-Symbolic agent? We're essentially trying to give our AI 2 different ways of thinking, much like humans do. First, we have our symbolic reasoning module. You can think of this as System 2 thinking. It's slow, deliberate, and based on logical rules that we explicitly write. It's our AI's common sense or rulebook. For the cart pole game, a rule might be as simple as, if the pole is leaning too far to the left, it's a good idea to push the cart to the left. This part of the brain is easy for us to understand and debug, but it might not be able to handle every complex situation. Second, we have the Echo State Network, or ESN. This is our System 1 thinking. It's fast, intuitive, and based on recognizing complex patterns over time. It's a special kind of recurrent neural network that maintains a rich, echoing memory of recent events. It doesn't operate on explicit rules. It just develops a gut feeling about the state of the game. Our agent's strategy is to listen to both its logical rulebook and its neural intuition, combine their advice, and then make a final, more robust decision on which action to take. Let's start with the most straightforward part of our hybrid brain, the symbolic reasoning module. This class is our explicit rulebook. In the init method, we define a dictionary called rules. Each key corresponds to a piece of the game's state, like pole angle, and its value is a lambda function that represents our rule. For example, the pole angle rule says, if the angle is very negative, leaning left, strongly suggest moving left by outputting 0.9, 0.1. If it's very positive, leaning right, strongly suggest moving right with 0.1, 0.9. Otherwise, if it's balanced, have no opinion and output 0.5, 0.5. We have a similar rule for the cart's position. The forward method takes the current state of the game, extracts the relevant values, applies all the rules, and then simply averages their suggested action probabilities to get a final symbolic output. We also have a refine rules method, which is a very simple way to make our symbolic system adaptable. After an episode, if the overall feedback was negative, it will update the rules to be a little less confident in their suggestions. It's a basic form of learning for our logical system. Now for the neuro part of our agent, the Neuro-Symbolic Echo State Network. Let's really take our time here and focus on how we initialize its core component, the reservoir, because this is what makes an echo state network so unique and powerful. An ESN is a type of recurrent neural network, but it has a revolutionary twist. In a traditional RNN, you use backpropagation to painstakingly train all the weights, which can be slow and difficult. The incredible idea behind ESNs is that we can create a large, complex, randomly generated network and keep its internal connections fixed. We never train them. This fixed network is called the reservoir. Think of it like a complex wind chime. You don't train the wind chime, you just build it. But when a gust of wind, our input signal, blows through it, the chime produces a very rich and complex set of sounds or echoes that are a high-dimensional representation of that simple gust. The reservoir works the same way. It's an echo chamber for data. When we feed our game state into it, the signal bounces around this fixed, random structure, creating complex patterns and dynamic states that capture the history of what has happened. So, how do we build this? First, we create self, win. This is the input weight matrix. It's our door into the reservoir. Its job is to take the low-dimensional game state, which has 4 features, and project it into our much higher dimensional reservoir space, which has 150 features. We initialize it with small random numbers. Next, and this is the most important part, we create self-W, the recurrent weight matrix that defines the internal connections of the reservoir itself. This is a careful 4-step process. We start with a dense matrix of random numbers using NumPy. We introduce sparsity. We create another random matrix of the same size and use it as a mask to set about 90% of the connections in W to 0. Why do this? A sparse reservoir is often more stable, computationally cheaper, and can lead to richer, more decoupled dynamics. Now for the magic, spectral radius scaling. This is a crucial mathematical step to ensure the reservoir has the echo state property. We calculate the eigenvalues of our matrix W and find the one with the largest absolute value. This is the spectral radius. We then scale our entire W matrix by this value. This ensures that the reservoir is stable. It prevents the echoes from either dying out to 0 instantly or exploding into infinity. We scale it by a factor of 0.9 to keep it just on the edge of stability, which is often where the most interesting dynamics occur. Finally, we convert our NumPy matrix W into a PyTorch tensor. Notice very carefully that we are not wrapping it in nen.parameter. This is how we tell PyTorch that these weights are fixed and should not be updated during training. This is the defining characteristic of an echo state network and what makes it so efficient. Continuing in our init method, let's assemble the rest of our hybrid model. After creating our input and reservoir weights, we initialize self.state, which is a vector of zeros that will hold the activation values of our reservoir neurons at each time step. Next, we create an instance of our symbolic reasoning module, the rulebook we defined earlier. This means every instance of our ESN will contain its own little logical component. Now for the most important part of an echo state network, the readout layer. This is a simple NN dot linear layer. The revolutionary idea of ESNs is that the randomly initialized reservoir is powerful enough to generate useful features. So the only part we actually need to train is this final readout layer. It reads the state of the reservoir and learns to map those complex patterns to a useful output. But look at its input dimension, reservoir dimension plus symbolic dimension. Our readout layer isn't just looking at the neural reservoir, it's also looking at the output from our symbolic module. This is the point of fusion where our two ways of thinking, the neural and the symbolic, come together before a final decision is made. Now, let's trace the flow of data through our model in the forward pass. This is what happens every time our agent needs to decide on an action. First, we update the state of our reservoir. The new state is calculated by taking the current input x multiplied by the input weights, adding it to the previous state of the reservoir multiplied by the recurrent weights, and then passing the result through a TH activation function. This is what makes it a recurrence network. Its current state depends on its previous state. This is our neurosignal. Second, in parallel, we call the forward method of our symbolic module. This takes the same input x and uses our hard-coded rules to produce the symbolic signal. Third, we combine these two signals. We use TorchCat to simply concatenate the reservoir state vector and the symbolic output vector into one larger vector. Finally, this combined vector, which now contains both the intuitive patterns from the ESN and the logical suggestions from the rulebook, is passed to our single trainable readout layer, which produces the final output scores for each possible action. The output of our Neuro-Symbolic echo state network is a set of raw scores, or logits, for each action. To use this in our reinforcement learning context, we need to convert these scores into probabilities. That's the simple job of our policy network class. It's a very thin wrapper. In its init method, it takes our ESN model as an argument and also defines a softmax layer. In its forward method, it first calls our ESN to get the raw scores. Then, it passes those scores through the softmax layer. Softmax is a mathematical function that takes a vector of numbers and turns it into a probability distribution, a new vector where all the elements are between 0 and 1 and they all sum up to 1. The output of this policy network is what we'll use to actually choose an action. All right, it's time to bring everything together in our main train function. This is where we set up the entire reinforcement learning experiment. First, we set our device to a GPU if one is available, and we create our CardPole v1 environment using the GIM library. We then get the input.dim and action.dim directly from the environment itself. This makes our code flexible. We also choose the size of our ESN's reservoir. This is a key hyperparameter we could tune later. Next, we instantiate our models. We first create the Neuro-Symbolic echo state network, and then we wrap it inside our policy network. Finally, we set up our optimizer. We're using the popular Adam optimizer. Now look closely at what we pass it. Policy.parameters. This is a key detail of using an echo state network. Because we defined the reservoir weights, self.w, as simple tensors and not nn.parameters, they are not included in this list. The only trainable parameters here are from the ESN's readout layer and the softmax layer. This is why ESNs can be so fast. We are only optimizing a very small part of the network. Now we enter the main training loop, which runs for a set number of episodes. Each episode is like one full attempt or one life for our agent. Inside the while not done loop, our agent interacts with the world. At each time step, first, it takes the current state and passes it to our policy network to get a vector of action probabilities. Second, instead of just greedily picking the action with the highest probability, we create a categorical distribution and sample from it. This sampling introduces exploration, allowing the agent to try out different actions and discover what works best. Third, we store the log probability of the action we just sampled. This is crucial for the policy gradient calculation we'll do later. Fourth, we perform the action in the environment using env step. The environment responds with the next observation, a reward, and flags to tell us if the episode has terminated. Finally, we store the reward we received and update our state to be the next state we just observed, getting ready for the next iteration of the loop. This slide shows the part of the code where our hybrid Neuro-Symbolic approach really comes to life. Inside the step loop, after our agent acts and receives a reward, we update a feedback dictionary. This is separate from the main reinforcement learning process. We're essentially creating a simple credit assignment system for our rules. For instance, for the pole angle, we check if the pole is nicely centered. If it is, we add the positive reward to its feedback score. If it's tilted too far, we give it a penalty of -1, regardless of the reward from the environment. We do the same for the cart's position. This helps us track if the states where our rules are active are generally leading to good or bad outcomes. Then, crucially, after the entire episode is finished, we call esn.refine symbolic rules and pass in this accumulated feedback dictionary. This is where our symbolic module gets a chance to learn and adapt its own rules based on the overall performance during that episode, making our entire system more adaptive. After each episode concludes, our agent needs to reflect on what happened and learn from its experience. This is done using the reinforced policy gradient algorithm. First, we need to figure out how good each action really was. Instead of just using the immediate reward, we calculate the discounted return. We loop through the rewards backwards, and for each step, we calculate R, which is the immediate reward plus the discounted value of all future rewards. This gives us a better estimate of the long-term value of being in a particular state. Second, we standardize these returns by subtracting the mean and dividing by the standard deviation. This is a very common and effective trick in policy gradient methods that helps stabilize training. Third, we calculate our loss. The formula is simple but powerful. For each action taken, we multiply its log probability by the standardized discounted return we just calculated. The intuition is this: if an action led to a high positive return, we want to make that action more likely in the future. If it led to a low negative return, we want to make it less likely. Finally, we perform the standard PyTorch update steps. We zero the gradients, backpropagate our calculated loss, and take a step with our optimizer. This updates the trainable weights in our ESN's readout layer, making our policy smarter for the next episode. So, let's step back and look at the amazing hybrid AI we've built today. This is not a standard black box neural network. We created a symbolic module, a transparent rulebook that injects our own domain knowledge into the agent. We also built an echo state network, a fascinating type of recurrent network that uses a fixed reservoir to efficiently capture temporal patterns. We then fused these two components into a single neuro-symbolic model, creating an agent that benefits from both logic and intuition. Finally, we successfully trained this hybrid brain using the classic reinforce algorithm to solve the cart pole challenge. This project is a fantastic starting point into the world of neuro-symbolic AI. From here, you could try designing more complex and adaptive symbolic rules. You could swap out the echo state network for other popular architectures like an LSTM or even a small transformer. Or you could try applying this powerful hybrid approach to much more complex reinforcement learning problems. Thank you so much for joining me on this deep dive. If you enjoyed building this and learned something new, Please give the video a like and subscribe for more tutorials on cutting-edge AI concepts. Happy coding! Hello everyone, and welcome to a deep dive tutorial on a truly fascinating and powerful corner of the neural network universe, echo state networks. If you've worked with recurrent neural networks like LSTMs or GRUs, you know how powerful they are, but you also know that training them can be incredibly slow and computationally expensive. Today we're going to explore an alternative paradigm called reservoir computing, and specifically its most popular implementation, the echo state network or ESN. We're going to learn the theory behind why these networks are so efficient, and then we're going to build one from absolute scratch. But we won't stop there. We'll build an advanced multi-scale ESN and use it as the brain for a reinforcement learning agent tasked with solving the classic cart pole problem. This is a university-level topic, but we're going to break it down step by step so that every component is crystal clear. This will be a long and detailed session, so get comfortable and let's begin our deep dive. You can find the complete project code on our GitHub. Just click the link in the description below this video. Before we dive into our solution, the echo state network, let's first understand the problem it was designed to solve. Why do we need an alternative to standard recurrent neural networks like LSTMs or GRUs? While these traditional RNNs are incredibly powerful for processing sequential data, they come with some significant challenges, especially during training. The main training algorithm, backpropagation through time, involves unrolling the network through its history, which is a very slow and memory-hungry process. Furthermore, they suffer from the infamous vanishing and exploding gradients problem. Imagine you're trying to teach the network by sending an error signal backwards in time. As this signal travels, it's repeatedly multiplied by the network's weights. If those weights are small, the signal can shrink exponentially until it vanishes, and the network can't learn from events that happened long ago. If the weights are large, the signal can explode, destabilizing the entire training process. This leads to a difficult and often frustrating process of hyperparameter tuning to get them to work well. This begs the question that researchers asked in the early 2000s, can we get all the benefits of these rich recurrent dynamics without paying the high price of this complex training? The answer, it turns out, is yes. This brings us to the beautiful and elegant core idea of the echo state network. The key insight is to decouple the part of the network that creates rich dynamics from the part that actually learns. An ESN consists of three distinct parts. We have an input layer, which simply feeds our external signal into the system. Then we have the heart of the ESN, the reservoir. This is a large, recurrently connected network of neurons. But here's the radical idea. We initialize this reservoir with random weights, and then we freeze it. We never ever train or update these internal connections. Its sole purpose is to act as a high-dimensional, nonlinear echo chamber. When an input signal enters, it causes complex reverberations or echoes throughout this reservoir. The state of the reservoir at any moment is a rich, dynamic reflection of the recent history of the inputs it has seen. Finally, we have the readout layer. This is a very simple linear layer, and it's the only part of the entire system that we train. Its job is to look at the incredibly complex and high-dimensional state of the reservoir's neurons and learn to map that state to our desired output. The best analogy is to imagine throwing a stone, which is our input, into a pond, which is our reservoir. The pond's physics are fixed. You don't train the water. But by observing the complex pattern of ripples on the surface, you can learn to infer what kind of stone was thrown and when. In an ESN, we don't train the reservoir. We only train the readout layer to learn how to interpret the ripples. Before we dive into the code for a single echo state network, Let's first understand the powerful, high-level architecture we'll be using in this project, the multi-scale echo state network. So why would we need more than one reservoir? Think about how you perceive the world. To make a good decision, you need to process information at different speeds or timescales. For the cart pole problem, the agent needs to react to very fast changes, like a sudden wobble of the pole. But it also needs to be aware of slower moving trends, like the cart consistently drifting too far to one side of the track. A single reservoir might be good at one of these, but not the other. A multi-scale ESN solves this by creating a team of specialists. Instead of one giant reservoir, we create several smaller independent reservoirs. Each reservoir in our team is configured with different properties, allowing it to specialize in capturing dynamics at a specific timescale. Let's look at the parameters we'll use in our code to define this team. First, reservoir dimensions. We are creating 3 reservoirs and we're giving them different sizes, 300, 400, and 500 neurons. Giving them different sizes can provide varying levels of complexity and capacity for the patterns they can represent. Next, spectral radii and sparsities. For this particular experiment, we're keeping these consistent across all 3 reservoirs to isolate the effect of the other parameters. They are all set to stable, well-established values. Now, for the most important parameter in our multi-scale design, leaky rates. This is how we create our specialists. We're giving each reservoir a different leaky rate, 0.2, 0.3, and 0.4. The reservoir with a high leaky rate of 0.4 will be our short-term memory expert. Its internal state will be heavily influenced by the most recent input, making it highly reactive and great at capturing fast-changing details. The reservoir with a low leaky rate will be our long-term strategist. Its neurons are more stubborn. They hold on to their previous state more strongly. This allows it to smooth out noisy inputs and integrate information over a much longer period, helping it recognize slow-moving trends. The one in the middle, at 0.3, provides a balanced perspective. The final step is to take the rich state vectors from all 3 of these specialist reservoirs and simply concatenate them together into one large superstate vector. This combined vector is then fed to our single trainable readout layer. By doing this, we are giving our decision maker the richest possible view of the world. It gets to hear from the short-term specialist, the long-term strategist, and the balanced expert all at once before making its final move. All right, let's dive into the code and build our echo state network class piece by piece. We'll start with the constructor, the init method. The first thing we do after calling super.init and storing some hyperparameters is to create our input weights, which we'll call win. This is the first component from our diagram. Its job is to take the input vector, which for cart pole has a dimension of 4, and project it into the much higher dimensional space of our reservoir, which might have 300, 400, or 500 neurons. We initialize this weight matrix with random values drawn from a uniform distribution. The torch.rand gives us values between 0 and 1, subtracting 0.5 centers them around 0, and multiplying by 2 scales them to be between -1 and 1. This is a standard way to create initial random weights. Now notice this line, self-register buffer. This is very important. In PyTorch, a parameter is a tensor that the optimizer knows it needs to update during training. A buffer, on the other hand, is a tensor that is part of the model state, but is not considered a trainable parameter. By registering win as a buffer, we are telling PyTorch, this is part of my model, so please move it to the GPU along with everything else, but do not try to calculate gradients for it. This is central to the ESN philosophy of keeping the input and reservoir connections fixed. Okay, we have our input weights. Now for the most interesting part, creating the recurrent reservoir weights, W. This matrix defines how the neurons inside our reservoir are connected to each other. The first step is to introduce sparsity. Why do we do this? A fully connected recurrent network can sometimes have dynamics that are too rigid or chaotic. By making the network sparse, meaning most neurons are not connected to most other neurons, we can encourage richer and more stable patterns to form. It's like having many smaller independent pathways for information to flow and interact. So, how do we do it in code? It's a simple three-step process. First, we create a dense square matrix W of the desired reservoir size with random values centered around 0. Second, we create a Boolean mask of the exact same size. We generate another matrix of random numbers between 0 and 1, and we check where these numbers are greater than our sparsity hyperparameter. So if sparsity is 0.5, this mask will be true for roughly half of its elements. Third, we use this mask to index into our weight matrix W and set those elements to 0. We've effectively just pruned a huge number of connections, leaving us with a sparse, random recurrent network. The next crucial step is to make sure this network is stable. This next piece of code is the most mathematically important part of creating our ESN. It's called spectral radius scaling, and its job is to ensure our reservoir has the echo state property. In simple terms, this property means that the influence of a past input should gradually fade away over time, but not too quickly. If the echoes die too fast, the network has no memory. If the echoes explode and become chaotic, the network state is useless. We need to find that perfect balance. The key to this balance is the spectral radius of our weight matrix W, which is defined as its largest absolute eigenvalue. For a stable system, this value needs to be less than 1. So our goal is to take our random sparse matrix W and scale it down so that its spectral radius is exactly equal to our desired value spectral radius hyperparameter, which is typically a value like 0.9. Calculating the exact eigenvalues is slow, so instead we use a fast and effective approximation method called power iteration. We start with a random vector EIG. Then we repeatedly multiply our matrix W by this vector. At each step, the vector EIG gets more and more aligned with the principal eigenvector of W. We normalize it at each step to prevent its magnitude from exploding. After about 50 iterations, the norm or length of this vector becomes a very good approximation of the largest eigenvalue. Once we have this maxig, the final step is simple. We just scale our entire weight matrix W by our target spectral radius divided by the max EIG we just found. This guarantees that our new scale W has exactly the spectral radius we want, ensuring our reservoir is stable and ready to produce useful echoes. We then register this final W as a buffer. Now that we've meticulously constructed our ESN in the init method, let's look at the forward pass. This is what happens at every single time step of the simulation. First, we make sure our input x is a flat vector. Then we come to the single most important equation in our network, the state update equation. This is what makes it a leaky integrating ESN. Let's break it down. The torch.tanh part is the standard RNN update. We take the current input x multiplied by the input weights, add it to the previous reservoir state, multiplied by the recurrent weights, and pass it through a tanh activation. This gives us the new potential state, but we don't just replace the old state with the new one. Instead, we perform a weighted average. We take 1 minus leaky rate times the old state, and add leaky rate times the new potential state. The leaky rate is a hyperparameter that controls how fast the reservoir state changes. A small leaky rate means the neurons are stubborn and hold on to their old state for longer, giving the network a longer memory. A large leaky rate makes the neurons update more quickly in response to new inputs. Finally, we normalize the resulting state vector by its norm. This is an extra trick to ensure the activations don't grow too large over time, which further improves the stability of our system. The output of this module is not a prediction, but the rich, high-dimensional state of the reservoir itself. Now, let's see how simple the code for the multi-scale ESN is, now that we've done all the hard work in our base EcoState network class. This multi-scale ESN class is essentially a manager for our team of reservoirs. In the init method, instead of single hyperparameters, it takes lists. A list of reservoir, DIMs, spectral, radii, sparsities, and leaky rates. It then uses a list comprehension to create multiple EcoState network instances, one for each set of parameters, and stores them in an NN module list. Then it creates our single trainable readout layer. Notice its input size, sum of reservoir dimensions. If we have reservoirs of size 300, 400, and 500, the input to this readout layer will be 1200. It's going to see the combined state of every reservoir simultaneously. The forward pass is just as elegant. It passes the input X to each reservoir in the list, collecting their individual state vectors. It then uses torch cat to concatenate these state vectors into one single large superstates vector. This combined vector, which contains information at multiple timescales, is then passed to our trainable readout layer to produce the final output scores. With our complex multi-scale ESN brain fully designed, the rest of the setup is standard reinforcement learning practice. First, we have the policy network class. This is an extremely simple but necessary wrapper. Its only job is to take the raw output scores or logits from our ESN and pass them through a softmax function. This converts the scores into a valid probability distribution where each value is between 0 and 1 and they all sum to 1. This gives us the probability of taking each possible action. Now, in our train function, we begin by setting up our experiment. We create our cart pole environment. We then define the lists of hyperparameters for our three different reservoirs. Notice that the leaky rates are different, 0.2, 0.3, and 0.4. This is how we're creating reservoirs that capture information at different timescales. We then instantiate our multi-scale ESN with these parameters and wrap it inside our policy network. Finally, we create our Atom optimizer. And again, it's crucial to remember that when we call policy.parameters, the only trainable weights it will find are those in the single readout layer of our multi-scale ESN. The vast majority of our network's parameters are fixed, which is why this approach is so efficient. Now we're inside the main training for loop, which iterates through episodes. Each episode is one full attempt by our agent to balance the pole. Inside the while not done loop, the agent lives its life step by step until the pole falls over. At each step, it performs a sequence of actions. First, it passes the current state of the environment to our policy network to get action probabilities. Second, it creates a categorical probability distribution from these probabilities and samples an action. This is a key concept in policy-based reinforcement learning. Instead of always choosing the action with the highest probability, which would be exploiting its current knowledge, sampling allows the agent to explore by occasionally trying out less likely actions. This is how it discovers new and better strategies. Third, we calculate and store the logprob or log probability of the action we just chose. We need this later for the policy gradient update. Fourth, we execute that action in the environment, and it gives us back the next state, the reward for that step, and whether the episode is done. Finally, we store the reward we received in our rewards list and update our state variable for the next iteration of the loop. We're essentially just collecting data during this phase, a history of actions taken, their log probabilities, and the rewards received. Once the episode is over, it's time for our agent to learn. We use a classic policy gradient algorithm called reinforce. The first thing we need to do is figure out how good each step of the episode actually was. Just looking at the immediate reward of +1 isn't enough. We want to know which actions led to long-term success. To do this, we calculate the discounted return for each step. We loop through the rewards list backwards. For each step, we define its return R as its immediate reward R plus gamma times the return of the next step. This gamma is a discount factor, usually around 0.99, which makes future rewards slightly less valuable than immediate ones. This process gives us a much better estimate of the true long-term value of each action we took. Next, we standardize these returns by subtracting their mean and dividing by their standard deviation. This is a crucial trick that helps stabilize training by keeping the values in a predictable range. Now we calculate our loss. The formula is the heart of the reinforce algorithm. For each step, we take the log prob of the action we took and multiply it by the standardized return for that step. The negative sign is there because optimizers work by minimizing loss. By minimizing this value, we are effectively pushing up the probability of actions that led to high returns and pushing down the probability of actions that led to low returns. Finally, we perform our standard PyTorch optimization. We zero the gradients, backpropagate our loss, and step the optimizer. This sends the learning signal back and updates the only trainable part of our model, the readout layer. So let's take a moment to recap the advanced and fascinating system we've built today. We didn't just build a neural network. We built an echo state network from the ground up. We went through the detailed theory and code for creating a sparse, random reservoir and ensuring its stability through spectral radius scaling. We then took it a step further, creating a multi-scale architecture by combining a team of ESNs, each tuned to a different time scale using a different leaky rate. This allowed our agent to process both long-term trends and short-term events simultaneously. We embedded this complex brain into a reinforcement learning agent and successfully trained it using the reinforced policy gradient algorithm, teaching its simple readout layer how to interpret the rich dynamics of the reservoirs to solve the cart pole problem. The result is a highly efficient recurrent model that demonstrates a powerful alternative to traditional RNNs. I highly encourage you to take this code and experiment. See for yourself how changing the reservoir sizes or the leaky rates affects the agent's learning speed and final performance. Try applying this architecture to a more challenging environment. This is a fantastic foundation for exploring the world of reservoir computing. Thank you so much for joining me for this deep dive. If you enjoyed it and learned something valuable, please give the video a like and subscribe for more advanced AI tutorials. Happy coding! Welcome to the BrainOmega channel. In today's session, we're diving into a crucial topic in the world of artificial intelligence. The main goal of this tutorial is to take a significant step forward toward understanding and implementing LLM alignment within our community. So what exactly do we mean when we talk about alignment in large language models? At its core, alignment isn't just about making an AI smarter, it's about making it wiser and more responsible. As you can see on the slide, alignment is the dedicated process of training and fine-tuning an LLM so that its actions and responses are consistently in sync with human values and intentions. The ultimate objective is to sculpt these powerful models into partners that are not only helpful but also fundamentally safe to interact with. The diagram on the right beautifully illustrates this. It's a continuous cycle. We provide feedback which helps refine the large language model. This refinement leads to what we call aligned positive outcomes, outputs that are beneficial and in line with our expectations. This process is repeated, creating a constant loop of improvement. To achieve this, the entire concept of alignment is built upon three foundational pillars, being helpful, honest, and harmless. First, helpful. This means the AI must go beyond just processing words. It needs to accurately grasp the user's true goal and genuinely attempt to meet that need. It's about being a useful and effective tool. Second, honest. An aligned LLM must be a source of truth. It should provide factually correct information and crucially have the integrity to admit when it doesn't know something rather than fabricating an answer. This pillar is all about building trust. And third, harmless. This is the ethical safeguard. The model must be explicitly designed to steer clear of generating content that is dangerous, biased, unethical, or otherwise harmful. It's our commitment to ensuring AI contributes positively to the world. By focusing on these three pillars, we can guide the development of large language models that are not just powerful, but also principled and beneficial for everyone. For those of you who want to dive deeper, the source code of this tutorial and the project is accessible in our GitHub repository. You can have access to the link in the description of this video. Now that we understand what alignment is, let's explore what it gives us and what its limitations are. This slide tackles a crucial distinction. Alignment is a powerful path toward building trust in AI, but it's not a magic bullet for achieving full explainability. First, let's focus on the strong link between alignment and trustworthiness. Think about anyone or anything you trust in your daily life, perhaps a skilled pilot or a seasoned doctor. You trust them because their actions are reliable, predictable, and consistently lead to positive outcomes. It's the exact same principle with LLMs. By meticulously aligning a model to be helpful, honest, and harmless, we ensure its behavior is consistent and acts in the user's best interest. As the Venn diagram illustrates, an aligned LLM and a trustworthy LLM are deeply interconnected concepts. Alignment is the how, trustworthiness is the result. However, the story changes when we compare alignment to explainability. Here, the link is much weaker, and this is a critical concept to grasp. Alignment is primarily concerned with the output, the what. It asks, is the model's final answer correct, safe, and useful? We are validating the quality and safety of the end product. Explainability, on the other hand, digs into the process, the why. It seeks to answer how exactly did the model navigate its billions of parameters to generate that specific output. This brings us to the black box dilemma, perfectly shown in the second diagram. We can have a model that is perfectly aligned. It gives us a validated, correct, and safe output every time. Yet the internal decision-making process that produced it can remain opaque. We can confirm what it concluded, but we can't always trace the precise path of why. So, the key takeaway is this. Alignment is our most effective tool for creating reliable, predictable, and safe AI that we can fundamentally trust. It solves the problem of behavior. But we should see it as distinct from the separate, ongoing scientific challenge of making these incredibly complex systems completely transparent. So, where is the field of alignment heading? This slide gives us a glimpse into the future, moving beyond the basics to explore the core philosophies and advanced techniques that are defining the next generation of AI. As the diagram illustrates, the path forward involves integrating three powerful and sophisticated approaches to build a more deeply and reliably aligned AI. Let's look at each of these pillars. First, we have AI-driven preference labeling. One of the biggest challenges in alignment is the sheer scale of human feedback required. It's incredibly time-consuming and costly. This technique is the solution. We are essentially training one AI model to understand human values and preferences so well that it can automate the process of labeling data for other models. Think of it as creating an AI supervisor that can apply human-like judgment at machine speed, breaking the bottleneck of manual work. Next, we have constitutional methods. This is a profound shift in philosophy. Instead of just telling an AI what not to do from the outside, we embed a set of core principles, a constitution, directly within its own operational logic. This gives the AI a framework for self-correction. It can review its own response, check it against principles like be helpful and harmless, and then revise it before it ever reaches the user. It's about building models with an internal moral compass. Finally, let's talk about advanced reasoning curricula. This is about teaching an AI how to think, not just what to know. Rather than just exposing a model to vast amounts of data, we create a structured training program, much like a school curriculum for a person. This curriculum is specifically designed to enhance the AI's ability to perform complex, multi-step reasoning and to follow a logical chain of thought. It's the difference between memorizing facts and developing true critical thinking skills. Ultimately, these three frontiers are converging. By automating feedback at scale, instilling principles for self-governance, and actively teaching complex reasoning, we are building the foundation for AI that is more capable, robust, and fundamentally aligned with human values. So, how do we actually implement alignment? Let's dive into the most common and effective method used today, RLHF, which stands for Reinforcement Learning from Human Feedback. As the diagram here illustrates, it's a dynamic, multi-stage process that creates a powerful feedback loop between human trainers and the AI model. The entire process begins with step 1, supervised fine-tuning or SFT. Think of this as the model's foundational education. We take a massive pre-trained model and give it its first taste of what we want it to be. We do this by training it on a high-quality human-crafted dataset of ideal conversations. This is like giving a student a textbook filled with perfect examples to learn from. This initial step teaches the model the basic style, tone, and safety protocols we expect. Step 2 is about building a judge. This is where we train the reward model. We take our model from the first step and have it generate several different responses to a variety of prompts. Then, human reviewers look at these responses and rank them from best to worst. This data, this collection of human preferences, is then used to train a completely separate model. The sole purpose of this reward model is to learn to predict which kinds of answers humans will prefer. It becomes an automated judge of quality. Finally, we reach step 3, reinforcement learning optimization. This is the most dynamic phase. The main LLM now operates in a live training environment. It generates a response, and our reward model, the AI judge we just built, immediately gives that response a score. This score acts as a reward signal in a reinforcement learning loop. Using a common algorithm like PPO, the model continuously adjusts its own internal strategy to try and maximize the rewards it gets from the judge. It's essentially a cycle of trial and error at a massive scale, where the model learns to consistently produce outputs that it knows will be scored highly by the human-calibrated reward model. So, in short, we first show it what good looks like, then we build a judge that understands our preferences, and finally, the model practices in front of that judge to perfect its behavior. This sophisticated three-step process is the engine behind today's most capable and aligned LLMs. Imagine you're a music producer trying to get the perfect vocal take. The old way is complicated. You first hire a panel of music critics to write a detailed scoring rubric for what good singing is. Then you use that complex rubric to coach the singer, take by take. It's slow, expensive, and often unstable. What if you could just sit with the singer, play them two different melodies, and say, "I prefer this one"? You just provide a simple preference. The singer learns directly from your choice, gradually steering their performance toward what you like. That, in a nutshell, is the breakthrough of direct preference optimization, or DPO. It's a powerful and elegant technique that scraps the complex machinery of traditional methods and teaches language models to be more helpful, safe, and aligned, directly from simple human or AI feedback. Before DPO, the gold standard was reinforcement learning from human feedback, or RLHF. As the name suggests, it's a multi-stage process. First, you train a separate reward model. You show it thousands of pairs of model responses and ask humans which one they prefer. The reward model learns to predict which response will get a higher score. Second, you use that reward model as a judge in a complex reinforcement learning loop. Your language model generates text, the reward model scores it, and you use algorithms like PPO to nudge the language model's policy toward generating higher scoring text. This process works, but it's a beast to manage. It involves training two massive models. It's computationally expensive because you're constantly sampling from the policy, and it's notoriously unstable and sensitive to hyperparameters. DPO's authors asked a brilliant question. Can we skip the separate reward model and the RL loop entirely? Their key insight was this. Your language model is secretly a reward model. Through a clever mathematical derivation, they showed that any optimal policy trained with RLHF has a direct fixed relationship with its underlying reward function. This means you can rephrase the entire optimization problem. Instead of training a reward model and then training a policy to match it, DPO defines the loss directly in terms of the policy itself. It collapses two complex stages into one simple, stable step. So, how does it do this? Let's look at the DPO loss function. It might look intimidating, but the idea is incredibly intuitive. For every training example, you have a prompt, a preferred response, Y sub W, and a rejected response, Y sub L. The DPO objective is to maximize the likelihood of the preferred responses over the rejected ones. Let's break it down. The core idea. At its heart, it looks at the log probabilities your model, pi theta, assigns to the winning and losing responses. The goal is to make the winner's probability go up and the loser's go down. The reference model, PyRef. You don't want the model to stray too far from its original stable knowledge base. The reference model, usually your initial supervised fine-tuned SFT model, acts as an anchor. DPO penalizes the policy for deviating too much from this reference, which prevents the model from forgetting its core capabilities or collapsing into repetitive outputs. The beta hyperparameter. This is your main tuning knob. It controls the strength of that anchor. A low beta keeps the model very close to the reference policy, leading to more conservative updates. A high beta allows the model to chase the preferences more aggressively, but risks instability. Think of it as the stretchiness of a leash. The sigmoid weight. This is the most elegant part. The entire term is wrapped in a logistic sigmoid function. This acts as a dynamic, intelligent weight. When the model already assigns a much higher probability to the winning response than the losing one, this weight is small. But when the model is wrong, when it thinks the losing response is better, the weight becomes large. This forces the model to focus its learning effort on the examples it's getting wrong, making training incredibly efficient and stable. In short, DPO increases the relative log probability of preferred responses, weighted by how incorrectly the model currently ranks them. The beauty of DPO is its simplicity. The practical pipeline is just two steps. Data collection. Start with a supervised fine-tuned SFT model. For a set of prompts, generate two responses. Have a human labeler or a more powerful AI. Choose the preferred one. This creates your preference dataset. If you're using a public dataset, this is already done for you. Fine-tuning. Optimize your SFT model using the DPO loss function. That's it. No separate reward model, no complex RL sampling loops. The paper even provides a PyTorch implementation that's just a handful of lines long. And if you don't have an SFT model to start with, the paper suggests a simple hack. Just fine-tune a base model on only the winning responses from your preference dataset to create a proxy SFT model before you begin DPO. So, does it work? The paper's experiments show a resounding yes. More efficient. On a controlled sentiment generation task, DPO achieved a better reward KL trade-off than PPO, even when PPO had access to the true ground truth reward function. This means for any given level of deviation from the original model, DPO gets you a higher reward. Higher quality. In summarization and single-turn dialogue, DPO consistently matched or outperformed strong RLHF baselines. For instance, in summarization, DPO achieved a 61% win rate against reference summaries, beating PPO's best performance of 57%. It was also the only computationally feasible method that significantly improved upon the chosen responses in the Anthropic dialogue dataset. More stable, the approach is far less sensitive to hyperparameters and sampling temperature than PPO, which can see its performance collapse under different settings. Direct Preference Optimization, or DPO, is a revolutionary, more direct approach, and today we're going to implement it from scratch to fine-tune the powerful Llama 3 model. In this video, we'll cover the entire pipeline. We have already explained the theory of DPO, so we'll dive into the code using cutting-edge libraries like Hugging Face's TRL and PEFT. We'll use techniques like LoRa for memory-efficient training and quantization to make this all possible on consumer-grade hardware. This is a complete end-to-end guide. By the end, you'll have a deep, practical understanding of how to take a powerful base model and align it with your own data and preferences. Let's get started. Before we jump into the code, let's quickly understand the three core technologies that make this project possible. First, Direct Preference Optimization, or DPO. Traditionally, to align a model with human preferences, a complex process called reinforcement learning with human feedback, or RLHF, was used. DPO is a newer, more elegant solution. It works with a simple but powerful type of data set, one that contains a prompt, a chosen or preferred response, and a rejected or less preferred response. The DPO loss function then directly optimizes the model to make the chosen responses more likely and the rejected responses less likely. It's more stable and often more effective than RLHF. Second, parameter-efficient fine-tuning, or PEFT, using a technique called LoRa. Fine-tuning a model with billions of parameters would require a massive amount of GPU memory because you need to store the gradients and optimizer states for every single weight. LoRa is a brilliant solution. We freeze the entire pre-trained model. All its billions of weights remain untouched. Then we inject tiny trainable matrices, called LoRa adapters, into the model's layers. We only train these small adapters, which represent a tiny fraction of the total parameters. This dramatically reduces the memory requirements, making fine-tuning possible on a single consumer GPU. Third, quantization. Even just loading a model like Llama 3.8b can take over 16 gigabytes of VRAM. To solve this, we use quantization. We load the model's weights using 8-bit integers instead of the standard 32-bit or 16-bit floating point numbers. This can cut the memory needed to load the model by 50 to 75%, making it feasible to run on more accessible hardware. By combining these three techniques, DPO for effective alignment, LoRa for memory-efficient training, and quantization for accessible model loading, we create a powerful and practical fine-tuning pipeline. So, you want to run this powerful AI model, but maybe your computer isn't quite up to the task? Don't worry at all. We can easily run this in the cloud using Google Colab Pro. The very first thing we need to do is give our project some serious power. Let's go up to the Runtime menu and click on Change Runtime Type. You'll see a pop-up window. The magic happens in the hardware accelerator. Instead of the standard GPU, if you have Colab Pro, you can select the powerful 800 GPU. This is a game changer for speed and will make running this model a breeze. Okay, with our 800 selected, let's get the software ready. We'll run our pip install commands to load all the essential Python libraries for this project. Next up, let's grab the code itself. We'll use a quick git clone command to download the entire project from GitHub. And just like that, we're ready to go. We'll move into the new folder and run the main script. And there it is. The model is running and generating its answer to our prompt. It's that simple to get started, even without your own powerful hardware. Let's start our code journey with dataprocessing.py. This script has one simple but crucial job: to prepare our dataset for the DPO trainer. The DPO trainer, which we'll see later, requires each example in our dataset to be a dictionary containing 3 specific keys: prompt, chosen, and rejected. Our format example function does exactly this. Let's walk through it. It takes a single example from our raw dataset and the tokenizer. First, it constructs the messages list that represents the start of the conversation. It checks if the example has a system prompt, and if so, adds it. Then it adds the user's question. Second, it uses a very handy function, tokenizer.applyChatTemplate. Every chat model has a specific format it was trained on, with special tokens to denote the start and end of turns. This function takes our list of messages and correctly formats it into a single string, prompt, complete with all the necessary special tokens. We set add_generation_prompt equals true to ensure it adds the token that signals to the model that it's the assistant's turn to speak. Third, it takes the chosen and rejected responses from the dataset and appends the tokenizer's end of sentence token to each one. This signals the end of a complete generation. Finally, it returns a dictionary with our 3 required keys, perfectly formatted for our DPO trainer. This function will be applied to every single example in our dataset. Now let's move to the main event, training.py. This script orchestrates the entire fine-tuning process. We start by importing all the necessary libraries. We have Torch for our core deep learning framework, datasets and transformers from Hugging Face for loading our data and models, PEFT for our parameter-efficient fine-tuning, and TARL, which contains our DPO trainer. Inside our train model function, the first step is to set up our tokenizer. We load it from the Hugging Face hub using autotokenizer.from_pretrained, pointing it to our base model. Then we configure it. We set the pet token to be the same as the EOS token, end of sentence token. This is a common practice for autoregressive models. We also set padding side equals left. This is a subtle but very important detail for causal language models. It ensures that when we batch multiple sequences of different lengths together, the padding is added to the left side so the final unpadded token of every sequence aligns on the right. This is crucial for efficient next token prediction. Finally, we explicitly define a chat template. While many models have this built in, setting it ourselves ensures maximum compatibility. This template uses a Jinja-like syntax to define exactly how a list of messages should be formatted into a string, using special tokens like imstart and imend to delineate turns. This guarantees our input is formatted perfectly. With our tokenizer ready, the next step is to load our data and our base model. First, we use load dataset from the datasets library to download our preference dataset directly from the Hugging Face hub. We're using the Intel Orca DPO pairs dataset, which is perfect for this task. Then, we use the .map method to apply our format example function to every single example in the dataset. This transforms our raw dataset into the prompt, chosen, rejected format that the DPO trainer needs. Next, we load our base model, Unsloth Llama 3.8b. This is a special version of Llama 3 optimized for faster training. Let's look at the arguments to from pre-trained. Device Map Auto is a fantastic feature that will automatically distribute the model's layers across multiple GPUs if you have them, or load it onto a single GPU or the CPU. We also specify torch dtype torch bfloat 16. This enables mixed precision training, which uses a more efficient data type for calculations, speeding up training and reducing memory usage. Finally, and this is a critical step for combining quantization with LoRa, we call prepare model for KBit-A training. This function from the PEFT library does some important housekeeping under the hood, like correctly casting certain layers to ensure that gradients can flow properly through a quantized model during training. This makes our efficient fine-tuning possible. Okay, we have our massive Llama 3 model loaded in memory, but it's frozen. We're not going to train its original weights. Instead, we're going to use the LoRa technique. First, we define our LoRa config. This object holds all the settings for our LoRa adapters. Let's break down the key parameters. R is the rank of the LoRa matrices. This is the most important hyperparameter. A smaller R, like 8 or 16, means smaller adapter matrices and fewer trainable parameters, leading to faster training but potentially less expressive power. A larger R, like 64, gives the model more capacity to learn, but increases the memory requirements. LoRa alpha is a scaling factor that is often set to be the same as R, and LoRa dropout applies dropout regularization specifically to the LoRa layers to help prevent overfitting. Once we have our configuration object, we call the magic function getPeftModel. This function takes our base model and the LoRa CFG, and it goes through the model's architecture, finds the target layers, usually the attention layers, and injects our small trainable LoRa adapter matrices next to them. It also handles freezing all the original weights. After this line, our model object is now a PEFT model, ready for efficient training. Now we're at the final setup step before training, configuring the DPO trainer. This is a fantastic high-level trainer class from the Hugging Face TRL, or Transformer Reinforcement Learning Library. It abstracts away all the complex math of the DPO loss function. First, we create a DPO config object. This holds all the training hyperparameters. Let's highlight a couple of key ones. Gradient accumulation steps is a crucial technique for training with small batch sizes. It allows us to compute gradients over several small batches and only update the model weights once, effectively simulating a much larger batch size without using more memory. Gradient checkpointing is another memory-saving trick that trades a little bit of extra computation time for a significant reduction in memory usage. We also set our learning rate, scheduler, and other standard training parameters here. Once our config object is ready, we instantiate the DPO trainer. We pass it our LoRa adapted model, our DPO-ish CFG, our processed dataset, and our tokenizer. One very cool feature of the DPO trainer is that we can set ref model equals none. In DPO, you need a reference copy of the original frozen model to calculate the loss. By setting this to none, the trainer is smart enough to automatically create and manage this reference copy for us, which simplifies our code a lot. After all that careful setup, the actual training process is beautifully simple, thanks to the Hugging Face Trainer API. We simply call trainer.train. This one line kicks off the entire fine-tuning process. The trainer will handle the training loop, moving data to the GPU, calculating the DPO loss, performing backpropagation, updating the LoRa weights with the optimizer, and adjusting the learning rate with the scheduler. It will also handle all the logging and progress bars for us. It's an incredibly powerful abstraction. Once the training is complete, we need to save our work. We call model.save pre-trained, open parenthesis, output directory, close parenthesis. Because our model is a PEFT model, this command is smart. It knows not to save the entire multi-billion parameter Llama model. Instead, it only saves the tiny LoRa adapter weights that we actually trained. This is why our final output directory will be very small, maybe only a few megabytes instead of many gigabytes. We also save the tokenizer to the same directory. This is good practice as it bundles the exact tokenizer configuration with the trained adapters, making it easy to load everything together for inference later. Now that we've fine-tuned our model, let's see how to use it in Inference.py. The load model for chat function handles getting our model ready for a conversation. First, we load our tokenizer from the base model and configure it with the exact same chat template and padding settings we used during training. This consistency is crucial. Next comes the model loading, which is a two-step process. First, we load the original massive frozen base model, just like we did before training. Second, we use PEFT_model from pre-trained. This function takes the base model and the path to our saved adapter path directory, and it loads our small, fine-tuned LoRa weights and merges them into the base model's architecture. We now have a single model object that has the full power of a Llama 3 combined with the specific alignment we taught it during DPO training. Finally, we switch the model into evaluation mode with model.eval. This turns off things like dropout. We also set use_cache equals true, which is an optimization that allows the model to reuse computations for past tokens, significantly speeding up the generation of long responses. With our model loaded, the chat function handles the process of generating a single response. First, just like in our data processing step, we use tokenizer apply chat template to format our system message and user message into a single, correctly formatted prompt string. Next, we use a very convenient high-level tool from the Transformers library, the pipeline. A pipeline abstracts away a lot of the manual tokenization and decoding steps. We create a text generation pipeline and give it our fine-tuned model and tokenizer. Finally, we call our generator with the prompt. We pass in several parameters to control the generation process. DoSample equals true tells the model to use sampling instead of just greedily picking the most likely next token, which makes the output more creative. Temperature controls the randomness. A higher value means more random. A lower value means more deterministic. And TopWP enables nucleus sampling, another advanced sampling technique. The pipeline handles the rest, and we simply return the generated text from the output. Finally, we have main.py, our project's entry point. This script serves as a command line interface, or CLI, that lets us control our entire application from the terminal. We use Python's built-in argparse library to do this. First, we create our parser. Then we add all the arguments we want to be able to control. The most important one is mode, which is a required choice between train and chat. This single argument will determine what our script does. We also add arguments for things like the base model name, the dataset, and the user message for chat mode. After parsing the arguments provided by the user on the command line, we have a simple if-else block that acts as a router. If the user ran the script with --mode train, we call our train model function from training.py, passing in the relevant arguments to start the fine-tuning process. If the user ran it with --mode chat, we call our load model for chat and chat functions from Inference. Passing in the user's message to generate and print a response. This simple, clean structure allows us to manage both training and inference from a single, easy-to-use command. So let's take a moment to recap the powerful and modern fine-tuning pipeline we've just built. We've gone deep into direct preference optimization, learning how to use preference pairs to effectively align a language model. We've mastered an incredibly efficient workflow using quantization to load a massive model into memory and then using PEFT with LoRa to fine-tune it with minimal resources. We've structured this all into a complete application with clean, modular code for data processing, training, and inference. And finally, we've tied it all together with a flexible command line interface. You now have the knowledge and the code to fine-tune state-of-the-art language models on your own custom data. I highly encourage you to experiment. Find a different preference dataset on the Hugging Face Hub and try training with it. Tweak the LoRa rank R and see how it affects the model's performance. As a great next step, you could even take the Inference PyScript and wrap it in a Gradio UI to create a shareable web demo of your custom-tuned model. Thank you so much for joining me on this deep dive. If you learned something valuable today, please give the video a like and subscribe for more tutorials on cutting-edge AI techniques. Happy fine-tuning! Hello everyone! In this tutorial and hands-on, we implement advanced generative AI based on Wasserstein GANs. Today, we're going to explore some of the fundamental challenges you'll encounter when training standard generative adversarial networks, or GANs. While GANs are incredibly powerful for generating new data, they are notoriously difficult to train. Let's dive into the most common problems. First up is a problem called mode collapse. In simple terms, this is when the generator gets lazy. It finds one or a very small number of samples that are really effective at fooling the discriminator and then produces nothing else. Instead of learning the entire distribution of the training data, for example, all the different breeds and poses of a dog, it only learns to generate, say, a single type of Chihuahua. You can feed the generator different random inputs, but it will still produce the same or very similar outputs. It's like an art forger who can create a perfect replica of the Mona Lisa, but has no creativity and can't paint anything else. The generator has collapsed to a single mode or a few modes of the data. The next major issue is unstable training. The core idea of a GAN is that the generator and discriminator compete and improve together, eventually reaching an equilibrium. But often this doesn't happen. Instead, they can get locked into a cycle where they just undermine each other. For instance, the generator might find a weakness in the discriminator and exploit it. The discriminator then learns to patch this weakness, but in doing so, it might change so much that the generator's previous progress is completely undone. The result is that their loss values, which you see on a graph, will swing up and down wildly and never converge. The quality of your generated images can get better, then worse, then better again, without ever reaching a stable high-quality state. A related problem is vanishing and flat gradients. This typically happens when the discriminator becomes too good too early in the training process. It gets so skilled at telling real from fake that its confidence level is always near 100%. To understand this, think of the gradient as the slope of the loss function. This slope tells the generator which direction to go to get better. When the discriminator is too confident, this slope becomes very close to zero. It becomes a flat gradient. This means the feedback signal sent to the generator vanishes or shrinks to almost nothing. The generator gets no useful information about how to improve. It's like a harsh critic who just says, "Your work is terrible," but gives no constructive feedback. The generator's loss stalls, it stops learning, and you're left with a poor generator that can't get any better. This brings us to a crucial point about GANs. The loss values don't mean what you think they mean. In a typical deep learning model, you want to see the loss go down, as that signals the model is improving. With GANs, this is not the case. The generator and discriminator losses simply reflect how each player is doing in their game against the other at that moment. A low generator loss could mean the images are great, or it could just mean the discriminator is currently bad at its job. You can have a GAN that produces beautiful, high-quality images, but its loss values might be high or oscillating. Therefore, you can't just look at the loss curve to know if your model is working. You have to constantly look at the images it's generating. Finally, even if your GAN seems to be working, it's hard to prove it objectively. How do you put a number on creativity or realism? There's no simple metric like accuracy to tell you if you have a good GAN. Researchers have developed sophisticated metrics like the Fréchet inception distance, or FID, which compares the statistics of generated images to real ones, but these aren't perfect. Ultimately, evaluating a GAN still requires a combination of these metrics and careful visual inspection by a human to judge the quality and diversity of the output. It's as much an art as it is a science. Understanding these challenges is the first step to overcoming them and has led to the development of many newer, more stable GAN architectures. And remember, the whole code for this tutorial is available on our GitHub page. You can find the link in the description of this video. We've all faced the classic frustrations with standard GANs. The training is unstable, the generator suffers from mode collapse, and worst of all, the loss value doesn't really tell you if your images are getting any better. But what if there was a better way? Enter the Wasserstein GAN, or WGAN. Its power comes from a completely new loss function inspired by a clever idea called the Earth mover's distance. This forces us to change how our models think. We no longer have a simple discriminator that guesses real or fake. Instead, we have a critic that gives each image a score of how real it thinks it is. So how do we actually code this? It's surprisingly elegant. The entire Wasserstein loss can be implemented with a single simple formula. The loss is the negative mean of the label times the score. Let's see how this one rule works. Remember, our labels are now +1 for real and -1 for fake. When the critic sees a real image, the label is +1. The formula becomes -1 times score. To minimize this loss, the model has to make the score a large positive number. When the critic sees a fake image, the label is -1. The formula becomes -1 times score, which is just the score itself. To minimize this, the model must make the score a large negative number. This one simple equation naturally fuels the entire training process. Now let's see how it applies to our two players. This slide breaks down the entire process. At its heart, the WGAN is a tug-of-war between the critic and the generator. On one side, we have the critic. Think of it as a tough but fair art critic. Its goal is simple: make the scores for real and fake images as different as possible. It looks at a real image from our dataset and works to give it a very high score. Then it looks at a fake image from the generator and tries to give it a very low score. The critic's objective is to maximize this difference. The bigger the gap, the better it's doing its job. On the other side, we have the generator. Think of it as the artist, constantly working to improve and fool the critic. The generator's only goal is to create fakes that receive a high score. Its loss function is a very clever trick. The generator works to minimize the negative of the score the critic gives its images. And as we know, minimizing a negative value is the exact same thing as maximizing the positive value. So it's actively trying to get the highest possible score, directly fighting the critic's goal. This constant tug-of-war is the magic of WGANs. But for all of this elegant math to work, there's one final crucial rule we must follow. This rule is called one-Lipschitz continuity. It sounds complicated, but the idea is simple. The critic is not allowed to change its output too wildly. Its response landscape must be smooth. Think of it like a road. You can have hills and valleys, but no vertical cliffs. Mathematically, this means the magnitude of the critic's gradient must be at most 1. This constraint is essential because it's what allows our tug-of-war laws to properly estimate the true Earth mover's distance. So, how do we enforce this? There are two popular methods. The original paper used weight clipping, which is simple but can be problematic. The modern preferred method is the gradient penalty. Here, we add a new term to our critic's loss that directly encourages its gradient norm to stay close to 1. This approach is far more stable and is the standard for high-quality WGANs. So, what's the big payoff for all this? Well, this new loss structure, the tug-of-war combined with the Lipschitz constraint, solves our biggest problems directly. First, it fixes the vanishing gradient problem. This push and pull dynamic ensures the generator always receives a clear, useful signal to learn from. Second, the loss finally means something. In a WGAN, when you see the loss value improving, it generally correlates with better looking images. You can finally trust your metrics. And finally, all of this leads to far more stable training, which means less mode collapse and a much more diverse set of high-quality results. It's a more elegant and powerful way to train generative models, and it's the foundation we'll build on for even more advanced techniques. Again, welcome to a deep dive masterclass on one of the most important and influential advancements in the history of generative adversarial networks, the Wasserstein GAN with gradient penalty, or WGAN GPIF. You've ever tried to train a standard GAN, you might have run into problems like mode collapse or unstable training. The WGAN GP was a groundbreaking solution to many of these issues, enabling more stable training and leading to higher quality image generation. In this comprehensive tutorial, we are going to build a complete WGAN GP from absolute scratch using PyTorch. We will construct a deep convolutional generator and critic, prepare the high-resolution Celebi dataset, and then write the unique WGAN GP training loop, paying special attention to the crucial gradient penalty term. We'll also integrate professional tools like weights and biases for experiment tracking. This is a long-form, detailed guide where we will explain every file, every function, and every line of code. By the end, you will not only have a working GAN that can generate realistic faces, but you will also have a deep theoretical understanding of what makes WGANs so powerful. Let's get started. Let's begin our code walkthrough with the foundation of any well-organized machine learning project, the configuration file src-config.py. By defining all our important parameters in one place, we make our project clean, readable, and incredibly easy to experiment with. If we want to try a different learning rate or a larger batch size, we only need to change it here. Let's look at some key parameters. We have our learning rate and the beta values for the Adam optimizer. These specific values of 0.5 and 0.9 are often recommended for more stable GAN training. Now, here are two of the most important hyperparameters for our WGAN GP. First, critic cycles. This is set to 3, which means for every one update to our generator, we will update our critic 3 times. In the WGAN framework, it's critical that the critic is very well trained and provides accurate feedback to the generator, so we give it more training steps. Second, gradient penalty lambda. This is the weighting factor for our special gradient penalty loss term. A value of 10 is the standard recommended value from the original WGAN GP paper. We also define our model dimensions, like the z-dim, which is the size of the random noise vector we'll feed to the generator, and the base channel depths for our convolutional layers. Finally, we have our data and environment settings, including a convenient toggle to enable or disable logging with weights and biases. Next up is src/utils.py, our toolbox of essential helper functions. First, we have initialize weights. Just like in the basic GAN, this function applies a specific weight initialization scheme recommended in the DCGAN paper. This is a crucial step for helping our deep convolutional networks train stably from the beginning. It sets the weights of convolutional layers from a narrow normal distribution and initializes the weights of batch normalization layers. Second, show tensor images. This is our visualization function. It takes a batch of image tensors from our generator, which have pixel values between -1 and 1. It then denormalizes them back to the 0 to 1 range, arranges them into a beautiful grid, and displays them using matplotlib. Crucially, if we have weights and biases enabled, it also logs this grid of images directly to our experiment dashboard. This allows us to scroll through our training history and visually see how our generator's image quality improves over time. Finally, we have save checkpoint and load checkpoint. These functions are vital for long training runs. Save checkpoint takes our models and optimizers and saves their complete state to a file. Load checkpoint does the reverse. This allows us to stop and resume training at any time without losing our progress, which is absolutely essential when training can take many hours or even days. Now, let's look at how we handle our data in src/dataset.py. We're creating a custom PyTorch dataset class. This is the standard way to interface any custom data source with PyTorch's powerful data loader. A custom dataset class needs 3 special methods. First, the init constructor. When we create an instance of our dataset, this method runs. It takes the path to our image directory and a limit on the number of images to use. It then walks through that directory and creates a list, self.items, containing the full file path for every single JPEG image. Second, the len method. This one is simple. The data loader needs to know the total size of the dataset, and this method just returns the length of our self-items list. Third, and most importantly, the getItem method. The data loader calls this method whenever it needs to fetch a single item from the dataset. It gets passed an index IDX. Inside, we perform all our pre-processing for that one image. We open the image file using the PIL library. We resize it to our target image size, which is 128 by 128 pixels. We then convert it to a NumPy array and transpose it from the standard height by width by channel format to the channel by height by width format that PyTorch expects. Finally, we convert it to a PyTorch tensor and normalize the pixel values from the 0,255 integer range to a 0,1 floating point range. This pre-processed tensor is what gets returned. Now for the getSeleba data loader function. This is a fantastic automated script that handles the entire data pipeline for us. The first thing it does is call KaggleHub.datasetDownload. The KaggleHub library is a convenient tool that allows us to download datasets directly from Kaggle within our Python script. You'll need to have your Kaggle API key set up for this to work. This line downloads the entire Selebe dataset to a local cache directory. Next, since the downloaded directory structure can sometimes be complex, the script has some logic to automatically walk through the downloaded folders and find the exact path to the directory that contains our JPEG images. It also intelligently handles the case where the images might be inside a zip file. It checks for the existence of img-align-seleba.zip, and if it finds it, it uses Python's zip file library to automatically extract all the images for us. Once it has the final IMG path, it creates an instance of our custom dataset class that we just reviewed. It then wraps this dataset object in a PyTorch data loader. The data loader is what will actually feed the data to our model during training. It handles creating batches of the specified batch size, shuffling the data every epoch so our model sees the images in a different order, and using multiple CPU workers to load the data in the background, ensuring our GPU is always fed with data and never sitting idle. Let's move on to the exciting part, src/models.py, where we define our two competing networks. First up is the generator. Our generator is a deep convolutional GAN, or DC GAN. Its job is to take a flat, one-dimensional noise vector of size z-dim and skillfully upsample it into a three-channel 128 by 128 pixel image. It achieves this using a series of conv transpose 2D layers, which are essentially the reverse of a standard convolutional layer. They increase the spatial dimensions of their input. Let's trace the architecture. In the forward method, the first thing we do is take the input noise vector and reshape it into a four-dimensional tensor with a spatial size of 1 by 1. This is the format our convolutional layers expect. This 1 by 1 image is then passed to our sequential model. The first block upsamples it to a 4 by 4 feature map. Each subsequent make-gen block then uses a stride of 2 to exactly double the spatial dimensions, going from 4 by 4 to 8 by 8, then 16 by 16, all the way up to 64 by 64. Notice how, as the spatial size increases, we decrease the number of channels. The make-gen block helper function is a standard DC GAN block, a conv transpose 2D layer followed by a batch norm 2D for training stability, and a ReLU activation. The final layer is a conv transpose 2D that takes the 64 by 64 feature map, upsamples it to our target size of 128 by 128, and sets the number of output channels to 3 for red, green, and blue. The very last step is a TAN activation, which ensures our output pixel values are in the range -1 to 1, matching our real data normalization. Now, for the other player in our game, the critic. In WGANs, we call it a critic instead of a discriminator, because its job isn't to output a probability between 0 and 1, but rather to output a raw score indicating how real it thinks an image is. A higher score means more real. Its architecture is a beautiful mirror image of the generator. It's a standard deep convolutional network that takes a 3-channel 128 by 128 image as input and progressively downsamples it. Each make-cret block uses a conv2D layer with a stride of 2 to halve the spatial dimensions, from 128 by 128 all the way down to a 4 by 4 feature map. At the same time, we double the number of channels at each step, which is a common pattern in CNNs for extracting increasingly abstract features. Let's look at the make-crit block. It contains a conv2D layer. Then, instead of batch norm, we're using instance norm 2D. This is a choice often made in GANs as it normalizes features per image, which can sometimes improve results. For our activation, we use leaky ReLU, which, as we discussed, is a GAN staple that helps prevent dying gradients. The final layer is a conv2D that takes the 4 by 4 feature map and collapses it down to a single 1 by 1 output channel. The forward method then takes this final feature map and flattens it into a single score for each image in the batch. This score is the critic's final verdict. Now we move to the source/trainer.py script. To keep our code clean and organized, we've encapsulated all the training logic inside a trainer class. Let's start with its init constructor. When we create a trainer object, we pass in all the essential components we've built so far: our generator and critic models, their respective optimizers, and the data loader. The constructor simply stores these as instance variables. It also initializes a cur step counter and lists to keep track of our losses. Then we have a check for WANB enabled. If this is set to true in our config, it calls the init WANB helper method. This is where we set up our experiment tracking. WANB init creates a new experiment run in our project. We pass our entire configuration dictionary to it, which is fantastic because it means all our hyperparameters will be saved and logged automatically with the run. the 1b.watch calls are also incredibly useful. They tell weights and biases to monitor our models, and it will automatically log things like the distribution of gradients and weights over time, which can be invaluable for debugging. Before we look at the training steps for our models, we need to understand the heart of the WGANGP algorithm, the gradient penalty. This function looks complex, but the idea is simple. For the Wasserstein loss to work properly, the critic must have a special property. Its gradient should have a norm of 1 everywhere. Enforcing this everywhere is impossible, so the WGANGP paper proposed a clever solution. Enforce it on points sampled randomly along the straight lines between pairs of real and fake images. Let's walk through the compute or gradient penalty function. First, we create a random tensor alpha with values between 0 and 1. Second, we use this alpha to create mixed images by linearly interpolating between our real and fake images. We also set requires grad true on these new images because we're about to calculate gradients with respect to them. Third, we get the critic's scores for these mixed images. Fourth, and this is the core of the function, we use torch.autograd grad. This is a powerful PyTorch function that explicitly calculates the gradient of some outputs, our mixed scores, with respect to some inputs, our mixed images. This gives us the gradient of the critic's output with respect to its input. Fifth, we calculate the L2 norm of this gradient for each image in the batch. Finally, we compute the penalty itself. The penalty is the mean squared distance between our calculated gradient norm and our target value of 1. We then scale this by our gradient penalty lambda hyperparameter. This loss term will be used to punish the critic if its gradients deviate from having a norm of 1. Now let's look at how we train our critic in the _train_critic_step function. A key feature of the WGANGP training process is that we train the critic more frequently than the generator. That's why this function contains a for loop that runs for critic cycles iterations, which we set to 3 in our config. Inside this loop, for each of its training steps, we first zero the critic's gradients. We generate a fresh batch of fake images from the generator. And again, notice the crucial .detach call here. We are only training the critic, so we must prevent gradients from flowing back to the generator. We then get the critic's predictions or scores for both the real images and the fake images. Next, we call our compute gradient penalty function using these same real and fake images to get our gradient penalty term GP. Finally, we compute the critic's loss. The formula is the heart of the Wasserstein GP loss for the critic. It is the mean score of the fake images minus the mean score of the real images plus our gradient penalty. The critic's goal is to minimize this loss. It does this by making the scores for real images as high as possible and the scores for fake images as low as possible, while also keeping its gradients well behaved. We then backpropagate this loss and take a step with the critic's optimizer. We repeat this entire process for the number of critical cycles. After the critic has been updated multiple times, it's the generator's turn to learn. The _train generator step function is much simpler. We start by zeroing the generator's gradients. We then create a new batch of fake images by passing random noise through the generator. Next, we get the critic's prediction for these fake images. And this is critically important. Notice that there is no .detach call this time. This is because the generator's entire learning signal comes from the critic. We need the gradients to be able to flow from the loss back through the critic and all the way into the generator's weights. Now for the loss function. The generator's goal is to produce images that the critic gives a very high score to. In other words, it wants to maximize the value of fake pred.mean. Since our optimizers in PyTorch work by minimizing a loss function, The way we achieve this is by defining our loss as negative fake prediction mean. Minimizing the negative of a value is mathematically identical to maximizing the original value. We then backpropagate this simple loss function and take a step with the generator's optimizer. This updates the generator's weights in a direction that should produce images that the current critic will score more highly. Finally, we have the main train method of our trainer class. This is the top-level orchestrator for the entire process. It consists of two nested loops. The outer loop iterates over our desired number of epochs, and the inner loop iterates through every batch of real images provided by our data loader. We wrap our data loader with TQDM to get a nice real-time progress bar in our console. Inside the inner loop, for every single batch of real images, we perform our two-step training process. First, we call our _train_critic_step function, passing in the real images. As we know, this will run the critic's training for critic cycles iterations. Second, we immediately call our iTrainGenerator step function. This performs a single update for the generator. After both models have been updated, we move on to logging and saving. We log the losses to weights and biases if it's enabled, and update our TQDM progress bar with the latest loss values. Periodically, based on our show step and save step config values, we'll pause to visualize a batch of newly generated images and save a checkpoint of our model's state. We then increment our global step counter and repeat the process for the next batch. This critic update, generator update, log and repeat cycle is the fundamental rhythm of our WGANGP training. Last but not least, we have our main entry point, main.py. This script is responsible for bringing all of our separate modular components together and starting the training process. Inside the run training function, we first initialize our generator and critic models and move them to our target device. Next, we create our two separate Adam optimizers, one for the generator's parameters and one for the critics, using the learning rate and beta values we defined in our config file. Then, we call our getSaliba function from our dataset script. This single call will handle the entire process of downloading, extracting, and preparing our dataset. With all our components ready, the models, the optimizers, and the data, we instantiate our trainer class, passing all these objects to its constructor. Finally, we simply call WGAN trainer train. This single line kicks off the entire training process we just detailed. The last block at the bottom is the actual start of the script. It first handles logging into weights and biases if we have it enabled, and then it calls our run training function to get everything started. To train this entire complex WGANGP, all you need to do is run this one file from your terminal. So let's step back and look at the incredible system we've just built. This is a state-of-the-art implementation of one of the most important GAN architectures ever developed. You have built a complete WGAN GP from scratch, understanding the theory behind the Wasserstein loss and the crucial role of the gradient penalty in stabilizing training. You've implemented a deep convolutional architecture capable of working with high-resolution 128 by 128 pixel images. You've created a fully automated data pipeline that can download and prepare a massive dataset with a single function call, and you've done it all within a professional modular code base that includes powerful tools like weights and biases for experiment tracking. You now have a solid foundation and a powerful template for any future generative modeling projects. I highly encourage you to experiment. Go into the config.py file and see what happens when you change the number of critic cycles or the learning rate. Try adapting the dataset. PyScript to work with a different image dataset you're interested in. Or for a real challenge, try to build on this architecture to implement even more advanced models. Thank you so much for joining me on this very deep dive. If you've enjoyed it and feel like you've leveled up your deep learning skills, please give the video a like and subscribe for more masterclass tutorials. Happy generating! Hello everyone, and welcome back to the BrainOmega channel. Today we have another tutorial and hands-on session for you, and we're tackling one of the most critical topics in artificial intelligence, LLM alignment. We'll explore exactly how developers take a powerful but raw AI and carefully shape it to be helpful, honest, and safe for users. Have you ever stopped to think about the magic behind an AI like ChatGPT? You ask it a complex question, and it doesn't just spew out random text from the internet. It understands your intent, it adopts the right tone, it tries to be helpful. How did a machine learn to be so cooperative? The journey from a raw, chaotic language model to a helpful assistant is not an accident. It's the result of a deliberate and ingenious process called alignment. Today, we're taking a deep dive into this process. Using this seminal diagram from OpenAI's research on InstructGPT, the model that paved the way for ChatGPT, we'll explore the science of teaching an AI to share our goals. We will break down each step in detail, understand why alignment is arguably the most important problem in AI safety, and examine the significant challenges that still have researchers racing to find better solutions. This is the story of how we're trying to make sure AI works for us, not just near us. Let's get started. Imagine a brilliant student who has read every book in the library. They have all the knowledge, but they're unfocused, they ramble, and they don't know how to answer a direct question. That's a base language model like the original GPT-3. Its only training was to predict the next word on a massive scale. The alignment process is how you turn that brilliant but unfocused student into a dedicated, helpful research assistant. The core technique is reinforcement learning from human feedback, or RLHF, and it begins with step 1, supervised fine-tuning SFT. The goal here is to give the model a basic template for what a good answer looks like. The process starts with collecting real-world prompts, many of which came from actual users of OpenAI's early API. This is crucial. It's not just academic questions, but messy, real-life requests. For our example, the prompt is, explain the moon landing to a 6-year-old. Instead of letting the AI try to answer, a human expert, a labeler, steps in and writes a high-quality exemplary response. You see it here. Some people went to the moon. This is called demonstration data because it demonstrates the desired behavior. This curated data set containing thousands of these prompt demonstration pairs is then used to fine-tune the base model. Think of it like a chef's training. You don't just give them a cookbook. You show them videos of a master chef preparing each dish perfectly. They learn the right techniques, the right timing, and the right presentation. This step alone provides a massive improvement, but SFT has a weakness. You can't possibly create a human demonstration for every single type of question a user might ask. To get an AI that can generalize to new, unseen prompts, we need to move from learning by imitation to learning from preference. That brings us to step 2, training a reward model. This is where we build our AI judge. The objective here is to teach a separate AI to understand human preferences with nuance. We start with a prompt and have our SFT model from step 1 generate several different answers. Here, A, B, C, and D. Let's imagine what these could be. Answer A might be technically correct, but full of jargon about orbital mechanics. Answer B might be factually wrong, saying they flew there in a balloon. Answer C might be simple, accurate, and engaging for a child. Answer D might be a bit too simplistic, leaving out key details. A human labeler then ranks these outputs. It's often much easier for a person to compare and say, C is better than A, which is better than D, which is better than B, than it is to write the perfect answer C from scratch. This ranking, D is preferred over C, which is preferred over A, and so on, is the crucial piece of data. Thousands upon thousands of these comparisons are collected and used to train a completely separate model, the reward model, RM. This reward model becomes our automated judge. It doesn't know how to write a story about frogs itself, but after reviewing countless ranked examples, it develops an incredibly sophisticated sense of what humans find helpful, truthful, and well-written. It learns to assign a high score to good answers and a low score to bad ones. Now that we have our judge, we can use it to train our main AI at a massive scale. And this leads to the grand finale, step 3, reinforcement learning. This is where the magic truly happens, in a dynamic and continuous loop. A new prompt is sampled, like write a story about frogs. Our main AI, the policy, writes an answer. Instantly, the reward model we just trained swings into action. It reads the prompt and the AI story and outputs a single number, a reward score. A high score says, great job. A low score says, try again. This reward is then used to update the AI's policy using an algorithm called PPO, or Proximal Policy Optimization. In simple terms, PPO is a clever way of taking a small, stable step in the right direction. It encourages the model to try things that will get a higher reward, but it does so cautiously, ensuring the model doesn't drastically change its strategy and forget all the useful language skills it already has. This loop runs millions of times. Generate, score, update, generate, score, update. The AI is essentially in a high-speed training simulation, constantly refining its ability to produce outputs that our AI judge and, by extension, humans will like. However, this intense optimization comes with a risk mentioned in the article, the alignment tax. If you only train the AI on pleasing the reward model for user tasks, it can start to forget some of its core knowledge and perform worse on other academic benchmarks. To solve this, OpenAI mixes a small amount of its original pre-training data back into this step. It's like making a student study for a specific exam, but also ensuring they keep up with their regular coursework so they remain well-rounded. As powerful as RLHF is, it is not a silver bullet. It's the first major step, but it comes with serious limitations that define the cutting edge of AI safety research today. First, as we've noted, it's incredibly resource-intensive. It relies on a human-in-the-loop system, but that loop is a bottleneck. We can build bigger models far faster than we can generate the high-quality human data needed to align them. Second, and perhaps most critically, is the problem of bias. The AI is being aligned to the preferences of a few hundred to a few thousand labelers. This group cannot represent the full diversity of global cultures, values, and perspectives. If you ask about a beautiful home, whose definition of beauty does it use? If you ask about a fair political policy, whose definition of fairness gets encoded? This is a profound societal challenge. Third, there is the risk of reward hacking. The AI's goal is simply to maximize its score from the reward model. It might discover that it can trick the judge. For instance, it might learn that long, confident-sounding answers get high scores, so it generates verbose, jargon-filled text that seems impressive but is actually vague and unhelpful. It's optimizing for the appearance of being good, not the reality. Because of these challenges, researchers are actively developing what comes next. This includes concepts like constitutional AI, where an AI critiques and improves its own answers based on a written constitution of ethical principles, reducing the need for constant human oversight. Other methods involve using AI models to debate each other to find flaws in reasoning, creating a more robust alignment signal than any single human could provide. The holy grail is to discover an alignment technique that scales with a model's intelligence, ensuring that as AI becomes ever more powerful, our ability to wisely steer it grows right alongside it. And for those who want to dive into the practical side, the complete code for this project is available on our GitHub page. You can access the link in the description of this video. Today, we are going to explore one of the most recent and powerful alignment algorithms, ORPO. The complexity of RLHF led researchers to ask, can we achieve the same goal more directly? This led to the breakthrough of direct preference optimization. The complexity of RLHF led researchers to ask, can we achieve the same goal more directly? This led to the breakthrough of direct policy optimization, or DPO. The core idea of DPO is brilliant. It showed that the entire complex RLHF pipeline can be mathematically simplified down to a simple loss function. All you need is a preference dataset with triplets of a prompt, a chosen response that is preferred, and a rejected response that is not. The DPO loss function then directly optimizes the model to assign a higher probability to the chosen response and a lower probability to the rejected response for the same prompt. This is much more stable and simpler than RLHF. However, DPO still has one drawback. During training, it needs to constantly compare the fine-tuned model's probabilities to the probabilities assigned by a frozen reference copy of the original model. This reference model consumes a significant amount of extra GPU memory. This brings us to the cutting-edge algorithm we'll be using today, ORPO, which stands for Monolithic Preference Optimization. ORPO's big idea is to ask, what if we could combine the simple SFT objective of learning to say the right thing with the DPO objective of learning to prefer the right thing into a single, elegant loss function? And that's exactly what it does. The ORPO loss has two parts. The first part is the standard next token prediction loss on the chosen response, just like in SFT. But it adds a penalty term. If the model assigns a very low probability to the good chosen response, it gets a large penalty. This forces the model to first learn to generate the good response well. Then, the DPO-like part of the loss kicks in to push the probability of the chosen response even higher than that of the rejected response. The incredible result of this combined approach is that it eliminates the need for a separate reference model. Because we're simultaneously reinforcing the correct language and the preference, the model doesn't drift away from its core knowledge. This makes ORPO even simpler and more memory efficient than DPO. It's the state of the art, and it's what we are going to build. So, you want to run the ORPO Llama fine-tuner project but don't have a powerful local GPU? No problem. We'll get it running in minutes using Google Colab. First, let's make sure our environment has the necessary hardware. Go to Runtime, select Change Runtime Type, and in the Hardware Accelerator drop-down, choose the T4 GPU. This is the key step that gives us the power needed for fine-tuning. Click Save. Now, let's bring in the code. In the first cell, we'll use the !git clone command followed by the project's GitHub URL. When you run this, Colab will download the entire ORPO Llama Fine-Tuner repository into our workspace. Next, we need to navigate into the project folder that was just created. We'll use the command %cd orpo-llama-fine-tuner. The %cd command changes our current directory so we can run the project's scripts. Finally, you're ready to start the fine-tuning. Simply run the command !python main.py. Colab will now execute the main script using the free T4 GPU to handle the intensive training process, and that's it. You're now successfully running the ORPO Llama Fine-Tuner project in the cloud. We will walk you through the process of setting up access to our dataset and model. The first step is to create a new Google Cloud project and configure an OAuth client. On the screen, you'll see a Google Drive access page. If you're trying to access to dataset or model, you might encounter this page requesting access. Simply enter a message if you like and click Request Access. We will then approve your request. Meanwhile, to get started with the necessary credentials, open your Google Cloud Console. If you don't have a project yet, you'll need to create one. Click on New Project and fill in the details. Once your project is created, navigate to the Clients section. If you see a message that says Google Auth Platform not configured, don't worry. Click on Create OAuth Client. This will take you to the setup process for your credentials. This is a crucial step for authenticating your application's access to Google Cloud Services. This process ensures secure access and management of your data and models. By following these steps, you'll have the foundational setup needed to move on to the next phase of our tutorial. Continuing from our last step, we are now ready to create the OAuth client ID that will be used to access our dataset and model. In your Google Cloud Console, under the Clients section, click on Create OAuth Client ID. You will be presented with a form. Select Web Application. As the application type, give your client a name. Something like Model Access is a good example. You don't need to fill in the authorized JavaScript origins or authorized redirect URIs for this particular setup. Click Create. Google will then generate your OAuth client credentials. A pop-up window will appear showing your client ID and client secret. This is your authentication key. Now, let's look at the file structure on the right side of the screen. You should have a folder for your project, in this case ORPO Llama Fine Tuner. Inside, you'll see files like config.py, main.py, and trainer.py. To properly configure your access, you need to create a file named credentials.json. Take the JSON snippet that Google provided and save it as credentials.json inside your project folder. The arrows on the screen show the file being renamed to credentials.json and being placed in the root of your project folder. This file will be read by your application to authenticate with Google Cloud Services, allowing you to seamlessly access your dataset and model for your fine-tuning tasks. This finalizes the setup for authenticated access. All right, with that deep dive into the theory, let's open up the code and start building. We're in the model/llama.py file. This single file will contain our entire from-scratch implementation of the Llama model architecture. First, let's walk through the imports at the top so we know what tools we have at our disposal. Import math. This is a standard Python library we'll need for just one thing, a square root calculation inside our attention mechanism. From data classes, import data class. This is a modern Python feature that gives us a super clean way to create classes that are primarily used for storing data, like our model configuration. From typing import optional, tuple, these are for type hinting. They don't change how the code runs, but they make it much more readable for us and other developers by specifying what kind of data to expect. Import torch, import torch.nn as nn, and from torch.nn import functional as f. These are our workhorses. We're importing the main PyTorch library, its core neural network module class, which we'll inherit from, and the library of common functions like softmax and silu, which we'll use by the conventional alias f. With our tools imported, we define our model args data class. Think of this as the blueprint or the recipe for our Llama model. It holds all the key architectural parameters in one organized place. Dim is the core dimensionality of our model's embeddings. Layers defines how deep our transformer will be. Heads is the number of attention heads. Cave heads is a key parameter for an optimization called grouped query attention, which we'll explore in detail. Vocab size defines how many unique tokens our model understands. And norm EPS is a tiny number we'll add during normalization to prevent any division by zero errors. This data class is our single source of truth for the model's architecture. The first component of our Llama model is its normalization layer. Instead of the standard layer norm used in the original transformer, Llama uses a simpler and more efficient variant called RMS norm, or root mean square normalization. Let's look at the init method. The key thing you'll notice is that it only has one trainable parameter, self.weight. This gain vector allows the layer to scale the normalized output. Unlike layer norm, there is no bias or shift parameter, which is part of what makes it simpler. The core logic is in the norm function. The formula for RMS norm is to take the input vector x and divide it by the square root of the mean of the squares of its elements. The x.pow of 2.mean over minus 1 keep dim equals true part calculates the mean of the squares. Torch.rsqrt is a highly optimized function that calculates 1 over the square root, which is faster than doing torch.sqrt and then a division. The small eps value is added for numerical stability to prevent division by 0. In the forward pass, we first normalize the input x by calling our underscore norm function. Then, we take this normalized output and multiply it by our learned weight parameter. This allows the network to learn the appropriate scale for the features at that point in the model. It's a simple, fast, and effective normalization technique. Next, we come to one of the most important and clever innovations in modern transformers: how we handle positional information. The original transformer added a separate, learned positional embedding to the token embedding. Llama uses a more advanced technique called rotary positional embeddings, or ROP. The core intuition behind ROP is that instead of adding position information, we can rotate our query and key vectors in a way that encodes their absolute and relative positions. The amount of rotation depends on the token's position in the sequence. Because the dot product between two rotated vectors depends on the difference in their rotation angles, the attention mechanism naturally learns to favor tokens with a certain relative distance. Let's look at the code. The pre-compute Inference CS function does exactly what its name says. It pre-calculates the cosine and sine components of all the rotation angles we will ever need, up to our max sequence length. It first calculates a set of base frequencies that are different for each dimension of our vectors. Then, it uses torch outer to create a matrix where each row corresponds to a position in the sequence and each column corresponds to a feature dimension containing the precise angle for that position dimension pair. The apply rotary MB function then takes our query and key vectors xq and xk and applies these rotations. The math looks a bit complex, but it's just a 2D rotation formula. It treats each pair of features in our vectors as a single complex number and multiplies it by the pre-computed rotation angle. This elegant method has been shown to be incredibly effective at helping transformers understand the relative positions of tokens. Another major innovation in the Llama architecture is an optimization called Grouped Query Attention, or GQA. Let's first understand the problem it solves. During inference, when the model generates text token by token, it stores the calculated keys and values from all previous tokens in a key value cache to avoid recomputing them. In standard multi-head attention, you have a separate key and value head for every query head. This cache can become a huge memory bottleneck. To solve this, a technique called multi-query attention was proposed, where you have many query heads but only a single key and value head that is shared by everyone. This drastically reduces the size of the KV cache but can sometimes lead to a loss in quality. Grouped query attention is the perfect compromise. We have our full number of query heads, but we have a smaller, intermediate number of key and value heads. These KV heads are then shared across groups of query heads. For example, we might have 32 query heads but only 8 KV heads, where each KV head is shared by a group of 4 query heads. The repeat KV function is the simple but essential mechanism that implements this sharing. It takes the key or value tensor, which has the smaller number of n KV heads, and it skillfully expands and reshapes it to match the full number of query heads. This effectively copies the KV heads so that each group of query heads can attend to its designated shared key and value. Alright, let's assemble all these advanced components into our main attention module. In the init method, we first calculate all our head dimensions based on the model args. We define our 4 crucial linear layers, WQ, WK, and WV, to project the input into query, key, and value vectors, and WO for the final output projection. Then we have a very important check. We see if our PyTorch version has scaled dot product attention. This is the function for flash attention, a highly optimized implementation of the attention mechanism that is much faster and more memory efficient. If it's not available, we fall back to creating a manual causal attention mask. Now for the forward pass, let's trace the data flow. The input X comes in. First, we pass it through our WQ, WK, and WV layers, and then reshape the output to separate the heads. Notice XK and XV are reshaped with the smaller n local KV heads. Next, we apply our rotary positional embeddings to the query and key vectors, rotating them to inject the positional information. Then we call our repeat KV function to implement grouped query attention, expanding the key and value tensors to match the number of query heads. After transposing the tensors to prepare for matrix multiplication, we finally calculate the attention. If flash attention is available, we use the single, highly optimized scale dot product attention function, simply setting is causal equals true. If not, we perform the manual attention calculation. Matrix multiply, Q and K transposed, scale, add the mask, apply softmax, and multiply by V. Finally, we reshape the output tensor back and pass it through our final output projection layer, WO, to get the result of this attention block. Every transformer block has 2 main components, an attention sublayer and a feed-forward sublayer. We've just built our advanced attention module. Now let's build the feed-forward part. The Llama architecture uses a specific variant of a feed-forward network called SWI-glue. In the feed-forward class, you'll notice it has 3 weight matrices, W1, W2, and W3. The forward method implements the SWI-glue formula. The input X is projected up by 2 separate matrices, W1 and W3. The output of the W1 projection is passed through a SILU activation function, which is then multiplied element-wise with the output of the W3 projection. This result is then projected back down by the W2 matrix. This gated structure has been shown to be very effective. Now we can finally assemble our complete transformer block. In its init, it simply creates an instance of our attention module and our feed-forward module. It also creates 2 separate RMS norm layers, one for each sublayer. The forward pass clearly shows the modern pre-normalization structure. The input X is first normalized by attention norm before it goes into the attention module. The output of the attention is then added back to the original unnormalized X in a residual connection. This result, H, is then normalized again by FFN norm before it goes into the feed-forward network. And finally, that output is added back to H in a second residual connection. This norm, then transform, then add pattern is a key feature of the Llama architecture and is critical for stable training of very deep networks. We've built all the components and now it's time for the final assembly in our Llama class. In the init method, we put all the pieces together. We create our talk embeddings layer, which will map our input token IDs to dense vectors. We then create our stack of transformer blocks, using a module list to hold all n layers of them. After the blocks, we have our final norm layer and the output linear layer that will produce our final vocabulary scores, or logits. Finally, we call our precompute FREX CIS function one time to calculate our rope frequencies, and we register them as non-persistent buffers. This is a small optimization that tells PyTorch these tensors are part of the model's state, but don't need to be saved in the state direct, as they can always be recomputed. Now for the forward pass. It takes our input tokens and optional targets. First, it gets the token embeddings. Then, it slices our pre-computed RoPE frequencies to match the current sequence length. It then passes the embeddings through every single transformer block in a for loop. After the final block, it applies the final normalization. Now we have a conditional check. If targets are provided, it means we are in training mode. We calculate the logits for the entire sequence. We then perform a crucial shift. We shift the logits one position to the left and the targets one position to the right. This aligns the prediction at time step t with the target at time step t plus 1, which is exactly the next token prediction task. We then calculate the cross-entropy loss. If targets are not provided, it means we are in inference mode. We don't need to compute logits for the whole sequence. We only care about predicting the next token. So as an optimization, we only compute the output for the very last token in the sequence, which is much faster. Let's take a quick look at config.py. This is our project's control panel. We've defined all our important parameters here. This includes training parameters like the batch size, epochs, and learning rate. A key parameter for our specific fine-tuning task is alpha ORPO. This is the scaling coefficient, often called lambda, that balances the two parts of the ORPO loss function, the standard language modeling loss and the preference ranking loss. The value of this parameter can have a significant impact on the final performance of our fine-tuned model. We also have our system and path configurations, which tell the script where to find the tokenizer, where to save checkpoints, and which dataset to use from the Hugging Face Hub. Having all of these settings in one place makes our code much cleaner and our experiments much easier to manage. Our project is designed to start from a pre-trained model, which we need to download. The script utils/gdrive.py is a self-contained utility for handling this. The getDrive service function is responsible for authenticating with the Google Drive API. It uses the standard OAuth2 flow. The first time you run it, it will look for a credentials.json file, which you need to get from the Google Cloud Console. It will then prompt you to visit a URL in your browser, authorize the application, and paste back an authorization code. Upon success, it saves your credentials in a token.json file. On all subsequent runs, it will find this token.json file and reuse your credentials without asking you to authorize again. The download and extract zip function then uses this authenticated service to download the specified file from Google Drive. It downloads the file into an in-memory buffer, shows the download progress, and then uses Python's zip file library to extract the contents, our model and tokenizer, into the correct directory. This makes the initial setup of our project completely automated. Now we arrive at the main conductor of our project, the ORPO trainer class in trainer.py. This class encapsulates all the logic for our fine-tuning process, making our main script incredibly clean and simple. Let's look at the init method. It acts as a master setup function. Instead of having one giant, messy constructor, we've broken down the setup process into a series of logical private helper methods. It first sets up our weights and biases logging, then it sets up the tokenizer, then it loads and prepares our Llama model, then it prepares our data loaders, and finally, it sets up our optimizer and learning rate scheduler. We're going to walk through each of these setup methods one by one to see exactly what they do. Let's look at the setup methods inside our ORPO trainer. First, setup port tokenizer calls our Google Drive download utility to ensure the files are present. Then it uses auto-tokenizer dot from pre-trained to load our tokenizer from the local path. It then configures the tokenizer with the specific chat template and pad token that the model expects. Next, setup model is where we load our pre-trained weights. It loads the base.pt checkpoint file, which contains both the model's configuration and its weights. It intelligently uses the model config from the checkpoint to create an instance of our from-scratch Llama class with the exact same architecture. Then it calls model.loadStateDictionary CKPT to load the pre-trained weights into our model. This is a perfect example of how to separate a model's architecture from its trained weights. Finally, here prepare data loaders handles our dataset. It's a smart function that first checks if we have a pre-processed tokenized version of the dataset saved locally in a cache. If so, it loads it instantly. If not, it downloads the raw dataset from the Hugging Face hub, performs all the necessary filtering and pre-processing steps to get it into the format we need for ORPO, and then saves the result to the cache directory, so we never have to do this slow pre-processing step again. It then creates and returns our standard PyTorch data loaders for training and validation. Now for the mathematical core of our trainer. The setup optimizer function creates our AtomW optimizer, which will update our model's weights. We also define a custom learning rate scheduler. This scheduler will implement a warm-up phase, where the learning rate gradually increases from 0, followed by a cosine decay phase, where it smoothly decreases. This is a very common and effective schedule for training transformers. The calculate log probs function is a complex but necessary helper. Its job is to calculate the total log probability of just the response part of a sequence, ignoring the prompt part. It does this with some clever masking. Finally, the get ORPO loss function. This is the heart of the entire project. It takes a batch of data and first performs a forward pass with the positive input IDs to get loss pos, which is our standard SFT language modeling loss on the chosen response. It then uses our helper function to get the log probability of this chosen response. It does the same for the negative input IDs to get the log probability of the rejected response. It then calculates the log odds term. This formula, taken directly from the ORPO paper, represents the odds ratio between the chosen and rejected responses. This term is then passed through a log sigmoid function. The final total loss is the combination we discussed in our theory section. It's the standard SFT loss, loss pos, minus our preference loss term, scaled by alpha ORPO. This is the single value we will backpropagate to train our model. With all of our setup methods and our loss function defined, the final train method is the orchestrator that puts them all into action. It starts by printing a banner and getting an initial estimate of the loss before any training has happened. This gives us a good baseline. Then it enters the main for loop, which iterates over our desired number of epochs. Inside this, we have another loop that iterates through every single batch in our train loader, wrapped in TQDM to give us a nice progress bar. For each batch, we perform the standard PyTorch training steps. We call optimizer.0grad to reset the gradients from the previous step. We move the batch of data to our target device, like the GPU. We call our getORPOLoss function to perform the forward pass and compute our final loss for this batch. This is the learning step. Total loss.backward computes the gradients. clipgrad.norm is a standard technique to prevent gradients from exploding. And optimizer.step and scheduler. Step, update our model's weights and the learning rate, respectively. Periodically, based on our log interval, we pause to call our estimate loss function, which evaluates the model on both the training and validation sets, and we log these metrics to the console and to weights and biases. Finally, at the end of every epoch, we call save down checkpoint to save our model's progress. The entire loop is wrapped in a try. Finally block to ensure that even if we interrupt the training, our resources are cleaned up properly. Last but not least, let's look at main.py. After all the complexity we've built in our model and trainer files, our main entry point is beautifully simple. This is a sign of a well-designed modular codebase. At the top, we have a place for you to insert your Hugging Face API token. We also enable some PyTorch performance enhancements like allow TF32, which can speed up computation on modern NVIDIA GPUs. Then we import our ORPO trainer class. The main function itself is incredibly concise. It does just two things. First, it creates an instance of our ORPO trainer. As we know, the __init method of this class will trigger our entire setup process, downloading data, loading the model, and preparing the optimizer. Second, it calls trainer.train, which kicks off the main training loop we just reviewed. The standard main block ensures that this main function is called when we run the script from our terminal with the command python main.py. That's it. All of our complex logic is neatly encapsulated in our trainer, and our main script is just a clean, simple launcher. And with that, our training process is complete. Let's take a moment to step back and appreciate the incredible state-of-the-art system that you have just built. This was a true deep dive, and you've accomplished a tremendous amount. We started our journey with a deep dive into the theory of AI alignment, tracing the evolution of fine-tuning from the early days of supervised fine-tuning through the complexities of RLHF and all the way to the modern and efficient DPO and ORPO algorithms. Then, we rolled up our sleeves and did what very few tutorials do. We built a complete LLAMA model from absolute scratch. You implemented every single advanced component from RMS norm and rotary positional embeddings to grouped query attention, giving you a fundamental understanding of this powerful architecture. Finally, we brought it all together. We created a professional end-to-end training pipeline that automatically downloads our data and pre-trained model. And we successfully fine-tuned our from-scratch Llama using the elegant and powerful ORPO loss function. You now have a deep practical understanding of how modern language models are built and aligned. The learning doesn't have to stop here. I highly encourage you to take this project and make it your own. Go into the config.py file and experiment with the hyperparameters. See for yourself how changing the alpha ORPO value affects the model's final performance. Try finding a new preference dataset on the Hugging Face Hub and fine-tune this model to be a specialist in a domain you're passionate about. And for a fantastic next step, you could build an Inference, PyScript, and a Gradio web interface to easily chat with and showcase your newly fine-tuned model. If you've enjoyed this deep dive masterclass and you feel like you've leveled up your AI engineering skills, it would mean the world to me if you could take a second to like this video and subscribe to the channel. Your support is what allows me to create more free, in-depth tutorials just like this one, and it lets me know that this content is valuable to you. Also, be sure to share it with any friends or colleagues who you think would find it useful. Thank you so much for joining me on this incredible journey. Happy coding, and I'll see you in the next video. Welcome to this tutorial on federated learning, where instead of gathering all your data in one place, we train models directly on each client's device. Think smartphones or edge sensors, and share only the learned updates with a central server. In our example code, the process begins by splitting the MNIST dataset into client-specific partitions, each of which loads data locally and trains a small convolutional neural network. After each client performs its local training, it sends its model updates back to the server. The server then aggregates these updates according to the chosen algorithm. FedAvg averages client model weights in proportion to their data size. FedSGD collects and averages gradients from each client after a single batch. FedDANE solves a local subproblem that approximates a Newton step by adding a carefully chosen quadratic term, and FedProx extends FedAvg by penalizing large deviations from the global model to improve stability under non-IID data. Once the server computes the new global model, it broadcasts it back to all clients for the next round. This interplay of local computation and periodic aggregation preserves privacy, reduces communication overhead, and leverages distributed compute resources. By exploring FedAvg, FedSGD, FedDANE, and FedProx in our code, you'll see how different strategies balance computation, communication frequency, and data heterogeneity to achieve efficient collaborative learning across distributed devices. The complete code for this tutorial is available on our GitHub page. See the link in the video description. We're looking at the core configuration for our federated learning experiment defined in config.py. The flconfig class encapsulates all the key hyperparameters. Here, algorithm selects which federated algorithm to run. Options include FedAvg, FedDANE, FedProx, or FedSGD, while NumClients controls how many edge devices will participate. We specify num rounds, the total number of communication rounds between server and clients, and local epochs, which determines how many passes each client makes over their local data per round. The frac parameter sets the fraction of clients sampled each round, currently set to 1.0, so all clients contribute every time. Learning rates appear twice. Local RLR defines each client's optimizer step size, and although global RLR isn't used by vanilla FedAvg, it's available for algorithms like FedDANE. Finally, batch size tunes the mini-batch processing on each device, and useChurnCuda tells the script to leverage a GPU if available. Together, these settings give us full control over the trade-offs between computation, communication, and convergence in federated learning. We dive into dataloader.py, where we prepare and partition the MNIST dataset for our federated setup. First, we define a transformation pipeline that converts images to tensors and normalizes them with the standard MNIST mean and standard deviation. We then download both the training and test splits of MNIST. Next, we partition the training set equally across all clients. We calculate data per client by dividing the total number of training samples by the configured number of clients. For each client, we create a subset of the global dataset using the appropriate index range and wrap it in a data loader with shuffling enabled. This ensures each client's local training sees its data in a random order. Finally, we assemble all client-specific loaders into a list and also prepare a global test loader without shuffling. This design lets each client train independently on its own slice of data, simulating the decentralized nature of federated learning while still enabling evaluation on a common test set. Here we define our client and server backbone, the MNISTCNN model. It starts with two convolutional layers. Conv1 takes the single-channel input and produces 32 feature maps, while Conv2 expands that to 64. Both use a 3x3 kernel with stride 1, and each convolution is followed by a ReLU nonlinearity to introduce essential nonlinear transformations. After the convolutions, we apply a 2x2 max pooling operation, which halves the spatial dimensions and helps the network learn translation invariant features. We then flatten the feature maps into a vector of size 12 by 12 by 64, feeding it into a fully connected layer with 128 hidden units and another ReLU activation. Finally, a second linear layer projects down to 10 output logits, one per MNIST digit class. This compact CNN balances expressivity and efficiency, making it a great choice for federated learning scenarios where both communication and compute resources can be constrained. In federated learning, effective aggregation is crucial because it directly influences convergence speed, stability, and communication efficiency. Let's dive deeper. The average model's function is the classic FedAvg approach. After each client trains locally for one or more epochs on its private data, it sends its updated model weights to the server. Internally, we extract each client's state sondict, a mapping of parameter names to tensors, and for each parameter key, for example, the convion.weight tensor, we stack all clients' tensors into a new dimension. Computing the mean along that dimension yields the aggregated weight. This simple arithmetic average implicitly assumes that each client's dataset is equally important. If you wanted to weight clients by dataset size, you could multiply each tensor by its client's fraction of the total data before summing and then divide by the sum of weights. Once the server updates its own model parameters with these average tensors, it broadcasts the refreshed global model back to clients for the next round. On the other hand, average gradients gives us a gradient-based aggregation path, which is especially useful for algorithms like FedSGD or when you want to apply momentum or adaptive optimizers at the server. Instead of exchanging full model weights, clients send only their gradients, often much smaller in magnitude and communication footprint. We gather each client's gradient dictionary from model name parameters, stack each parameter's gradient vector across clients, and compute the mean. This average gradient can then be applied with a server-side optimizer step, allowing you to leverage server global learning rates, momentum, or atom updates. One caveat: if clients have very skewed data distributions, raw gradient averaging can amplify noise. Techniques like gradient clipping or secure aggregation may be necessary to stabilize training. Together, these utilities show the two fundamental flavors of federated aggregation. Weight averaging is straightforward and robust for homogeneous settings, while gradient averaging unlocks more sophisticated optimization strategies. Choosing between them, or even combining them, lets you tailor your federated algorithm to your data privacy, communication, and convergence needs. We'll unpack the 4 custom optimizers that enable different flavors of federated updates. FedAvg optimizer inherits SGD. This is just plain vanilla SGD under the hood. Clients perform multiple local SGD steps, and then the server calls our average model's utility to merge their weights. No special logic here. FedAvg relies on model averaging to converge. FedProx optimizer extends SGD. We add a proximal term to the update, controlled by hyperparameter and mu. After the usual SGD dot step, we loop over each parameter p and its corresponding global parameter g. We adjust p.data by subtracting mu times lr times open parenthesis p.data minus g.data close parenthesis. Intuitively, this gently pulls your local model back toward the global model each iteration, mitigating client drift when their data distributions diverge. FedDANE optimizer extends SGD, builds on FedProx by also using a snapshot of the global gradient. After the base SGD step, for each parameter p, we compute a corrected gradient, where global grad is the server's aggregated gradient from the previous round, and g is the global weight snapshot. We then take a manual gradient descent step using this corrected gradient. This hybrid approach, proximal regularization plus gradient correction, aligns local updates more closely with the overall objective. FedSGD optimizer implements optimizer. Unlike the others, clients do no local epochs. They compute a single batch of gradients, send them back, and then stop. The server averages these gradients across clients and redistributes them. On each step, we directly apply the average global gradients to the local parameters. That means p.data minus equals lr times global grad. This keeps communication per round high, gradients every batch, but avoids client computation overhead. Together, these optimizer classes show how you can plug in different federated update rules simply by swapping out an optimizer. The shared training loop remains unchanged, highlighting the modularity and extensibility of this design. Let's dive deeper into the client class to understand exactly how each client performs its local training. Initialization, init method. We start by taking a fresh copy of the global model and moving it to the client's device, CPU or GPU. The client's private data is wrapped in a data loader for mini-batch training. We pull in the shared config, which holds hyperparameters like learning rate, number of local epochs, and the chosen algorithm name. A simple dictionary maps algorithm names, FedAvg, FedProx, FedDANE, FedSGD, to the corresponding optimizer class. This dynamic lookup means you can add new algorithms without changing the training loop. For FedProx and FedDANE, we also pass in the proximal coefficient mu, which controls the strength of the regularization toward the global weights. Training entry point, train method. We always switch the model to .train mode to ensure layers like dropout or batch norm behave correctly. Epoch count. For FedSGD, we only do one pass because it's purely gradient-based and we send gradients directly. For all other algorithms, we run config.local epochs, passes over the local data to balance communication cost versus computation. Batch loop with progress bars. We wrap the outer epoch loop in Trange and the inner batch loop in TQYIM so you see real-time feedback on training progress for each client. Data movement. Each data target pair is moved to the same device as the model. We call optimizer.zeroGrad to clear any stale gradients from the previous batch. A forward pass through self.model open parenthesis. Data close parenthesis produces raw scores, which we feed into f.nll_loss to compute the negative log likelihood loss. Note, for a true NLL, you'd usually have a log softmax layer, but this code assumes the optimizer or model includes that internally. Loss.backward.computes gradients with respect to all model parameters. Algorithm-specific update steps, FedAvg self. Optimizer.step parenthesis applies a simple SGD step on the local objective, accumulating client-specific weight updates. FedProx.step global params global model augments the SGD step with a proximal term that pulls client weights back toward the global parameters. This helps reduce client drift in heterogeneous data settings. FedDANE step global params global model global gradients global grads solves a quadratic subproblem at each client using both the global weights and the server aggregated gradients. This typically involves an inner Newton or quasi-Newton update to better align local updates with the global objective. FedSGD.step global gradients are global grads. Instead of updating weights locally, this variant immediately uses the local gradients and returns them to the server, which applies a global aggregation step. Return value. After finishing all epochs and batches, the client returns its updated model, or in the case of FedSGD, you'd return just the computed gradients. The server then collects these models or gradients from all participating clients and performs the global aggregation via average models or average gradients before sending the next round of updated global parameters back to each client. Let's walk through the server class, which coordinates the entire federated workflow. Initialization. We instantiate a fresh global model, MNIST CNN, and move it to the chosen device, CPU or GPU. The server holds references to each client's data loader and the central test loader for evaluation. Client selection. Select clients. We compute numSelected as the fraction config.frac of all clients, at least one. Here, for simplicity, we always pick the first numSelected clients. In practice, you might sample at random. Local training, train clients. For every selected client index, we make a deep copy of the global model, ensuring each client starts from the same parameters. We run standard PyTorch SGD for config.local epochs, looping over that client's local MNIST partition. After local training, we collect the client's updated model. Aggregation, AVG grads renamed but actually FedAvg. We grab the global model's state dict, then for each parameter key. We stack the corresponding tensors from all local models into a single tensor of shape, num clients. We compute the mean across the client dimension and replace the global parameter with this average. Finally, we load these average parameters back into the global model. Evaluation, evaluate. We switch the global model to evaluation mode and iterate over the held-out test loader. We accumulate correct predictions to compute overall accuracy, which we print after each round. Execution loop run. We repeat for config.num rounds communication rounds. 1. Select a subset of clients. 2. Train them locally. 3. Aggregate their models via weighted averaging. 4. Evaluate the updated global model on the central test set. This loop captures the essence of federated learning, decentralized local computation with periodic centralized aggregation. By modularizing client selection, local training, aggregation, and evaluation, this server framework cleanly implements the FedAvg algorithm while remaining extensible to other schemes like FedProx or FedSGD simply by swapping in different optimizer logic on the client side. In main.py, we orchestrate the entire federated learning workflow with a few clear steps. First, we parse a command line argument --algo so you can choose among FedAvg, FedDANE, FedProx, or FedSGD without touching the code. Next, we instantiate flconfig using that choice, which sets up how many clients will participate, how many rounds will run, learning rates, batch sizes, and other hyperparameters. We also detect whether a GPU is available and set our computation device accordingly. Then we call load MNIST partitions config to split the MNIST training set evenly across each client, returning a list of client-specific data loaders and a shared test loader. With data in hand, we initialize the server object, passing it our config, loaders, and device, and invoke server.run, which loops through each communication round, selecting clients, performing local training, aggregating updates into the global model, and printing the test accuracy after each round. Once training wraps up, we build the final save path, such as model/global/fedavg.phth, create any missing directories on disk, and serialize the learned global model parameters with torch.save. A simple confirmation message tells you where the checkpoint lives, so you can jump straight into further experiments or deployment. And that wraps up our deep dive into implementing federated learning from scratch on MNIST, covering everything from data partitioning and local client optimizers through FedAvg, FedProx, FedDANE, and FedSGD to server-side aggregation and evaluation. You now understand how each component fits together, how hyperparameters flow from config.py, and how the orchestration in main.py brings it all to life. Armed with this knowledge, you can experiment with larger models, different data sets, or more sophisticated client selection strategies to push the boundaries of privacy-preserving AI. If you found this tutorial helpful, don't forget to hit the like button, subscribe for more machine learning walkthroughs, and ring the bell so you never miss an update. Thanks for watching, and I'll see you in the next video. Welcome to this tutorial on combining reinforcement learning with a Bayesian echo-state network policy gradient. Let's break this down step by step. First, in reinforcement learning, or RL, we have an agent that learns to make decisions by interacting with an environment. Think of a robot learning to walk, or a program learning to play a video game. The agent observes the state of the environment, selects an action, and receives a reward based on the outcome. Over time, it aims to maximize its cumulative reward by learning which actions are most beneficial in different situations. Now, traditional RL algorithms often use deep neural networks to represent the agent's policy, especially for environments where the state is complex or involves sequences over time. But training these networks, particularly recurrent neural networks, can be computationally demanding and may require a lot of data to generalize well. This is where the Echo State Network, or ESN, comes in. The ESN is a special kind of recurrent neural network, but with a twist. Instead of training all the network weights, only the final output layer, called the readout, is trained. The rest of the network, called the reservoir, is a large, randomly initialized, and sparsely connected set of neurons. When you input a signal, the reservoir generates a rich, nonlinear echo of your input over time. Because only the readout layer is trained, ESNs are extremely efficient and can capture complex temporal dependencies without the heavy computational cost of traditional RNNs. However, a challenge remains. How do we ensure that our agent not only learns, but also knows when it is uncertain about its decisions? This is important, especially in real-world scenarios where making mistakes can be costly or dangerous. To address this, we make the ESN Bayesian by introducing dropout at the readout layer, not just during training, but also during inference. This means that every time our agent needs to make a decision, it passes the state through the ESN multiple times, each time randomly dropping different connections in the readout. The output is averaged across these passes, which not only makes the policy more robust, but also gives us a measure of uncertainty in the agent's actions. This technique, sometimes called Monte Carlo dropout, helps the agent explore more intelligently and avoid overconfident, risky decisions. In the training process, we use the policy gradient method, specifically the reinforce algorithm. Here, the agent samples actions based on the policy's output, collects rewards, and then updates its policy to increase the likelihood of actions that led to higher rewards. By using the Bayesian ESN as the policy network, our agent can both learn from the environment efficiently and handle uncertainty naturally. By combining the strengths of reinforcement learning, the efficiency and temporal modeling of echo state networks, and the uncertainty awareness of Bayesian inference, we create a system that is both powerful and practical. This approach enables agents to learn faster, make safer decisions, and generalize better, even in environments where data is limited or uncertainty is high. In the next part of this tutorial, we'll walk through the implementation step by step, so you can see exactly how to build and train a Bayesian echo state network policy gradient agent for your own projects. If you'd like to experiment with this yourself, the source code for this project is publicly available on our GitHub. You can find the link in the description of this video. We encourage you to explore, run the code, and try extending the ideas to your own environments. In this part of code, we're looking at two foundational utility functions that support the integrity and robustness of our reinforcement learning experiments. The first function, setSeed, is all about reproducibility. By setting the random seeds for both NumPy and PyTorch and configuring the backend to behave deterministically, we ensure that our experiments are repeatable. This means that if you or someone else runs the code with the same seed, you'll get exactly the same results, even when running on different hardware or with GPU acceleration. This is a key practice in both research and production, where understanding and verifying results is crucial. The second function, reset.env, addresses an important compatibility concern with the OpenAI GIM library. Over time, GIM has updated how its environments are reset, changing the format of what's returned. Our reset.env function checks for these differences and handles them automatically, so our main code stays clean and compatible with both old and new versions of GIM. It also supports seeding, further enhancing the reproducibility of our experiments. Together, these utility functions make our reinforcement learning code more robust, maintainable, and reliable, ensuring that our results are both trustworthy and easy to share or extend in future projects. Let's take a deep dive into our echo-state network implementation with a Bayesian readout and see why this architecture is so valuable in reinforcement learning tasks. We start with the Bayesian readout class. This layer is simple in structure but powerful in effect. It consists of a fully connected linear layer, which transforms the reservoir's output into the final output space, such as action scores for our agent. But what really sets it apart is the dropout layer that follows. By enabling dropout during both training and inference, we turn our deterministic neural network into a Bayesian estimator. Each forward pass will drop a random set of connections in the readout, meaning every prediction is slightly different. This property lets us sample from an approximate distribution of possible outputs for a given input, rather than producing a single, possibly overconfident answer. In practical terms, this helps our agent understand when it's uncertain about the best action, allowing it to explore more wisely. Now, let's talk about the main event, the Echo State Network class. The ESN is inspired by biological brains, which are made up of vast networks of sparsely connected neurons. In our implementation, we replicate this idea by creating a reservoir, a large pool of randomly connected units. The connection weights are set at initialization and not updated during learning. To make this reservoir useful, we carefully control its properties. First, the W in matrix connects the input to the reservoir. It's randomly initialized and scaled to ensure inputs are distributed widely across the reservoir units, providing a rich set of responses to every new input. Next, the W matrix sets up the reservoir's internal connections. These are also random and sparse, meaning each neuron only connects to a small fraction of the others. Before we use this matrix, we adjust its spectral radius, the largest absolute value among its eigenvalues. This is a critical step. Setting the spectral radius properly makes sure the reservoir's activity is neither too explosive nor too forgetful, so it can maintain meaningful echoes of past inputs for the agent to learn from. The network also keeps track of its own internal state. Every time it receives a new input, it updates this state using a leaky integration formula. This formula is important because it balances the influence of new information with the memory of previous states. The leaky rate hyperparameter controls this trade-off, allowing you to tune the ESN's memory for the task at hand. After each update, we normalize the state vector to keep the system numerically stable and avoid issues like exploding or vanishing activations. What makes the ESN unique is that after this complex and dynamic transformation, only the output layer is trained. The vast majority of the network, the reservoir, remains fixed. This design means the ESN can model temporal relationships in data with much less computational effort compared to fully trained recurrent neural networks. In the forward pass, all of this comes together. An input is projected into the reservoir, the internal state is updated and normalized, and the resulting state is passed through the Bayesian readout layer. When we use this model in reinforcement learning, we often make several forward passes for the same input, each with different dropout masks. By averaging these outputs, we get not just a prediction, but also a sense of how confident the model is, crucial for agents that need to balance exploration and exploitation. Altogether, this echo state network with Bayesian readout gives us a lightweight, powerful, and uncertainty-aware foundation for reinforcement learning agents, especially in environments with sequential structure and uncertain outcomes. This combination allows our agent to efficiently learn from experience, model temporal patterns, and make safer, more informed decisions. Now let's look at how we connect our echo state network to action selection through the policy network. The policy network class acts as the interface between the rich, dynamic representations produced by the ESN and the action space of the environment. When the agent receives a new observation, this policy network passes it through the ESN to capture both the current state and its temporal context. The ESN's output, known as logits, represents the network's unnormalized confidence for each action. We then apply a softmax function to these logits, which converts them into a proper probability distribution. This means each possible action is assigned a probability based on the agent's understanding of the environment at that moment. With this setup, the agent can sample actions according to these probabilities, naturally balancing exploration and exploitation, a key principle in reinforcement learning. In summary, the policy network wraps the ESN's temporal modeling power in a simple, reliable action selection layer, forming the heart of our agent's decision-making process. In this part of the project, we're bringing everything together with our main training script for the Bayesian Echo State Network Policy Gradient Agent. The script starts by ensuring compatibility across different GIM versions and imports all the modules we need. We begin training by setting a random seed, which guarantees that each run is repeatable and reliable. The cart poll environment is created, and the ESN-based policy network is initialized on the right device, whether that's a GPU or your local CPU. The core of the script is the training loop. For each episode, we reset the environment and step through it using our policy. Here's where the Bayesian element comes in. At each time step, the policy network runs several stochastic forward passes with dropout active, and we average the resulting action probabilities. This gives our agent a sense of uncertainty about its actions, making its exploration more robust and less likely to overfit or get stuck. After collecting all the rewards for an episode, the script computes the discounted return for each time step, normalizes these returns, and uses them to perform a policy gradient update. This process teaches the agent to favor actions that lead to higher cumulative rewards. Every 10 episodes, the script prints out the agent's total reward so we can monitor its learning progress. Altogether, this training script showcases how modern reinforcement learning practices like Bayesian uncertainty estimation, reproducible experiments, and robust policy optimization can be combined to create a powerful learning agent for sequential decision-making tasks like cart poll. That brings us to the end of our journey with reinforcement learning using a Bayesian echo state network policy gradient agent on the cart poll environment. Through this tutorial, we explored how to build reproducible experiments, leverage the power of echo state networks for temporal sequence modeling, and incorporate Bayesian uncertainty into our action selection for safer and smarter exploration. We walked step by step through the core utilities, the ESN architecture, the Bayesian policy network, and the complete training loop, showing not just how each piece works, but why these choices matter in practice. The end result is a modular, efficient, and uncertainty-aware reinforcement learning agent that you can use as a foundation for your own experiments and projects. If you found this video tutorial helpful, please don't forget to like the video and subscribe to the channel for more deep learning and reinforcement learning content. And remember, the full source code is publicly available on our GitHub. The link is in the video description. Thanks for watching and happy experimenting. Welcome to BrainOmega. Today, we're embarking on a hands-on journey to build a powerful time series prediction system using some of the most exciting tools in modern deep learning, transformers and echo state networks, ESN. If you've ever wondered how to tackle huge data sets, capture complex patterns over time, or experiment with state-of-the-art models, this video is your roadmap. We'll start with the big ideas, then gently dive into the actual code, showing you how each piece fits together. Whether you're new to machine learning or just curious about hybrid architectures, you'll find practical guidance and pro tips along the way. Let's first get our bearings. This project is organized into several Python files, each handling a key stage of the workflow. Main.py is our central command center. It downloads data, pre-processes it, initializes the model, and launches training. Dataset.py defines how we transform raw data into learnable sequences and prepare it for PyTorch's deep learning pipelines. Models.py contains the brains of our system, the hybrid transformer plus ESN architecture. Train.py handles the training and validation loop, including smart features like early stopping. Utils.py provides utility functions, such as our robust custom loss. And of course, we have a clear README to guide setup and usage. Let's explore these step by step and see how data flows through the pipeline. The full source code for this project is open to everyone and available on our GitHub. You'll find the link in the description of this video. I encourage you to explore the code, try it out yourself, and even contribute if you want. Having the source code will help you follow along with this tutorial step by step. One of the biggest challenges in time series analysis is structuring the data so that the model can learn patterns over time. In our dataset.py, we address this with two main components, a sequence creator and a PyTorch dataset class. First, we have a function called createSequences. Imagine you have a long stream of measurements, maybe network traffic data or sensor readings. This function slices that stream into overlapping windows, each of a fixed length, so the model can learn, given this recent history, what comes next. For every window, the target is simply the next value in the series. This is how we train our model to predict the future, step by step. Next, we wrap our sequences and targets in a custom class that inherits from PyTorch's dataset. This is a best practice, letting us easily batch, shuffle, and feed data to our model. When you call len on this dataset, you get the total number of training examples. When you fetch an item by index, you get both the input sequence and the target value as PyTorch tensors ready for the GPU. This modular design keeps things tidy and scalable, especially when datasets get huge. Now let's really dig into the core of our time series prediction engine, the hybrid transformer ESN model. This class brings together two world-class ideas: transformers, known for their ability to understand complex sequence relationships, and echo-state networks, ESNs, famous for their memory efficiency in time-dependent tasks. Let's break down the constructor step by step. Input projection. Our raw data, like a single feature per time step, is passed through a fully connected layer. This lifts the data into a higher dimensional space, D-model, giving the network more room to express relationships and patterns. Think of it like turning a single musical note into a rich chord. Transformer encoder. Next, we stack one or more transformer encoder layers, each with multiple attention heads. These layers let the model focus on important parts of the sequence, regardless of how far back in time they occurred. If you're new to transformers, attention means the model can way past events based on their actual relevance to the current prediction, not just how close they are. The dropout parameter helps regularize learning, fighting overfitting. Echo State Network, ESN. Reservoir. Now comes the fun part. We create a reservoir of neurons, a big block of nodes that mix and echo information as time passes. Input weights. Each new feature vector from the transformer is mixed into this reservoir using small, random, learnable weights. Reservoir weights. The reservoir is recurrent. At each time step, the previous state gets transformed by an internal connection matrix, We initialize these weights orthogonally for stability and scale them by a key parameter, the spectral radius. This is a core ESN trick. If the spectral radius is just right, usually less than 1, the reservoir will remember just enough of the past without becoming unstable or forgetful. Sparsity. To mimic how biological brains and real-world networks work, we zero out a large percentage of connections using a random mask. This reduces computation and makes the memory more selective. So, readout layer. Finally, the entire temporal history is distilled down to a single output using a linear layer. This is our prediction, usually the next value in the time series. The forward pass is where the hybrid power shows. Each sequence in the batch is projected and transformed. For each time step, the output of the transformer is fed into the ESN reservoir. The TAN activation is used here, a classic choice for keeping the reservoir's values nicely bounded and non-linear. The internal state is updated at every step, letting it echo the effects of past time steps forward, but always with a twist. The latest transformer-informed features influence every update. By the time we reach the end of the sequence, the reservoir state is a sophisticated blend of all the sequence information filtered by both attention and memory. The readout layer then maps this powerful high-dimensional state to our prediction. Why does this hybrid work so well? Transformers give flexible global pattern recognition, great for trends, periodicity, and sudden jumps. ESNs contribute fast, low overhead memory, tracking fine details and local interactions. Together, they allow the model to understand what to remember and how to remember it. For anyone tackling real-world time series, where trends, outliers, and subtle dependencies all matter, this design is both cutting-edge and practical. You can experiment with more layers, different spectral radii, or even change how the reservoir is updated to adapt this framework to your specific problem. Let's walk through the heart of our training process in train.py, focusing on the train and evaluate function. This is where your model learns and where all the magic of modern deep learning best practices comes together. We start by initializing two lists, train losses and test losses, which will store the average loss for each epoch. This makes it easy to plot learning curves and spot issues later on. We also set best test loss to infinity at first, so any real loss value will be better, and we use early stop counter to track if our model stops improving. Now for the main training loop. For each epoch, we switch our model to training mode using model.train. This is crucial in PyTorch. It enables features like dropout and batch normalization, which are only meant to be active during training. We set the epoch's training loss accumulator to 0. Next, we loop over all the mini batches from our train loader. Each batch contains a chunk of input sequences, X batch, and the corresponding targets, Y batch. We make sure both are on the correct device, CPU or GPU. Notice the unsqueezed left parenthesis negative, one right parenthesis. This adds an extra dimension to our input, matching what the model expects. For example, left bracket batch, sequence, one right bracket. Before each step, we zero out the gradients with optimizer.zeroGrad. This is vital because by default, PyTorch accumulates gradients. Forgetting to reset them would mix up updates from multiple batches. We run our batch through the model to get predictions, outputs, compute the loss against the ground truth, and call loss backward to compute gradients. The optimizer step method then updates all learnable parameters based on these gradients. The total loss for the epoch is updated by adding the loss for this batch. Once all batches are processed, we average the loss by dividing by the number of batches and append it to our list of training losses. After training, it's time to evaluate. We switch the model to evaluation mode with model.eval. This tells PyTorch to disable dropout and use running stats for batch norm, so results are consistent and not random. We use torch.noGradContext to save memory and computation, since we won't be updating the model here. Inside this block, we repeat the batch loop for the test data, moving each batch to the right device, getting predictions, and summing up the loss. Again, we average the total loss at the end and store it. We also step the learning rate scheduler based on the test loss. This can automatically reduce the learning rate if improvements plateau, a trick that helps the model escape local minima. For transparency, we print out the training and test loss for each epoch so you can watch progress in real time. Now comes early stopping, which is a huge help when working with big data. If the current test loss is lower than our best ever, we reset the early stop counter and remember this as our best model so far. If it isn't better, we increment the counter. If the model hasn't improved for a set number of epochs, patience, we print a message and break out of training early. This saves time, resources, and usually gives you the best generalizing model. Finally, the function returns lists of train and test losses, which you can use for plotting or further analysis. When it comes to deep learning, the loss function you choose can make a huge difference, especially for regression problems like time series forecasting. Here in utils.py, we use a clever alternative to the classic mean squared error, the log-cosh loss. Let's break down the code line by line. First, we calculate the prediction error for each data point. This is just the difference between what the model predicts, y_pred, and what the actual value should be, y_true. In PyTorch, this works element-wise, so you get an error for every single prediction. Next, we apply two mathematical functions, the hyperbolic cosine, cosh, and the natural logarithm, log. The hyperbolic cosine grows almost exponentially for large positive or negative numbers, but for small values, it's very close to 1. When you take the log of the cosh, you get a function that looks a lot like a squared error near 0, so it still punishes small mistakes, but grows much slower for big errors. This means the loss is less sensitive to outliers. Occasional wild data points won't totally dominate your model's learning process, which is a common headache with mean squared error, especially in real-world data. Finally, we take the mean of all these losses to return a single scalar value. PyTorch's Tensor Operations make all of this run fast and efficiently on your GPU. This approach is particularly handy when your data set isn't perfectly clean. Maybe there are measurement errors, occasional transmission spikes, or rare but huge anomalies. With log-cosh loss, your model can learn the general trend without getting distracted by those occasional big mistakes. You can easily swap in any custom loss function in PyTorch, just like this one. Try experimenting with different loss functions on your data. You might be surprised how much it can improve stability and generalization. With our data pipeline in place, main.pa takes the role of conductor, orchestrating every stage from raw data to trained model. What's really special about this script is how configurable and reproducible it is, just like you'd want in serious research or industry work. First up, automatic dataset download. No more worrying about manual downloads or mismatched file paths. The Kaggle Hub library grabs the right dataset for you, meaning you can switch to new data sources with a single argument. Fantastic for benchmarking or exploring new domains. Next, we load and preprocess our data. We use pandas to read the dataset and focus on the length column, which is a typical feature for time series like traffic, network load, or signals. Limiting the number of samples, max data, keeps things memory efficient. We scale everything to 0, 1 using min-max scaler. This step is crucial. Deep learning models are much more stable when features are normalized, letting the optimizer update weights smoothly and avoid numerical blowups. Then, we prepare sequences for supervised learning. Using our own createSequences function, we turn a long-time series into overlapping input-output pairs. Each input is a chunk of history. Each target is the value that follows. We split the data into training and testing sets. Always set a random seed, random state for reproducibility. Next, we wrap the arrays into custom PyTorch dataset classes and use data loader for efficient batching and optional shuffling. Now we initialize our hybrid model and get the device right. The script automatically uses your GPU if available, a huge speed up for big experiments. The model is parameterized from the command line, so you can tweak everything: hidden sizes, number of layers, reservoir memory, attention heads, just by changing arguments. This makes testing new ideas or tuning hyperparameters fast and consistent. For optimization, we choose AdamW, which is robust to noisy gradients and helps prevent overfitting with weight decay. Our learning rate scheduler is set to monitor test loss. If progress stalls, it automatically shrinks the learning rate, often helping the model escape flat spots and find a better solution. The actual training and evaluation happens with a single function call, passing in all the tools and parameters. All losses, metrics, and checkpoints are handled inside, making the script both clean and powerful. Finally, the argument parser gives you complete control from the command line. This is a best practice for any serious machine learning project. You never have to touch the code to run new experiments, just adjust the flags. It's easy to log, easy to repeat, and perfect for running on servers or in collaborative teams. This pattern, modular, command line driven, and device aware, is how professional ML pipelines are structured in both research and production. It's designed for speed, reliability, and extensibility, so you can push your ideas further, faster. And there you have it, a complete modern pipeline for time series forecasting designed for large-scale datasets and rapid experimentation. Each file plays a crucial role, from data preparation to model definition and training. The modular, configurable design means you can easily extend or adapt the system, try different datasets, play with the model's hyperparameters, or swap in new architectures. As a final tip, always start with a clear structure like this. Break your project into logical parts. Keep your code modular and use command line arguments to make experimentation painless. This not only makes your research reproducible, but also lets you scale up to bigger and more complex challenges. Thanks for following along on BrainOmega. If you enjoyed this deep dive, please like, subscribe, and leave your questions or ideas in the comments. What should we build next? Happy coding! When most people think of ChatGPT, they think of asking a question and getting an answer back instantly. But what if you could make something smarter? Something that doesn't just answer questions, but actually plans what to do, calls tools like a calculator or a search function, and then reflects on its answer before telling you? That's what we mean by an agentic AI, an AI that doesn't just respond, but acts. In today's tutorial, we're going to build a from-scratch agentic AI in Python. This is not just a coding exercise, it's a practical framework you can extend into your own assistants, automation scripts, or even game characters. We'll start simple. Our agent will propose a challenging question, solve it using reasoning and optional tool calls, and give a polished answer. Along the way, you'll learn about safe API key handling, OpenAI's function calling, memory buffers, and scalable project structure. We'll be using Python 3.10+, the OpenAI SDK, and Python.env. You don't need to know everything about AI to follow along. I'll explain each concept as we go, By the end, you'll not only understand how to run this project, but also how to extend it with your own custom tools. Before we write any code, we need to decide where everything will live. Many beginners start with a single .py file, and that's fine for quick experiments, but it quickly becomes messy as your project grows. That's why we're creating a clean, modular folder structure from the start. In our src/folder, we'll put all our Python code. Inside src tools, we'll keep small, self-contained Python scripts that add abilities to our agent. For example, a safe math evaluator. The src/agent/folder will contain the brain of our AI, the logic that handles planning tool calling and producing answers. We'll also have a config.py file for loading settings like API keys and a run-demo.py script to run our agent. This separation makes it incredibly easy to grow the project. If you want to add a Wikipedia search tool, drop it in Tools/. If you want to make your agent store conversation history to disk, you'll add that in Agent Core PY. Professional developers structure code this way because it's easier to test, maintain, and share. The source code for this project is available on our GitHub. You can find the link in the description of this video. Now let's handle dependencies. Instead of using a plain requirements.txt file, we're going with the modern pyproject.toml format. This file not only declares what libraries we need, but also describes our project for package managers. That's especially useful if you ever publish your code or work with others. In pyproject.toml, we specify our Python version requirement, project metadata, and dependencies. Python.env for environment variable handling and OpenAI for making API calls. We also include a configuration for rough, a fast Python linter, which helps keep the code neat and consistent. A good tip here, always specify minimum versions for your dependencies, like OpenAI greater than or equal to 1.40.0. This ensures that you're using a version that supports all the features in your code, but still lets you upgrade later. This habit saves you from a lot of "it works on my machine" issues. Security is important when working with APIs. You should never put your API keys directly in your Python code, especially if you're going to share it on GitHub. Instead, we use a .env file that contains our sensitive values and load them into the program at runtime. The .env example file is just a template that shows what variables you need to set without revealing your real keys. In our .env example, we include OpenAI API key and also 3 model selection variables, one for the main model, one for a faster model, and one for a tiny, very fast model. This makes it easy to switch between high quality, low latency, and ultra cheap calls without changing any code. Just edit the .env file and restart the program. The best practice is to add .env to your .gitignore so it never gets pushed to GitHub. If your key is ever leaked, even once, you should consider it compromised and replace it immediately. This file is all about configuration management. At the very top, we use .env to load our .env file so all those environment variables become available to Python. We then wrap the settings in a data class called settings, which keeps everything neatly organized and type safe. If the API key isn't found, we immediately raise an error. This is called failing fast, and it's a good habit. It stops the program before it can run into confusing errors later. The make client function returns an OpenAI client object, which we'll use to talk to the API. Even though the OpenAI SDK can read the API key automatically from the environment, creating a client explicitly makes your code easier to test and more flexible if you ever need multiple clients with different settings. This is our first example of giving the agent a tool. Think of tools as little Python functions that the agent can call when it needs help. This one, evaluate math, is a safe math evaluator. It can run simple arithmetic, take square roots, or compute factorials. We use a typedict to define the input schema, basically a contract that says, if you want to use this tool, here's the data format you must give me. This is important because OpenAI's function calling feature needs a JSON schema to understand how to call your tool. In the eval mode, we strictly limit the allowed characters to digits and basic math symbols. This prevents dangerous code from being executed. In real-world apps, you'd use a proper math parser library for extra safety, but this is enough for our example. The key takeaway is that tools extend your AI's abilities beyond just text generation. This is where our agent's brain lives. The agent class manages tools, memory, and the logic for proposing and solving questions. The memory here is very simple, just a list of recent conversation turns, but even this small feature makes the agent more coherent. The propose question method uses our fast model to generate a difficult question. We use a prompt that specifically instructs the model to output only the question text, no explanations or answers. This is a small but important detail. When you want precise output, be explicit in your instructions. The solve method is more interesting. First, it builds a system message to set the assistant's role, a precise problem solver that uses tools when arithmetic is needed. We pass in our tool definitions using OpenAI's function calling feature. If the model decides to call a tool, we execute it, add the result to the conversation, and then ask the model again for the final answer. If no tool is needed, we use the model's first response. This pattern, plan, act, reflect, is at the core of agentic AI systems. The agent class is the central brain of our system. It's responsible for orchestrating the conversation, deciding when to use external tools, and keeping track of what's already been said. You can think of it as the conductor in an orchestra. It doesn't play the instruments itself, but it decides which section should play and when. Inside the class, we store three important things: the OpenAI client and settings, so the agent knows how to talk to the models; a registry of available tools, so it knows what actions it can take; and a small memory buffer, so it remembers the recent conversation. Even though our memory is just a list of message dictionaries right now, this tiny feature already makes the AI more coherent because it allows each new step to be informed by the previous ones. The propose question method is where the agent starts its reasoning journey. Here, we use our fast model to generate a challenging question. The reason we pick a smaller, cheaper model is that this step doesn't require deep reasoning power. It's just a creative prompt. The real trick here is in how we write the instructions. We explicitly tell the model to output only the question text with no explanations or answers. This might seem like a small thing, but in prompt engineering, specificity is key. Without that instruction, the model might produce extra fluff or even give away the answer. Being clear and restrictive in your prompts is one of the simplest and most effective ways to improve AI reliability. The solve method is where things get interesting. This is where the agent takes the question and decides how to respond. First, it sends a system message that defines the assistant's role. In our case, a precise problem solver that uses tools when arithmetic is needed. This is crucial because it sets the behavioral boundaries for the model. Next, we pass in the list of tool definitions using OpenAI's function calling feature. This tells the model exactly which tools exist, what they're called, what they do, and what arguments they accept. If the model decides that one of these tools can help solve the problem, it will respond with a tool call instead of a direct answer. We then execute that tool in Python, capture the output, and feed it back into the conversation. Finally, we give the model another chance to produce the final answer, now informed by the tool's result. If the model doesn't think a tool is needed, we skip straight to using its first response. Either way, the pattern here is the same: plan, act, reflect. First, the agent plans its approach, then it acts, possibly by calling a tool. Finally, it reflects on the result and produces a concise, polished answer. This loop is the foundation of agentic AI systems, and you'll see variations of it everywhere in modern AI tooling. The beauty is that once the structure is in place, you can add more tools, extend the memory, or even introduce multi-step planning without changing the core logic. This is the script you'll actually run. It loads settings, creates the OpenAI client, and initializes the agent. Then it goes through two phases. First, asking the agent to propose a question, and second, asking it to solve that question. I use the rich library here for colored output in the terminal, but it's optional. The key thing is that this script shows the agent in action. If you're making a video, this is where you can pause after the question and challenge your viewers to solve it themselves before revealing the AI's answer. And there you have it, a fully working, from-scratch agentic AI in Python. We didn't just build a script, we built a framework that can think, act, and adapt. Along the way, you saw how to securely manage API keys, design a clean project structure, define and register safe tools, and use OpenAI's function calling to give our AI real-world capabilities. We also explored how even a simple memory system makes responses more coherent, and how the plan-act-reflect loop is at the core of almost every modern AI agent. The best part is that this is just the foundation. You can now add your own tools, maybe a web searcher, a data visualizer, or an API that hooks into your own systems. You can extend the memory so the agent remembers past conversations for days or weeks, or you can experiment with different models to find the perfect balance between cost, speed, and accuracy. If you've been following along, you now have the building blocks to create your own custom AI assistants. Keep experimenting, keep adding capabilities, and most importantly, keep your tools safe, your prompts clear, and your design modular. That way, your AI will always be ready to grow into something even more powerful. If you found this tutorial helpful, give it a thumbs up, share it with a friend who's into AI, and don't forget to subscribe to BrainOmega for more in-depth AI and coding tutorials. Hit the bell icon so you never miss a future project. Thanks for watching, and I'll see you in the next tutorial.